Hello, everyone. Welcome to the fifth Applied Active Inference Symposium, Day 3, November 14, 2025. My name is Zohre Rahmanajad. I'm honored to introduce the first presenters of today, Steph Macurdy and Andrius Kulikauskas, presenting Money and the Free Energy Principle. Okay, the stage is yours, please.
Thank you. Thank you to the Active Inference Institute for hosting this symposium and having us give this talk. This is Money and the Free Energy Principle. My name is Steph Macurdy. I'm the head of blockchain research and education at Wolfram Research. And my collaborator is Andrius Kulikauskas, PhD in mathematics, who runs Math for Wisdom. In this presentation, we thought it would be a good idea for me to share a little bit about my story and how I arrived at the Active Inference Institute. And I'm going to share a connection that I see in that I believe is true in free energy principle and money. And then I'm going to give it to Andrius to speak a little bit more about the math of energy, entropy, and free energy, and pull back the curtain a little bit. So my story begins around 2014 when I read these two books back to back, and they kind of set the stage for the next decade of my two approaches of research. One direction was Cosmic Evolution by astrophysicist from Harvard, Eric Chai-San, which kind of said something around the lines of um, how much free energy is flowing through a physical system normalized by mass and time. And it points to this evolution across the universe in a direction of complexity. And in the other direction, on the other end of the spectrum, was this book called Why Information Grows by Cesar Hidalgo, a statistical physicist from MIT. And that kind of gave me another way of seeing a similar story, which was how do you measure and determine order and structure in systems? And that kind of painted a picture of information growth or entropy minimization. So this colored uh, a spectrum or two roads for me. And I'm going to just fill in some personal events over the past 10 years that help color this in. So in 2015, I found Bitcoin. And while I didn't understand it completely technically at the time, I became fascinated by the consensus mechanism called proof of work, which to me really was the connection between energy, computation, and value. And it was interesting because while reaching this distributed consensus in a new way, we could organize economies or economics or money in different ways. And that gave me just a sense that we could be looking at either ends of the spectrum. In 2017, I had another question that I really wanted to answer, which was about solar energy. So I went to work for Tesla in 2017 to understand a little bit more about the proliferation of solar energy and solar panels. And it was obvious that in nature, the sun provides ample free energy. And I expected the same to be true for our economy, that more of our energy production would come from the sun. Tesla had an interesting approach, which said there are constraints and limitations on the current electrical grid infrastructure. To get around that, one needs high free energy density of batteries. So that colored in another kind of 2 points on my spectrum here. Then in 2020, I learned about Wolfram physics. And this was Stephen Wolfram's fundamental physics project. And Stephen Wolfram has an approach to physics which is deeply computational. And that's computation with a capital C. It's how do you look at simple rules and how does that lead to emergent complexity? And that filled in a couple more gaps in my understanding of the major pillars of physics: general relativity, quantum mechanics, and statistical mechanics, or he calls the second law of thermodynamics. So I was seeing this happen. I joined Wolfram. I was tasked to lead the research team at Wolfram Blockchain Labs. And there I studied many blockchains, many consensus protocols, and many cryptocurrencies. And I learned about a new blockchain in 2024 called Quai Network, which really captured my attention for two reasons. It has a novel consensus protocol called proof of entropy minima, which is a variant of Bitcoin's proof of work. And it has a two token architecture, which is important because money has several important characteristics. And if you have more than one token, you can separate those characteristics and be more true to what those characteristics of money might be. So all of my attention over the past year and a half has been on understanding that more, and that led to coming to the Active Inference Institute a couple of months ago, where I met Andrius. We're both investigating the math of active inference, and we hit it off. Andrius began working for me in helping me to understand the two token architecture of Quai Network and the math of active inference. And we've had a wonderful back and forth over the past couple of months investigating these things. And so it feels like this is my story, and I've been orbiting around the free energy principle. I've been looking at it from a physical energy perspective and an informational computational perspective. And all of those things kind of have brought me to want to learn more. So I'm here as an investigator, still on a path and journey trying to learn more. But I wanted to say one thing technically about Quai Network and about the consensus mechanism, because it might show a little bit more about what we mean when we say proof of entropy minima. So this paper in 2023 by Carl Kreeder and Shrikara Shastri put out the way that this is calculated. So proof of Shannon entropy minimization is what we're speaking about here. And what we really want to talk about, at least in the blockchain world, is when Bitcoin is doing its mining. This is what people refer to. It's running this secure hash algorithm with a 256-bit digest. And this algorithm, SHA-256, has an output of 256 ones and zeros. And so the total possible state space of any particular hash is 2 to the 256. Now, what can you do with that? Well, if you put a simple rule or a simple constraint on that state space, for example, if you look at the number of consecutive leading zeros in the output of a SHA-256 hash beyond some threshold, you can start to find interesting properties, and you can use those properties in a distributed computer. So here's an output, 256 bits. I've colored in the first 9 leading zeros, and that's what we're measuring. And we say in this space, 256 bits, the first 9 in this example are zeros, and that lets us say something like we are going to quantify that number of bits and remove them or accumulate them. We're going to accumulate them from one block to the next perpetually. And in that way, what we're doing is we're accumulating uncertainty and removing it. And that's the sense in which we're talking about proof of Shannon entropy minimization. That's a lot of words, but what does it look like visually? Here is the output of 5,000 SHA-256 outputs in integer form. And as you can tell, there's not much signal here. But when you impose a constraint like this simple rule, consecutive leading zeros, you can start to see that we get this kind of hierarchy of events, that some events are rarer than others. And you can use that fact to sequence events in a hierarchy, and that can be used as setting a certain time interval in a distributed computer. Because there's not one global clock in this distributed computer. And so being able to get into the nuance of establishing a frequency or a time interval in several levels really gives us this hierarchical ordering, which means we can establish when one output is greater than another, and that can lead to establishing a dominant blockchain and a subordinate blockchain. And that's important because we can distribute the algorithm in any geography and get the same statistical results off of it. So we're lifting some statistical properties out of this distribution of work. And Pi Network takes this to its, as far as I can tell, takes it to its limit and just really extends and expresses that idea to scale to a large degree. And so the rule is simple. It is the change in entropy is the number of states removed from one block to the next, but it's a small difference that makes all the difference. And I just want to say one last thing. The other important fact about Pi Network is that it is a two-token architecture. And this is important because in the characteristics of money, like store value, medium of exchange, and unit of account, if all of those are lumped into a single token, it makes that token carry a lot of burden. And when you separate the characteristics of money, you get around something called Gresham's paradox, which simply states that if you've designed a global decentralized monetary system to make a superior form of money, let's say in this case it's Bitcoin, it could be gold, the participants are incentivized to hoard that money. And that's in direct tension with another characteristic of a monetary system, which is if you're hoarding, you're not exchanging. And so it diminishes that value. So it's important that we kind of pull apart these characteristics. And in this network, because we're measuring entropy, we are playing with the idea of calling the chi token an entropy measure, and we're calling y an free energy measure. So there's something here to play with, and it's still in pursuit. But with that said, I want to pause there and let Andrius take the reins here and speak about the math of energy, free energy, and entropy. Andrius?
Thank you, Steph. And thank you to the Active Inference Institute. Steph and I met through the Active Inference Institute, so I recommend if you want to meet people, that's the place to go. And I am always interested in meeting people because I lead an investigatory community, Math for Wisdom. So check that out. And so thank you, Steph, for all of your lifelong insights and intuitions. It's a wealth that brought you to Chi and Kwai and brought you as an investigator to try to make sense, does this work? Could it work? Should it work? What would that look like? What's the structure? And that brought you to active inference because, as you said, there's these two currencies, one that seems related to entropy and scarcity, the Kwai, another that's related to energy, the cost of electricity, and that's Chi. And what's the natural relationship between that in an economy? So this slide shows the summary of what I want to talk about, which is this equation relating energy equals free energy plus entropy. And so, of course, free energy is active inferences, valuable asset, and so that's why we're here. And so this formula is very good, and I've always wanted to understand it better. So my theme is that, and this was said by Carl Friston, quoting Richard Feynman at a keynote address, that if I create it, I can understand it, which kind of means like a lot of times I'm not understanding things, I'm not able to create them. So some things I will tell you I know, and some things I'll tell you I don't know. So the summary is that to explain this mathematical equation, and then to explain in terms of cryptocurrency, the distinction between belief in an economic system and belief in the economic system. Those are the themes. And then I have a PhD in math, but specifically algebraic combinatorics, which is the math for counting things. But really what it means is if you look at an algebraic equation, can you say what it's actually trying to tell us? You know, what is actually, what does it mean really? You know, so the way I write these equations, I write them out like this. And if you'll see, the entropy term has a q of x and a log of 1 over q of x. But the energy term has a q of x and a log of 1 over p of x comma y. These are probability distributions. And the main theme of my comments is that here they're different. But if you made this equal to q of x, then you would get entropy. So this kind of leads to the theme that entropy is a sort of degenerate energy. And so now let me talk about energy. I mean, first I'll talk about entropy, and then I'll talk about energy. So let's rethink these things. And you may have seen this formula for entropy. I've always been curious, like, why does it have a minus sign? It becomes very hard on my mind. So it turns out that negative of a log is just log of 1 over q of x. So first of all, you'll always see me writing this because I'm allergic to negative signs unless they really have a purpose. Okay, so this is my personal allergy. Another thing is that, and Steph saw that this is important, q of x appears in 2 places. That's like one actor in 2 roles, okay? So it's important to be not confused, you know, that they're playing 2 very different roles. One will be knowledge gain, and the other one will be the knowledge lens. So you can see there's a distinction here between an observer and an observed. The knowledge lens is all about the expected value, and that's coming from an observer looking at everything through a lens of different probabilities they're assigning, or sometimes they're called different weights. But what are they looking at? Well, they're taking the expected value of this term, which is the knowledge gained, okay? Why is that the knowledge gained? Well, this is a way of writing. And so let's remember that this is a probability distribution. So that means that these values, you know, x can be cat or whatever. The probability of cat will be a number, maybe like 30%, or, you know, 0,3, or 0.3 if you're American. I got living in Lithuania, so 0,3. So q of x is going to be greater than equal to 0 and less than or equal to 1. Now, if you're very astute, you'll note that if this is 0, this is going to be a big problem because 1 over 0 is against the law. So, but here, this could be 0. So all of a sudden, we're seeing that these 2 roles start to imply different things. That in the case of what I call the observed, you're not allowed to have 0 probability. I mean, nature wants it to be there or just don't talk about it, okay? But from the point of view of the observer, you're in control. You can carve things up. You can say, hey, nothing happened here. I'm observing, okay? So there's a huge qualitative difference, and we pick up on this by caring about these things. So let's go back to say this is a positive number, and it's less than 1, okay? Less than or equal to. If it was 1, that means you're certain. Then it would be 1 over 1, that's 1. Log of 1 is 0. So when you're certain the entropy is 0, there's no, I mean, not the entropy, but this part's 0, and the knowledge gained is 0, So that makes sense. No knowledge gained if you're certain. But otherwise, like let's say this is 1/2, 1 over 1/2 is going to be 2. And you can see that whatever this fraction is, but if you flip it over, it's going to be bigger than 1. And when you take a log of something that's bigger than 1, it's going to be bigger than 0. Okay, so these are positive numbers. So negative log of q of x is actually a positive number. Okay, that's one point. And so let's look more specifically, and we're going to be working in log base 2 because it's these probabilistic choices, this or that, that's comfortable, but we could be working in other logs. But if you look at 1 over 1/8, so 1/8 is a probability, you flip this over, it becomes log 2 of 8. 8 is 2 times 2 times 2, we write it as 2 to the 3. And then log base that is just pulling down that exponent, it's 3. Okay, so, and that means that you have 3 choices. So like 1/8 would be the probability of flipping a coin 3 times and getting something specific like tails and then head. Well, that's basically 3 bits of information. That's 3 choices, binary choices. So that's 3 units of knowledge gained. And so when we rethink entropy, we see that all these numbers are positive. Everything here is positive. And then, let's look at this knowledge lens and just talk about that. So your knowledge lens could be how you're looking at the world. Let's say you're looking planetary-wise, and let's say it's very crude, but you're going to say, look, it's 1/4 land and 3/4 water, okay? So if you want to talk about the ruggedness or smoothness of the planet, you'd say, well, 3/4 is very smooth, and then 1/4 is ruggedness. So it puts things in perspective. But it could be, let's say, 1/4 youth, 3/4 adults, okay? Then you want to look at the loudness of music that's preferred at a festival. You could balance it in like that. Or it could be like the relationship between me and everybody else. So it could be like 1/4 me in terms of how we're feeling and 3/4 everybody else. More likely, it's more like 3/4 me, 1/4 the rest of you. So that's how it's balanced. So these are examples. You can see how then that would, then you can actually calculate a case. So let's say let's put together these knowledge lenses. So let's say it's 1/4. To do entropy, you see, these are both the same thing, but they're in different situations. So 1/4, and you flip over the 1/4, that'd be 4. 1/4 times log 2 of 4, plus, let's say 3/4, log 2, you flip over the 3/4, you get 4/3. So if we calculate it out, 4 is 2 times 2, so log 2 of 4 is 2. 1/4 times 2. Log 2 of 4 over 3, that's basically roughly 40%, which is 2 over 5. I just made it, I like fractions, so I wrote it like that, times 3/4, okay? So the knowledge lens is the first fraction, and then the knowledge gained, the surprising. So in the case of the 1/4, like, it's more surprising, you get 2 in terms of the land part, but the water part's less surprising. That's 2/5 of surprise on that end. So, and then 3/4 is how often you have that. And you put it all together, 1/4 times 2, that would be like 1/2. I can write 10/20. 3/4 times 2/5, that'd be 6/20. So you can add it up. And you can see like who contributed more entropy. Actually, it was the land that contributed more entropy, because it was only 1/4, but it contributed a lot of surprise. Okay, so the land contributed more. The rarer one contributed more entropy, these building blocks. The water, there's 3/4 water, but it's just not as surprising. So it's not collecting as much entropy. And so this is the expected value of knowledge gained. The knowledge gained from the land is 2, like, wow, something happened. Knowledge gained from the sea, like if an asteroid hits into the sea, it's, oh well, not such a big deal, not such big news. So that's 2/5. But the chance of it happening, this asteroid falling on land or water, well, 3/4 chance it's going to fall there, 1/4 there. So you're kind of adding it up. And then maybe something I'll be talking about, it's interesting, this relationship, 10 to 6, right? 10 over 20 to 6 over 20. We'll be looking at that, okay, how that changes. So why don't we do that? Why don't we go to the next slide? Because we're so into entropy, we really want to just add it, because you'll see I actually don't understand it. So, and I think it's a secret probably, like no one really understands it, and we'll try to show that why, but it's entropy is ambiguity though. I think that part I kind of understand, because entropy means that well, from a physicist's point of view, and I have a bachelor's degree in physics, it means that you have more possible configurations that will give you the same result. Okay, so it becomes like a combinatorial thing. So it's very that part's the ambiguity. And doubling entropy is something conceivable, kind of straightforward. Let's do that. And so we'll look at a specific case. Let's say there's n equal probabilities, each with 1 over n, and n times 1 over n equals 100% is 1. Okay, so the formula for entropy becomes this. You're summing over all the possibilities, and each of these building blocks has the probability in front, which is 1 over n, times log 2 of 1 over the probability, which is 1 over n. And you'll flip this over, you'll get n. Okay, so let's look at it concretely. And we did this one, so 8 times, but see, now there's 8 of them because we've got, that was just a separate building block, but now we're going to have all 8 building blocks. And what you'll notice is that the 8 times 1/8 cancel. So when everything's very uniform, there's nothing really contributed by the knowledge lens to entropy. It's kind of saying like we roll out, we're not affecting the knowledge gain because we're just very neutral. We're so neutral, we're not going to really affect knowledge gain. So it's all left to the log 2 of 8. But you'll see that, okay, log 2 of 8, we saw was 3. If we do it with 64, which is 8 squared, 64, you'll get again 1 over 64. That part cancels. That's just all neutral. It's 64 equal probabilities, each with 1 over 64 chance. Okay, you'll look at the log 2 of 64. This is the knowledge gained. That's 2 to the 6 because it's 8 times 8, 8 squared, or it's 2 cubed times 2 cubed, so that's 2 to the 6, so it's going to be 6. And so you can see it doubled, okay? So the lessons is that in this particular case, when everything's very neutral, there's the knowledge lens is, has equal probabilities, then the only contribution is from the what we call surprise, I call knowledge gained, and that in order to double it, you really have to square it, okay? So that's a big deal. Like you have to square it if you want to double the entropy. If you want to double the knowledge gained, and so basically like if you threw a coin 3 times, you got to throw a coin 3 more times, okay? And then so that'll be squaring. So like the entropy, if you did 1,000 computations or choices, let's say, right? And you want to double the entropy, you got to go up to 1,000,000, okay? Or if you want to go up from 1,000,000, you got to go up to not 1 billion, but 1 trillion, right? Like, so doubling entropy is not something you would want to ever do, really, especially not in that type of SHA-56 game, where it's all uniform, okay? So doubling's clear. Now, what about halving, though? Okay, because not everything's uniform. And so if you go backwards, okay, you can go backwards from 64 to 8, 8 to, well, let's say we can go to 4 to 2 and whatever. So you get to 2. How do you go halve that, right? Like, where do you go, right? So that's this diagram. If you only have 2 choices, one will have probability x, and the other one will probably have 1 minus x. So like if x is 10%, then the other one would be 90%, right? And so you add this up, this will be x over log of 2, 1 over x. This will be 1 minus x, log 2 of 1 over 1 minus x, right? Well, you can play around with that. And I drew this blue graph to show that because I don't know how to solve that. And I don't think anybody knows how to solve this type of thing. Unfortunately, but we can graph it with my Excel spreadsheet. That's my computer of choice. And so then, or actually I use OpenOffice Calc, I'll admit, I can't afford Excel. So 0 to 100%, and then the entropy goes up to 1, okay? So 1/2 log 2 of 2 plus 1/2 log 2 of 2, log 2 of 2 is 1, 1/2 plus 1/2 is 1. You can believe me on that if that was too fast for you. But the question is, okay, this will go down. So that's the peak. So kind of makes sense. Maximum ambiguity when both probabilities are the same. Now we could get half the entropy. I'm sorry, maximum, entropy and maximum ambiguity. We could get half the entropy if we were willing to skew it, okay? And it turns out that happens at 1/9. So it's 1/9 this way, 8/9 that way for some magical unknown reason. But that 1 to 8 ratio, and this is approximate, it's these are real numbers. So, but I like fractions. So 1/9 to 8/9, that is when this goes by 2. And so I made this whole thing like, if you want to go half again, it'd be to get 1/4, it'd be 1/24 to 23/24, 1/8, 1/57, 1/58 to 57/58, and you can see the sequence going down. And so that is a fascinating sequence. And these integers are not known. I mean, they're not in the Encyclopedia of Integer Sequences, okay? So that means that this is treading new ground, right? But you could see this one attention because, like, in order to have the ambiguity, that means that you somehow are able to skew things to get half, okay? And if we saw, and if you want to say, well, who's got the ambiguity part, right? Like, is it in this A or is it in the B part, right? So if A is the 1/9 part, or is it in the B part? Well, it's 2.3 of, this will be 2.3 to 1, okay? But when you go to 1/24, it's going to be 3.2 to 1, and then 4.1 to 1, and 4.9. Now, this is very nice because, instead of these huge numbers growing, like, this is growing slow, first of all. So when you want to, like, we were doubling, like when we were going up to double the entropy, we're just going up like crazy. But now all of a sudden, we're just getting a slightly more certainty by saying we're going to have a slightly smaller percentage and then a slightly smaller percentage, and then we're going to feel like the knowledge gained by halving is going to be halved. Let's see, I got to be careful. The expected knowledge gain, let's say. The expected knowledge gain to be halved. So just very curious, but this almost looks like the integers, but these aren't integers. And of course, these are rounded, but these aren't integers. So there's a whole world, I call these invisible numbers, okay? And so that's what's coming up. So I went too long on this, but now you feel like you don't know entropy and I don't know entropy. We're even, okay? So let's talk about energy then. So energy, I also don't know about energy, but I know that there's Boltzmann's distribution and it relates probability to energy and energy states. And so I think the crucial thing I kind of figured out reading this is that at equilibrium, okay? So if you've got a system at equilibrium, and it turns out this is a theme for Steph, but like that's useless, okay? So in the useless case, which is kind of like the default case, like the death of the universe case, it's just a uniform temperature and you just can't get a hold of it, just things bouncing around, sharing that energy, and they're just, okay. So in that case, you can tell how all the energy states are going to distribute themselves. And then you can look at the sum. So each energy state would be this separate thing. You can look at the sum. That's called the canonical partition function. I'm so awesome. And so then if you take that percentage, that's a probability. I am going to do a little trick here. This is called Z a lot of times, but I'm going to just put in this curly E to say, really, you can just not ignore the Z if you just put in this curly E, because it'll be E to the, it's just another E factor, basically. You just convert this number. It's a number, and you just convert it to that kind of number. And so the point of that is that it's like a ground state energy. Okay, so so e to the I minus epsilon is just recalibrating the energy to a ground state. You're just moving it up or down, so that you don't worry about it. So that's the first thing we'll do. Now, let's look at what that means then in terms of flipping it around, because we want to know the energy. So if we flip it around, we go, okay, let's take the log. That gets rid of the E, right? So now the log is equal to this difference of energies over Boltzmann's constant times the temperature. Well, negative, we've already seen how to handle that. It's the log of 1 over p to the I, p sub I, and that'll be that. So, wow, we got our knowledge gained. We see that it's a difference in energy compared to the base energy and divided by temperature. So I'll be writing like energy divided by temperature, etc. And it makes things more messy, but it's basically true. But actually, this is just a multiplicative constant. You can get rid of it if you introduce this number b, and these are just numbers, so you can introduce it like this, and you put e to this Boltzmann constant times the temperature. It's all flipped over. That can be the base for your logarithm. And so if you just say, look, I'm not going to work in natural logarithms, I'm going to work with this log with this base, okay, then the whole thing goes away, okay? So, and it's really not temperature, it's 1 over temperature, and it's, got this constant in it. So 1 over temperature is in a certain sense more natural. Coldness is more natural than warmness, because coldness, when things are cold, that means they're moving around very slowly. They're much more receptive to energy, they're actually more adaptive. Like you give it a little bit of energy, and it will give a lot of flexibility, a lot more increase in ambiguity, which is to say, a lot of increase in possibilities if you just give it a little energy. So like in the human body, everything's slowed down. That's the point. Everything's controlled, right? So that you give it a little bump and things could happen in different directions. That's really the derivative of entropy versus energy. That's the way you really want to talk about it. So you really want to talk about it like 1 over temperature. But you can think of that as the interface, and that's maybe I'll say more about that later, but it's really just the interface, like you're playing with the speed of things. So, if you want things to be, just play with the speed of time, so to speak. That'll change the temperature to hot or cold or whatever. Okay, that's just maybe not so important. But see, basically, if we do that, then we don't just have then the information gain, the knowledge gain, but we have the expected value. So let's take the same probability and let's take the expected value, and that'll be the expected value of energy, okay? So when we say energy, sometimes we mean a single state, but we sometimes like look over all the states. Now, if you look over all the states with the same probability, well, then you're getting entropy. So expected energy is entropy, okay? But that's because we're at equilibrium, okay? So that's a crucial thing about Boltzmann's distribution, is that it's not really, it's like when you have this special case, the default case where like, we're gonna look through the knowledge lens of our probability, like we're in our own messy room and it's just, I don't know what to say, like it's as messy as it's ever gonna be. Like there's no mother to make us clean it up, let's say. There's nobody we're just ourselves, right? Our natural selves kind of drift to this state where like, it's just like that. So, but in disequilibrium, you see, we're gonna make these different. We're gonna say, no, our mother came, or our father came, to be more, maybe to blame our fathers, not our mothers, let's say. And then they said, oh, no, you can't, what are you doing, right? So that's expected energy. I expect you to clean it up. That's right. So this tension. Okay. So now let's get to what we're talking about, because we're so smart and so ready. We want to explain this equation down here, which I introduced us with. It turns out it's super easy to derive, okay? But I think conceptually more easy, because we're going to just start here comparing these two probability distributions, and this line says it all. It's just so trivial. It's so trivial you won't understand it. So I'm going to give a little story to help you understand how trivial this is. The story is that it's a dialogue between two people. I think Steph says that's maybe the easiest way to understand, like me and Steph, right? And so, but for me, it's just more visceral. Two minds, the unconscious and the conscious, okay? And so a lot of times in active inference, we see the X and the Y. The Y is the evidence. And I think of that as the sensory mind, okay? And a lot of times we write it for P, we don't write it for Q, because P is the probability distribution that's tapping into that sensory evidence, okay? But there's also inferred causes, right? Like, so maybe the evidence is that there was a shadow, but the inferred cause is that I'm walking under a tree, right? So the unconscious notices everything, right? But the conscious may not care about the shadow, but cares about the tree because I don't want to walk into the tree, right? I don't mind walking into a shadow, it's a big deal. So then I have this dialogue between these two. So the unconscious mind is like 100 billion neurons giving me all these answers, every single pixel, right? Every neuron's got an answer. They're all pandemonium, as they call it. But I'm trying to compress that. And this is all I know. I know all these things, but I'm trying to say, no, it's smarter to think in terms of what I don't know. Tell me, Andrius, like what you don't know about entropy, right? Get to the point. What you don't know about energy, right? So I boil it down to 100,000 black boxes, cortical columns, questions, words. Every word is something I don't know. Like, so if I say horse, I'm really saying, what is a horse? And then the other mind tells me, oh, here's a picture of a horse. Here's a fact about a horse. Here's a horse etc. So what we have here, and this is like a autoencoder, and this is from the 90s when I was at school at UCSD. You compress all, and this is something a computer could do on its own, even back in the 90s. It could say, look, the computer doesn't have to be trained. It's just going to try to randomly, by trial by error, compress things. It's going to compress them and decompress them. And then it's going to see how it happens. So it's going to compress this information into this language that's more sparse and pure. And this is going to decompress it, decode it, encode and decode. Did it get the same thing back? If it did, that's valid. Was that a better compression than what you had before? Okay, so that's a typical game. And so the idea is that I have a chasm, an abyss between the mind that knows, which is basically representing the whole world, which is basically like, my unconscious just tapped into my body, tapped into the world. On the other side, I have a mind divorced from the world. You see how I'm abstract thinker, whatever. I just have no clue, right? But by being a tricky question thinker, embracing my knowledge, we work it out. We got the same information, two forms. Now, so imagine that dialogue. And now let's say, okay, I've got the sensory information. I can use my conscious mind to slip it in here and break it up into two factors, okay? Q compared to P, and then just 1 over Q. So I can multiply by 1, I can multiply by Q on top and Q on the bottom. I can do that, but it mentally breaks this up into two different things. And that is it, okay? That's all it is. It's just a slick using of the Q to break things up. I can take the log, it makes it additive. So instead of multiplying, I'm summing, which can be nice. I do my thing where I flip everything upside down, right? So Q over P is the same as 1 over P over Q, because I want to understand what I'm reading, right? I want to be able to create it. So if I write it this way, I say, oh, that's knowledge gain, that's knowledge gain, that's knowledge gain. But they're different knowledge gains. This is Q of X, this is P of X comma Y, this is how they compare. And now I say, now I'm going to add my knowledge lens to the whole thing. So now with the energy, and this is obviously disequilibrium, the observed world, the sensory world, is the knowledge gained. But the knowledge lens, how the observer is looking at it, is the Q of X. It's the conscious is observing the unconscious, right? And when you do that, though, when you play this game, and when you break things up like that, you're going to get two parts. And that's the interesting part. Like, you're going to get a useful term and a useless term. You're going to get a disequilibrium term where you can actually do work because there's this tension. I can clean up my room. And there's going to be the lazy day where I don't. Okay, so there's lazy Andrius is, you can't have Andrius clean up his room if you don't allow for lazy Andrius. That's the law of the universe, right? Like, so that's basically what this is saying. And so you can do the same type of thing here. Maybe just to go back. So the free energy is saying, okay, my father wants me to clean my room. How does that look like to me? Okay, that's the free energy. How does it look like to me? I don't see the notion of cleanliness. That's like, where'd that come from? And here's the total picture of it, okay? Where it's not about me, it's about reality. Cleanliness is a real thing, okay? But here it's like how I look at cleanliness, and then here's just me, okay? So now we're going to say, you can take this equation, which is more common, with the free energy principle, you can break it up into divergence and knowledge gained, or also known as surprisal. I'm no longer surprised, I'll just call it knowledge gained. So, but it's just this formula here. P of X comma Y, we're looking at two things, the evidence and the knowledge inferred. State, so it could be a state or an action, whatever. It's, if you're not familiar with this notation, when you have the probability of two things, it's just the probability of the one, let's say the evidence, plus given the evidence, what's the probability of the other, okay, the cause. So it's probability of the shadow, and then given the shadow, what's the probability of the tree, okay? You just break that up. Now, and then if you just do that, you flip everything over, and then you've got the free energy breakup. And there's other breakups, I think it would just work the same. If you noticed, lazy Andrius didn't use Bayes' theorem. Bayes' theorem would say, well, P of X given Y times P of Y equals P of Y over given X times P of X, right? And then you can flip over and you can say, well, then you can say, we want to do priors and we want to do it, but we can't. It's all intractable. And so we're going to flip it all over. So we use Bayes' theorem, et cetera, et cetera. There's a whole story. Lazy Andrius, well, lazy Andrius and the Feynman Andrius said, look, if I can't create, I don't understand it. So I was trying to create all that and I just got this. And lazy Andrius said, why do you need all that, right? That's the problem with me. So let's now apply this to cryptocurrency. We worked a hard time trying to make sense of Qua and Chi and etc. And what's the point? And the cool thing is that it's question of like, does it make sense to have two currencies? And you can see, just like energy has kinetic energy and potential energy, where kinetic energy is kind of useless. It's the energy of moving things around, bumping into each other. Potential energy says there's like a unifying thing that everyone can respond to. It's not local, it's a global thing, like my father. So just like in that way, you can have two currencies. And in particular, the particular problem with Bitcoin because there's only one currency, it's priced in the dollar. So if the goal of this in Steph's heart is to say, hey, can we have a civilization, a world where it has a economic currency that's not depending on fiat currency. It's not this current system. Can we have an independent system that's not dependent on nation states and powers, etc., right? Well, then it's got to be able to price itself. So it does kind of need two currencies, right? It shouldn't be priced in the dollar or whatever. And so there's a need. But on the other hand, like in order to get people to want to support this, they really want to win, by mining and things like that, or investing or whatever. They need a currency that allows them to speculate, but we also need a currency for everyday things. Well, this comes at a cost, okay? So if you're not familiar, but like Bitcoin mining, I think recently it's like $20 billion a year. Okay, so $20 billion a year just up in smoke in electricity costs. It's huge. Now, what are you getting for that? You're getting a $2 trillion economy, okay? So that becomes an interesting ratio. Okay, but per year, so 1% per year you have to devote just to go up in smoke. But then you get this $2 trillion economy, which is not a joke. So that ratio became very interesting. Like, what does that mean? And we compared that to the price in dollars. And this is log because, as you can see, it starts at $1, $10, $100, $1,000, 10,000. And at the very top, it's $100,000, which is like the current price for Bitcoin, changing as I speak. So if you do a log chart, you can see like there's ups and there's downs, but like that up is a huge up and that down is a huge down, right? I mean, it went from 1,000 down to maybe 200, right? It went from 15,000 down to maybe, 6,000 or something, so it's going up like that. What you'll notice, if you look at that ratio, mining cost over market cap, it swings, so it goes down to 2%, it goes up to 7%, and then down to 2% and 6%, and so on. It's swinging up and down. Now, a very curious thing is that when this mining cost is high comparing to market cap, which means lots of people are spending a lot of money mining, right, compared to what it's actually supporting, okay? That's when the price is down. So there's a curious thing, like when the price is, and you kind of make sense, we saw this whole, the economy of Bitcoin being this, that there has to be an even rate of creating these Bitcoins. And it's a contest, it's these lottery tickets like Steph was showing, when there's a lot of people wanting to get the lottery ticket has to be hard to get and becomes increasingly, exponentially harder. And when there's not a lot of people, they got to make it easy so that people would mine it because they need a steady rate of these Bitcoins being created, one every 10 minutes or so, okay? Chi and Kwa is maybe one every 5 seconds. So that type of thing. So what's the connection? Okay, and I really don't know. I don't know. But it's about the cost of doing business, I suspect. So if you want a civilization, then, you look at the Egyptian pyramids, let's say. What is that all about? It may just simply be the cost of doing business. Like if you want to have a well-functioning civilization, you say, look, we're going to build pyramids, right? There's got to be no reason for that. It's just simply that's how we organize ourselves. Okay, and if that's 10%, but that can elevate everyone's standard of living, why not, right? Our society is built on fiat money, the Federal Reserve System. There's these obligations to have exponential growth in currency, in economic value. Like it's, we got to grow by 2 or 3% a year, which is obviously unsustainable, but we're forced to do that. And if you can't do that, then you have to go find a ghetto where you can have victims, and then you can sign them up for telephone plans that they never ordered and things like that. So you have to have what some presidents call some kind of countries, let's say. You just have to have all kinds of horrible things in order to have this moral caste system, and to have that, where everyone can look down on somebody and not be so unhappy about themselves that I'm a telemarketer, but I don't use drugs. I use drugs, but I buy them with money, etc. So horrible thing. That's part of the cost of a civilization, you see. Now, what if we didn't have to have, wars and 5% military expansion? What if we just could make our own money, right? Okay, so we burn it up in smoke. Okay, so maybe that's not the best system, but maybe it's better than what we have, right? I think that's an important thing to say. So this cost of doing business, and then what it becomes is kind of like one of my concluding thoughts, or maybe my few thoughts about cryptocurrency, but is this distinction between belief in the system and belief in the system. So the sensory system believes in the world. There's an answer, I got it. But see, these miners, they believe more. There's no economy there, like, in Chi and Quai or when Bitcoin started out. There's nothing being used, but people believe that they should be mining it because they believe this thing has a future. They believe that there's something there. They're in on it. Okay, they drank the Kool-Aid. Okay, so it's belief in the system. So, like with our active inference community, you can drink the Kool-Aid, and then you're like these miners, and you're saying, "Yeah, I'm gonna," Okay, so that's in an early stage. People drink the Kool-Aid, they set this up, they invest millions of dollars in a new community currency, cryptocurrency. But then what happens? Maybe some miners say, "Hey, I'm not getting anywhere with this," or "I just stopped believing." But they got a bunch of coins left that they have to. So maybe those coins, they try to get something with them. So now they believe in the system. They believe that there's these coins. They just don't believe it's worth mining, right? Or it's not their problem. Now, in a healthy economy, everyone just believes in the money. Let's say, I believe in dollars, but I don't believe that money is the point of life. But like, I believe, okay, I'll function with dollars or euros or whatever currency. I believe in the system. I don't necessarily believe in the belief in the system. And so it's kind of like with acceleration versus velocity. If you throw a ball up in the air, there's a certain point where it just hangs, right? Like it has no velocity, but there's acceleration. Okay, so that's like starting an economy. Like there's no point to it. There's nothing being exchanged, right? But there's acceleration. People are investing in it. And then the question is, it shifts over, like, is there a real economy or not? That becomes the question. So that's very little said about cryptocurrency, but I think but do you think, like, we'll have a discussion, maybe there's more said in there. But I did say a lot about the math of active inference. I gave an alternative approach. Okay, so we both, with the customary approach, we both agree, okay, there's a distinction between evidence and inferred causes, let's say, right? Y and X. But you see, in the traditional, customary, orthodox model, there's a generative model, and it's predictive. And then Q of X is just an approximation, You see, whereas in my case, it's like, look, Q of X is the whole point. The whole point is to have a dialogue, right? The whole point is to have your own mind, right? So these should be different. And if Q of X was a perfect approximation, that's like encoding yourself with yourself, one-to-one with the same alphabet would be absolutely useless. So to call it an approximation is to suggest that a perfect one would be great, but that would be absolutely useless. So, and then to say approximation is it only serves this. And so then also for historical reasons, I think, this is for historical reasons, the generative model was considered the predictive model. So we have to predict where all these shadows are instead of saying, why would I predict where shadows are? No, I'm just going to predict where trees are, right? So why do I have to care about shadows? So this X in my understanding, like X would be really actions. What are the possible actions? So I'm stumbling around the dark, and then here's all the information of what I should be doing, So I'm poking my head around. I've got concepts, I've got conceptualization swimming around, and I'm trying to, so this X really is my sensory information saying, look, your arm moved. You've got neurons telling you your arm moved, or you can't move, or whatever it is. And there's some kind of mystery, magical combination, why these two things divorced with each other. Somehow they look at their relationship, somehow they're able to communicate. Or you can believe in the optimization fairy. Okay, so the free energy principle saying, oh, there's all these approximations out there, but the optimization fairy is going to pick the one that has minimal free energy, by blah, blah, or maximal free energy. I always get confused. It's going to do that, you see. So you can choose two stories, narratives. And so they talk about, like, if you noticed in the math, there's no Markov boundaries, there's no Markov anything, there's no, the beautiful idea of active inference is that you have action perception loops. You can update, when there's something off, you can update your model, you can update the world, but none of that is here. None of it, as far as I can see. So there is a gap, though, between these two. So these are two ways of looking at it. That's my conclusion. I hand it over to you, Steph.
Thank you, Andrius. That was, you covered some serious ground, and thanks for filling in a few of the gaps that I forgot to add in. So there's a question in chat that I wanted to make sure that you got to answer, which was, what does it mean that entropy is a degenerate entropy?
Yeah, so it's just, maybe my mind is degenerate. Maybe that's entropy. Yeah, it's a degenerate energy, right? So if I go back, you can see my slides, right?
Correct.
Let's go back to the very beginning, what I wanted to show. see, this looks just like that, right? I mean, they have the same form if you write it this way. Q of x and P of x comma y, Q of x and Q of x. So all I'm saying is that if you picked P of x comma y to be Q of x, you could pick it to be all kinds of things. But if you picked it to be Q of x, then you would get entropy. And so what that means in practice is that there's a useless way of looking at things in terms of getting things done or working or whatever. It's like if you pick the window you're going to pick on the world is going to be the window of how you look at things in the world, right? The window you're looking upon the world is the window that you're informing yourself, like of your reality, right? Like you're talking to yourself in this way. You're not going to get anywhere special. Basically, you're just kind of like bumping around against yourself. Okay. You're just at equilibrium. It's not going to change you, maybe to say like that. It's just going to keep you who you are. You're not going to clean your room because of that. Okay. So maybe if you're looking for self-motivation, and this is maybe related to Alex Kiefer's thing, is like, well, how would this relate to self-motivation? We can see external motivation operating. Oh, so there's a third level, I would say, would be expected free energy. You see, the Orthodox Church of active inference, if I can consider myself a member, is that in order to compare policies, you have to go back into the sensory world and imagine, okay, if this is going to be a shadow and this is going to be a shadow here, et cetera, et cetera. This is bizarre. No, if I was going to compare policies, I would want to compress yet again. Instead of 100,000 concepts, I'd want to have maybe 10 different parameters that I could compare against to say, maybe this is about speed. Maybe this is about decision-making. Maybe this is about morality. Maybe this is about friendship. I don't know. So that would be how I would be wanting to get it down to, not saying like, well, did I like the smell of this cheese or something? That's a very strange, see, and that's why I call it a religion, because those things are baked in because Carl Friston looks at the world this way, and we're just kind of going along. And I just think that that's science fiction. It's fan fiction. That's my personal belief. I can make up my own fan fiction, and then we can have two fan fictions, and then we can talk about a science that distinguishes between science fictions. So I don't know if I answered that very well.
Thank you. Do we have 4 minutes to wrap up, Daniel?
Yeah. You can make any last comments or stuff. I was just curious, what is the uncertainty that's being reduced? About what to whom? Because the zeros stacking up at the beginning of a hashing algorithm, to me that's like flipping lots of 100 coins, and then if you get 50 heads or 80 heads or whatever the threshold is, you just keep that lot and you discard the hashes that didn't get it. So I don't know if that process ever updates any beliefs that I have, other than just the hypothetically non-forgeable work of flipping those batches of coins. So what do the zeros leading up or other kinds of hash plays lead to actually? How do you see that in terms of belief updating and uncertainty reduction in something?
Yeah, well, good question. And let's see if I can hit it. It's essentially establishing kind of this like arbitrary boundary where we say, let's just play with what a Shannon entropy measurement could be in a single hash output. So all we're caring about, all we're thinking about at this moment is 256 bits, and we have to employ an arbitrary rule. So we could look at leading ones, we could look at leading zeros, we could look at pairs of ones and zeros. But so that's what I'm saying is an arbitrary rule used. But in the kind of state space of that single output, if we were to arbitrarily determine that the leading number of zeros is what we cared about as a way of saying that's a known state or an unknown state, we're saying we're going to accumulate a number of known, or let's say accumulate a number of unknown states, and what is the expectation that we should, at the next interval, overcome that amount of unknown states. So the leading number of zeros is, like, let's say we have 50 leading zeros. That, to get 50 leading zeros, is a really improbable event. And that's improbable relative to the typical output that has some number less leading zeros. And so if we're comparing a very improbable event to what we expect from that typical statistical distribution, then we can arbitrarily just measure the difference of that single rare event and what we typically expect. And once we have that, then we kind of say that's the uncertainty, that difference between the expected average and the improbable event. We're going to say that's valid. We're going to reward for that. And we're going to hold that and add it to the previous amount, the one that was done just previously. And so we're accumulating those bits, that difference at each step. Let's see if that answered, but that was my immediate attempt.
Cool. I will look forward to learning more. Thank you both for the presentations, and great to hear the stories and the perspectives.
Thank you, Andrius.
Thank you,
Huge
Steph.
ground covered. Love it, and let's catch up very soon.
See you.
Peace and love.
Bye.
Um, Welcome back. We're moving straight to the second session of the day, Interactive Math Tools for Active Inference Education by Octopus. Remember, you can drop your questions in the live chat throughout the presentation. So, Octopus, please.
Hello, welcome everyone. Thank you so much for coming. I'm very excited to discuss some things with you today. And the thing that I'm wanting to talk about is the connection between three things that I find very interesting. And two of them, I would say I know relatively well. And those three things are active inference, math, and education. So I've been in math and in education for a while now, under different names and different personas, but always extremely interested in it. And I think there's an obvious connection between active inference and education through some of the major concepts here. So I'd like to talk about that first. What I've seen in the last few decades is a major shift in how education is enacted. And this is going away from a hierarchical top-down model where essentially the teacher enacts command and control on the students towards a more decentralized collaborative model. This decentralized collaborative model was partially forced by COVID, but I think it was also in the making already. And the Active Inference Institute, I believe, I hope it's not a mischaracterization in the eyes of the organizers, is part of this movement, where it's not just one expert who is solely lecturing, like I'm trying to do right now, but rather it is an interactive and decentralized model that leverages all of the nodes that can exist within the network. How does this relate to math? Well, one of the things that traditional education does is assign grades. And already there's math there. We have a problem in grading, which is the fact that grading runs into this issue. First of all, it's rewards-based, and inherently it runs into Goodhart's law. So if an A is the reward for being a good student, but then being a good student becomes about getting the A, there's a distortion effect that's inevitable. But even more, we're taking arbitrary measurements and then further making them arbitrary and distorted by compressing them into these bins. So the difference between an 89.9 or an 89.4 or an 88.7 can feel very, very determinative and even destructive in the learner's future. I don't necessarily have a good answer to that, except to look at what is the purpose of grading. And the purpose of grading, I believe, is to provide feedback to the learner as to where their progress is. So if we think of grading not as a labeling system, but as a feedback system, then it can change our viewpoint of it. And whatever purpose giving letter grades was intended to serve can perhaps be reimagined into other systems that provide feedback on learning. And so instead of thinking about a classroom, either in a high school or a university or however else we want to think about it, I would like for us to think about learning as occurring within a learning system, and to think about the different ways in which learning systems can be designed. So already this is an application of active inference principles, because, I hope this is getting somewhere that's clear to people who are interested in active inference, that active inference is about how agents can learn, or at least that's one interpretation of it. And so if we're thinking about a learning system, and we're thinking about the individual agents who want to learn, regardless of their roles, then we can start to leverage active inference principles towards this process of education. Why am I specifically interested in math education? Besides the fact that it is my chosen interest, I think it's the place where it is easiest to fall into the grading distortion trap. And what I mean by that is that we often can conceptualize math problems as having a right answer or a wrong answer, and then the system might be enacted as our goal is to get people to get to as many right answers as quickly as possible. And my personal perspective is that that's antiquated. It may have worked well at a time when the job of a computer was fulfilled by a human, because you didn't need completely accurate answers very quickly. And while there is still some value in that, there's so many more things that can be done with math. And the type of feedback we want to give, ideally, in my view, should enable the full range of play within that space. So I have no idea if people are even still hearing me, and I'm just going to continue to rant in this vein. Because I don't think that the feedback loop is, I don't think that the opportunity here is one-sided. Obviously, math is an important part of active inference. And for many people who want to learn active inference, they're stymied in some sense by the fact that so much of the presentation is mathematical. And while you can do work around that by speaking to things at the conceptual level or the verbal level or the graphical level, it would also be great if we could solve the problem a bit more upstream by making people comfortable with the mathematics as it's actually written, qua math. The other thing is there's also the fact that active inference as a discipline, I believe, wants to grow. And that part of that is engaging in effective educational activities, of which the Active Inference Institute is one exemplar. So this is the frame for the rest of the things I'm going to be saying. From this high-level conceptual view, we're going to switch to a more technical and tactical view, which is one approach that might be used to present active inference, and specifically the math of active inference, within an educational framework. So the brief lesson or tutorial or play session that I will be leading is about math, and it's about specifically the math of active inference. But let's also look at how active inference not only sits inside the lesson, but how the lesson sits inside active inference, and how these tools might be leveraged so that we can use active inference principles to teach and to learn more effectively. Ordinarily, I would pause for questions, and I'm not sure if that's appropriate here or not.
Octopus, if people in the live chat have questions, they can write it, but this is awesome. It's a great topic. Continue.
Thank you. So I appreciate the feedback. So what I want to switch to now is a specific lesson, and I'm going to put the invite link so that you can participate in the lesson in the role of a student. And I will be participating in the lesson as the role of an instructor, the way that I would give this if I were in an institution tasked with teaching a concept. So let me clear that.
And I'll put that link in the YouTube live chat.
Awesome.
Yep.
So
and also,
I'm going to...
Just wanted to add for context that in the textbook group that you were facilitating the math learning group. So if you buried the lead there.
Oh, well, that's true. I do have some experience. Did several months, I think, of working with communication about the mathematics of active inference. And so this is coming into that informed my perspective here of, actually, let me speak about that experience too. while I work out the technical things here. So there's a mode of the mode of mathematics education that I discussed a moment ago. How can we get people to as many correct answers as quickly as possible? My experience of trying to work within that mode is that it necessarily or almost automatically creates a sense in which people feel threatened emotionally. Most people have a horror story of when they stopped liking math. I have my own horror story of when I stopped liking math. I'm just thankful that I also have a return story of when I started liking it again. And for a lot of people who have this horror story of when they stopped liking math, it was when suddenly they had too much too fast, in the words of the Grateful Dead. So if our goal is to determine who can get as many correct answers as quickly as possible, then if you don't do that, there's a risk that you will be made to feel stupid, especially if you're a young child who's put into this intensive pressure process. And I feel this is incredibly destructive, not only at the human level, personal level, but also at the institutional, societal, and discipline level. And so a lot of the work I'm doing is about bypassing that aversion, recreating or creating experiences that enable math to be viewed as a play-based activity, where if you get it wrong, you'll get it right next time. Or if you get it wrong, you can at least still enjoy the experience. And maybe when you come back to it next time, at the very least, we won't be afraid of it. So I'm going to, if you go to student.amplify.com/join, I believe, and type in this code NEN7C, and I will also copy it and put it in the chat locally. That will enable you to join this activity in the role of a student. And there will be different people who have different levels of knowledge around the topics that we're discussing. And what I'm going to ask is that you enter this activity in a spirit of play. What do I mean by that? Well, I don't mean destructive play. I will be seeing the responses. And so if you type obscenities or things of that nature, I can't stop you from doing that. But it would certainly be a negative experience for me, and I think for the other participants. I would just not show those responses. But in play, what I mean is that we're going to intentionally set aside our seriousness and our internal pressure. I have chosen to do that by bringing along my second octopus head. I enjoy that, so I'm bringing that joy to this experience. But secondly, another way we might play is if you are an expert in this field and you know all the answers and you could get the right answers really quickly, that you seek a different objective. So if you are an expert, if you could write a test on active inference, then maybe you could try imagining that you are a complete beginner. And instead of giving yourself the challenge of correctness, you could give yourself the challenge of empathy, which is a very difficult metacognitive problem, I would say. And also a very scientifically applicable one, because an agent who can engage in metacognition can enter the mind of another agent. And that's its own active inference problem, isn't it? I hope some of what I'm saying here makes sense. I'm going to begin teaching by clicking on the Teach button. And this will enable me to see the responses that people are giving as students. And hopefully this will maintain under civil decorum. We will see. So I'm going to give people some time to join here, and just consciously pause for a few minutes dead air is unacceptable in radio, but in education, we don't call it dead air. We just call it quiet. And so it's okay here if there's some quiet in the moment. I can see that 4 people have joined. I can see your names, and I should have warned you about that, but I don't think anyone has de-anonymized themselves. But I could anonymize people. And these become the names of famous mathematicians or scientists. And I personally like anonymized mode better. No, I also buried the lead on this. The tool that I'm using is called Amplify. When I was first introduced to it, it was called Desmos Teacher. I haven't used it in several years. And so since I ceased being a classroom teacher, but I've been playing with it a little bit in anticipation of this presentation. And I will be showing some responses anonymized. I'm going to shuffle. And if you're concerned about the fact that real names are visible for a moment, you can leave and come back just by reusing the same link. So I deeply appreciate the people who have joined so far, and encourage anyone who is interested to join. There's still plenty of room. And the first question I'm asking is, what describes your interest? And there's an x-axis here of interest in active inference. And there's a y-axis that says I'm interested in education. And if I switch to student view here, hopefully I can have some empathy for people who didn't join this, who didn't design this. There's a star, and I can drag the star to where it represents my place on this XY axis. So if you're a complete teacher, or if your focus is only on teaching, maybe maybe some teachers knew about this and are coming, but they don't know much about active inference, then you would be up in the close to the y-axis. If you are completely interested in active inference and have disdain for students or anyone who is learning the subject, you might be closer to here. If you're the session organizer, you might be really high on the y equals x line. But this enables us to get a sense of the current audience that's interacting with the presentation. And I like this as an introduction. I feel part of the feedback loop, part of the information that the agent is seeking to accurately update their beliefs is whether or not I, as the teacher agent, am willing to seek information about their beliefs currently, or about their worldview or their position. And so again, that's metacognition. I don't agree with the quote that, I don't agree that emotional effect is the only effective of component teaching, component of effective teaching. But this isn't manipulative. It's a place of genuine curiosity. So I am curious about the audience that has come so far. And let's see what the audience looks like. Should be the case, if I did this correctly, that I see multiple stars showing up. And it looks like I do. You can see here, hopefully, the smaller dark stars are different individuals. And so it looks to me like most of the people positioned themselves as being mostly interested about active inference, primarily. But there are people who are knowledgeable about active inference and are interested in teaching. And so I can see the two clusters. Now, if this were a quote unquote real class, there would be a decision point for me. Do I want the class to know that there are two clusters? Since this is a simulated class, I think it's appropriate to reveal this. But if I were in a situation where I thought people might be having some of their personal risk, they might not want people to know that there's someone here who's not as interested in education. And that's a design choice that I, as the teacher agent, would have to make. The next screen, if y'all would be willing to leave that screen and come with me to the next screen. And the student view of this simply says, make a prediction. Predict a value 0 through 10. And then there are only 6 options, 0 through 5. So what I might be, maybe this mistake was made on purpose. Maybe this mistake is the result of not checking carefully. Sometimes it's good to make mistakes on purpose. V.I. Arnold, the great Russian mathematician, I mean, the great Russian mathematician, let's not undersell the great there. He was well known for intentionally injecting mistakes into his lectures to make sure that students were paying attention. And I am told that he would even allow these mistakes to compound, that if no one caught an intentional mistake and called it out, that he would continue with the wrong assumption until someone caught it. I'm not willing to go that far. It does feel to me that there is a place where, as the teacher agent, I would need to step in and point out there is a mistake. But I would certainly view the fact that no one had caught it, or that no one had felt comfortable enough to challenge the teacher agent's quote unquote authority. That would be very helpful to me in updating my beliefs that were in terms of taking future actions. So I'm not presenting hard quantitative things about this, but I'm trying to bring active inference language to a process that I use in teaching mathematics, hopefully effectively. Daniel, is this making sense?
Yeah.
Okay. Feedback helpful. So I'm curious, though, how the students respond to the fact that the task they're asked to engage in doesn't actually match their set of expected experiences. Is this distressing to them? Do they not even notice it? Do they think it's funny? All types of responses. And if I could edit this in live time, I might even add a poll of how much did it bother you?
What I'll add here, Octopus, is that you're definitely right and have experienced that with the math psychology around active inference, and it can feel like there's some inner math sanctum or some equations on pedestals, and it's something other than learning or applying active inference until that equation is like deciphered. And when you said that active inference is in the lesson and vice versa, it's like, this is already the process. And even just clicking next on a page, just regular actions that we might take at a second time scale, or just through an interface with computers or in conversation, those are kind of the conceptual moments that are the kind of like the moon, not the finger. And then that helps the equations, which the symbols could be different letters, or they could be different sounds or shapes. But those are describing something which is like the cognitive situation with prediction, observation, updating, action selection. And so helping, whatever the content were, helping pull that thread of active inference. And then it's a double treat that the lesson is also about KL divergence or whatever it happens to be, which helps us understand the cognitive scenario at an analytical level. But from an experiential level, just learning something, the more novel and surprising, the better.
That's certainly how I feel. I have almost an insatiable need for novelty. I feel it's the more novel and surprising, the better, as long as it's comfortable enough. So I wouldn't probably wear my second octopus head to a high school classroom, or maybe I would, I don't know. But and maybe this is an active inference concept that's well known, but there's a level of novelty and surprise that can be overwhelming, at least to student agents in my experience. How does that show up? And I want to get back to what I had planned, but now you've said something that I'm wanting to know more about. Does that show up in the sense that if the information is so surprising that the agent doesn't have a way to integrate it, it puts their survival at risk? Is there any way to describe that within the active inference framework, that like, this is distressing to me, how unexpected this event is?
Yeah, I mean, a lot of ways to go with that. I think of one situation where we have a flat prior preference. So we're open to all outcomes and don't have a prior preference on which would be better, like all options from the menu. It's kind of like the flat prior distribution from the previous session. And then in that situation, novelty and learning can be a dominant imperative. But then if we think about a distribution like homeostasis of temperature or blood sugar, where it's modeled as there being a strong preference, when you're outside on one of the far tails of temperature or of blood sugar, then it threatens the autopoiesis and the life of the agent itself. So that kind of goes outside of a information band into a sort of survival mortal computing.
So is it correct to say that how it feels to the agent is about what their expectations were or what their prior beliefs were? I mean, let's be honest, many students in a learning system, let's say a state-controlled learning system, are of the strong preference not to be there. And I always wonder how much that plays into it. Like John Taylor Gatto, who I've been reading a lot lately, goes into, I don't want to turn this into a thing about my anarchism either, but he is talking about how, like, the public educational system in America, at least as he experienced in New York City in the 1990s, was just so socially constrained. And so top-down command and control is to be highly non-functional. And that his effectiveness was to the extent that he could remain within the system while completely subverting it. Anytime I see an agent who's active who is exercising their agency to be effective within a system, and yet is highly critical of the system. He was New York State Teacher of the Year, and then at his lecture just gave a critique of the entire system within which he worked. the fact that an agent can be critical of the system within which they exist is something that's interesting to me. And I'm guessing that these are not like novel ideas, but the fact that you, specifically Daniel, personally, are capable of just turning whatever I say into active inference, like Rumpelstiltskin spinning straw into gold, is something I always find value in and am tempted to just exploit as much as possible for my own learning journey. Do you have anything you want to say to that? I don't want to put you on the spot, but I will return in a moment.
Keep going through the slides so that we can see the whole lesson within the session.
All right, that sounds good. Thank you for keeping me on track. So then the next thing here is a formula review. And there's actually nothing here. And this wasn't a matter of time. So what you could do is you could simply put cards here that had a concept on one card, like let's say entropy, and then a formula on the other. And they would be free floating. And then you would simply ask the students to match them. There are these things called tactivities from the University of Colorado for teaching calculus. This is a digital version of a tactivity. In the physical setting, you would simply have the cards be cut out and you would ask students to match them by letter number pairs. Here you could have two columns, or you could have free floating cards that you then asked to match. This is a very different type of question from the previous question. To be honest, I think it would be very inappropriate and jarring, because the nature of this question is, the nature of the prior question is so open-ended as to be almost meaningless. Like, I ask you to predict, it's Alice in Wonderland, like predict a value 0 through 10, but you can only do 0 through 5. Why are we predicting? How can you predict if there's no objective, like you're just randomly choosing? All of these things are fine. That's a wonderful type of absurdist play, perhaps jarring in a goal-directed setting. And then here is a highly knowledge-dependent, goal-directed problem where you need to at least be able to do flashcards quickly so that we can proceed. And they're two very different types of questions, and each is at the extreme. And so moving from one to the other is something that could be very distressing to an agent. And that's why it's intended in a spirit of play. But if you're actually intensely invested in following or being a good agent, it could be difficult. Let's move on. So let's move on to the part that's more content directed and a little bit less metacognitive. So this is more open-ended, but it's closer to a goal direction. Prior versus likelihood. Here I'm asking the students just to, if you look at the student view here, you should be able to drag the points. And as you drag these points, it moves the distributions. So you can move the prior distribution, which is in blue. And you can move the prior distribution, which is in green. And you can move the likelihood distribution, which is in blue. And there is no objective here. It's just getting you used to the idea that these curves are controllable. And these points are actually at the mean. That's not important at this point for the students to know. It's not important for the students to know that these are normal distributions. It's just a matter of seeing what can happen if you click. And I can see that most of the students are there. And I'd like to ask the students to move them to wherever they would like to have them. And then we can proceed from there. I'm going to show you what I see as the teacher view. Should be the case that I can see individual responses here. An overlay wouldn't really make sense, but and it may be a lag or internet issue, but what I would be able to see is individual students' responses. Here we go. I can see that the different students or learner agents have put the curves in different places. I can also see, for instance, who has touched it by comparing it, and I can see who is actively dragging it as I talk about it, which is a nice feedback for me of who is engaging. If we're ready to move on, let's go to slide 5, learner agents, and I appreciate y'all. This is what a student would see. I have now introduced a red KL rectangle, which will show up in a moment. And there's no explanation of what KL is, other than it's a red rectangle on the screen. But as you drag distributions, the KL, and there's a text prompt here, what makes KL bigger, what makes KL smaller. And as the student drags the distributions around, they're going to see KL move. And this is a tactile discovery, kinesthetic discovery of a relationship that is not yet well understood. And I guess the question is, does it have to be well understood at this point? Or can it be enough that you know that as you drag these points, the rectangle changes? In other words, what I'm trying to do here is to make these felt sense of feedback central before we introduce anything conceptual or high level or give any exact definitions. This can just be that I'm clicking and dragging and seeing what happens. And for some people, that's comfortable. For some people, it's not, and that's okay. But this is what this slide is about. And then I also ask for response. There's a prompt here. What do you notice? So you can drag to make it bigger or drag to make it smaller. And there are really only 2 directions. So if you get it wrong, you'll get it right next time. And what I think the students will notice is that as you drag them closer, KL gets smaller. I'm going to check the anonymized responses and see if there's evidence that we're ready to move on. So I don't want to rush anyone, but I also have to fit within the time box that we have. Okay, we're fine on time. So if learner agents, simulated learner agents, if y'all are willing, when you have a moment, if you would type what you notice. We already have 1 response. I also love this beautiful overlay graph of being able to see all of the student engagements at the same time. That's another concept that I think of it from the perspective of cryptography, like our securities, computation, like multi-party computation. So if we have in a multi-agent system, and all of these agents are exploring in their own way. And then there's let's say, a higher level agent or a meta agent who can observe all of the individual explorations. This is a nice position to be in for me as a teacher learner agent who is not only trying to convey certain material, or in this case, just guide the exploration of certain material, but also it's a nice place for me to be as someone who is going to be engaging in repeated interactions with these other agents, knowing about their temperament, like are they wanting to go far away or stay close? Things like that can be very helpful information if it's not over-indexed on. I'm a little bit self-conscious about the fact that there's a risk of panopticon, that making this process clear to the students will heighten their anxiety about the fact that they're being watched. I personally have some trauma around surveillance capitalism from the rushed move to virtual education during COVID. And I can't imagine how I would have dealt with it if I were a high school student or middle school student. The fact that someone above you can be watching and collecting data produces different responses for people. And so when I engage in this process with students, I want it to be clear what is happening. And I can also get a sense of the power that a company that is able to collect customer or consumer data or user data might feel, because I can learn a lot. A lot of times in this process, students have suggested ideas to me that I would not have originated on my own, and it actually deepened my understanding of the subject. Something that we could do here that might be fun as an offshoot is think about, is there a way we could enable collaborative play where the agents are directed for something kind of like the Reddit experiments where they're adjusting one pixel at a time? Maybe I could ask them to try to produce a particular histogram of KL, for instance. I love playing with these ideas, trying different things. And I'm exploring the exploration of other agents, which is something I really enjoy doing also. Can we move to slide 6, please? So the challenge here is by hand, try drawing two distributions that will have large KL. And so I'm checking, I'm not sure, what students may or may not know here. And the best way to figure out what they know is to ask them. So my hypothesis would be that most students will draw things that look similar to the example they saw. And that the prior question was about small KL, but that they will have the concept that large KL could be achieved by separating the curves more, because their goal was smallest, but it also asked about largest. And so I'm sure they'll see, there's only two directions to go. But I'm curious, first of all, that they'll get this concept, but second of all, what the curves will look like. Some people will be demand avoidant. That's something that I often am. Or they may feel very playful. They may want to adjust and see how far outside the space of two normal distributions with the same standard deviation they can achieve. This one is also fun as overlay, and because when we switch here, the students were originally doing two different, but we could position ourselves to think about an open discussion where we compared distributions that originated from different learner agent responses. So even though this curve and this curve, the curve in yellow and the curve that I am now going to redraw in green, even though these two curves may have originated with different learner agents, we can now pull them up into one set from which we can select any two to discuss. And we can guide or open the door to free initiation of hypotheses with things like, if this curve looks more like maybe a exponential distribution or something. Well, what we were looking at before were symmetric normal distributions. Do you believe that KL could even be calculated for two distributions that are this different, and why? So these are some options that these are some choices I would need to be making as the teacher learner agent, or as the central learner agent, or the guide agent, or however we conceptualize it. Also appreciate the Dadaist contribution. This is not two distributions. If we could move on to the next slide in the interest of time. And then I'm going to give the students directed reading, the Wikipedia page, which may or may not be any good, but it gives us a place to start. And probably I would have my own interpretation of the Kullback-Leibler divergence revealed at this point. I would be happy to draw, autonomously around the discussion. But at some point, we're going to have to bite the bullet and look at the formula and think about the formula. And now here's a good jumping on point. And this is sort of the reverse approach to the way that I typically saw concepts presented, especially pre-university, which is you would often just start with a formula on the board and then you would begin to unpack it. And that can be very informative. I'm sympathetic to that approach now that I have a better understanding of how to intuit many of the symbols through lived experience of fighting and playing with symbols to do mathematical work. But it's a choice that one needs to make. When will the formula and how will the formula be given? And how much information will be given at once? As another, I've chunked things quite small, I would say. For some people, this is really going to test their patience. For others, it's exactly the right pace. So the next slide is a very low-level challenge. Given the fact that the formula for the Kullback-Leibler divergence is in the Wikipedia article, are you comfortable using the math keyboard to type it? And you do have a math keyboard available here that's got many standard symbols, in addition to things like superscripts and ratios. It has, sine, cosine. So you're going to need natural log or log, and we can discuss the difference between those if we need to. But you have the building blocks here. My memory is it also accepts input in MathJax or TextStyle. But regardless, I'm giving the students a chance to use the formula and rehearse the formula in a very low pressure way that there can't really be a direct right or wrong answer for. And assessing and giving practice in their comfort with communicating math using symbols. So this takes how long it takes. I would probably in a 1-hour class be hoping to get a bit more than this. This might be the first somewhere between 10 and 25 minutes, depending on the audience. But the goal here is not just to give an example half lesson on Kullback-Leibler divergence, but to be engaged in thinking and conversation about active inference inside math education, inside active inference. And at that point, we have either a subset inclusion where the two concepts are equal, or we have a fractal, whereas we zoom in on one, we keep seeing the other. And either of those conceptualizations makes me very happy. So that's what I have prepared for today. And I'm happy to use the rest of the time as the facilitator directs. Thank you so much.
Thank you, Octopus. If anyone has a question in the live chat, we can see. Otherwise, what was most surprising or the best learning experience or a fun or symbolic anecdote from your time with the math learning group in the textbook?
I think it was the difficulty I had finding a way that I could write formulas quickly. So I actually went out and bought a tablet there are two things. The first is how difficult it was to write formulas on a computer screen for me personally. And I felt that that was helpful because it put me in a context where I had a disadvantage. And that felt to me that it made play slightly more fair, although I think it also was frustrating. The second thing is because of the way the sessions were structured, I was mainly coming from a place where I was responding to student questions. And that was fine. That was totally fine, and I enjoyed it. But it reminded me of the fact of being like in a tutoring lab where you're always in response mode. And I got to experience that again after not having worked in that way for a while. And to reflect on the difference between being in response mode where someone else is setting the agenda and you have to fill in, versus something like this where as I can have any essentially level of direction I want when I'm teaching a class. And so comparing those different experiences, being outside of my comfort level, both of those were things I found interesting and valuable to reflect on.
Great. And then a last question from live chat, and that'll be it. From Sleepy Sylvia. How would you encourage students to interact in a classroom? It doesn't seem easy to switch from a mindset of passive learning to play.
So I personally encourage them by being playful about the experience from the outset. I guess I don't believe people, so I have never been able to be effective when I was completely serious about what I was doing. And I'm not sure that people in general often can be. There are some things that require extreme precision. And for those moments, like let's say calculating a medicine dosage, one certainly needs focus, but focus is limited. And so I think that encouraging play comes down to recognizing that play is likely ultimately more effective in most cases, especially if we're in an environment that we can lead ourselves to believe is low stakes. Perhaps we will get a bad grade, but getting a bad grade is not a threat to us as a person. I hope that makes sense.
Yeah, I think that really closes the loop also with the homeostasis, which is like if all outcomes of the learning encounter were non-threatening and equally preferable, it would be like foraging in an open field. But if some of those doors, there's a threat that comes up against our feeling of survival, then it can be as threatening as anything. So, thank you, Octopus. Great to have you around, and till next time.
Till next time, friend.
All right, bye.
For the third session of the third day of the symposium, we have active inference in biology. Modeling the environment as an agent. First, Chris Fields will present the topic, and then Virginia Bleu Knight will facilitate the Q&A. Thank you for presenting. The stage is yours, please.
Okay, thank you very much. I want to talk today about applications of active inference in biology, and particularly the issue of modeling the environment as an active inference agent, which the FEP, in fact, requires us to do. But the approach I want to take is via the symmetries of the FEP. And I want to focus in particular on two symmetries of the FEP and hence the active inference formalism. One is that all components of any decomposition of any system are active inference agents and need to be treated as such. And the other symmetry is that all boundaries between systems, so all Markov blankets, for example, in the classical picture, are information symmetric. Both of these symmetries are universal. They come just from the physics, but they're both especially relevant to thinking of active inference in a biological or social setting. So in thinking about any interactions between living systems and their environments, these two symmetries have to be taken fairly seriously from a modeling methodology point of view. So where we're going today is first to discuss a little bit of physics. And I'll be using physics from the top down. So starting with the description of an entire isolated system, some kind of universe, and adopting very simple assumptions and seeing where that physics takes us. This is kind of an unfamiliar way to start thinking about the physics of a system if you're typically used to starting with particles behaving in space-time, or even a dynamical system that's defined in some spatial coordinates. We won't, in particular, be talking about spatial coordinates at all. We'll be talking about systems completely independently of any spatial embedding. So once we're done with the physics, I want to consider two examples. One is niche construction, and show how niche construction is an instance of active inference. And then the other example will be cognitive offloading, taking part of your problem and giving it to your environment to solve for you. And I'll also show that that generically is an outcome of active inference. And then finally, I'll talk about some methodological implications of this way of thinking, and in particular, methodological implications of these two symmetries of the FEP. So, top-down physics. We're just going to assume three things. We're going to assume that any system that we're interested in can be described with a finite Hilbert space. So a Hilbert space is just a space whose basis vectors are the possible values of the possible degrees of freedom of the system. So if you think of asking a system a bunch of yes-no questions, every yes-no question corresponds to one of the basis vectors of this state space, if you use a Hilbert space as the state space. And therefore, we can think of any of these spaces as just spaces of qubits, quantum bits, because those are the most fundamental entity to which you can ask a yes-no question and get an answer, either yes or no. So we'll assume that all systems can be described in this way, and we'll assume that they're all finite dimensional. And that's just for convenience. They can be arbitrarily large. But if we assume they're finite dimensional, we don't have to worry about singularities, which just cause problems. The second assumption we'll make is that there's some sort of background time parameter. There's some intuitive concept of time that we can use to talk about change. And we will not assume that this is measurable by any experiment. So it's just a parameter that we'll use in the theory, and measurable times have to be constructed, but they're constructed from this background time parameter. And the way to think about that is a measurable time requires a clock, and for a clock to be meaningful, it has to change. And to talk about change, we have to assume some sort of background time. So all clocks run slower than the fundamental frequency of the background time parameter that we're assuming. Then the third assumption we're going to make is that isolated systems conserve information. And this is the principle of unitarity, which is the fundamental principle of quantum theory. It says that if you have an isolated system and its state is evolving in this background time, then the state will encode exactly the same amount of information at every time. That assumption might be considered controversial. If you throw out that assumption, then you throw out quantum theory. So you've thrown out a lot of empirical physics and have a lot of explaining to do. It requires a whole new theory of how everything works if you abandon unitarity. So we're making these assumptions with a goal, which is universality. If we make these assumptions, we describe all systems and all interactions up to the three assumptions that we've made. They apply to everything. And of course, we pay a price for this, which is abstraction. The results that we get will give us constraints on models, but they don't tell us how to build models. So the outcome is a set of methodological constraints that have to be complied with. It's not a model building procedure. And before going on, I'll put in a plug for this recent book that Jim Glazebrook and I wrote that explores the implications of making these assumptions. And we're doing a live stream on that at the end of January for the Active Inference Institute. So if you're interested in this kind of approach to physics, that may be of interest to you. Again, it's not for a couple of months. So let's start with the first implication of unitarity, which I label here decompositional equivalence. The implication is that you can take a system, any isolated system, so I'll call that U for universe, and that system has some internal dynamics, which we can represent with a Hamiltonian operator. You don't have to worry about how to write that down or anything else. It's an operator that classically corresponds to the total energy of the system, but it is an operator that preserves information, the information in the state of this isolated system U. And U being isolated just means that information doesn't flow in and it doesn't flow out. So decompositional equivalence is the fact that I can now slice that system any way I want to into two components, which I'll call S and E for system and environment. And I can represent each of those components as having an internal dynamics. And I can represent their interaction by, again, a Hamiltonian operator that describes information flow between the two systems at some boundary, the boundary where I've sliced the system. And that operator, HU, decomposes additively. which means that I can slice this system any way I want to, and I don't affect its overall dynamics at all. So what that means methodologically is that physics by itself does not give us boundaries. There are no joints in you for it to be carved at. The boundaries that we see are all boundaries that we have defined by stipulation. So the picture of an evolving universe where the physics itself gives you the boundaries around things is actually inconsistent with the three assumptions that we've made. The physics doesn't produce any boundaries if you make those three assumptions. However, the physics defines the interaction, which I've labeled here HSE, at any boundary that we stipulate by making a model. So it's our choice as theorists. We can slice the system any way we want, and the physics gives us the interaction. And it gives it to us by this simple formula I've written here. So this symmetry, in fact, is key to the free energy principle. And now we can state the free energy principle. It says that if we slice this system U, if we slice any isolated system anywhere to define two components S and E, then if S and E are to remain in a separable joint state, so if they're going to remain mutually statistically independent, then they have to both behave in a way that's consistent with that mutual statistical independence, which in quantum theory we call separability. Separability just means lack of entanglement. So if S and E are going to be separate systems, things that we can talk about independently, they're not entangled. So they have to behave in a way that is consistent with them not being entangled. And maintaining separability, not becoming entangled, requires keeping the interaction weak with respect to the internal interactions. So we can express that by thinking of the dimensions of the interaction, which are the same as the dimensions of the Hilbert spaces. The dimension of the interaction is the same as the dimension of this boundary that I've used to slice the system. And that boundary just has to be much smaller than either of the systems that it separates. And that is intuitively obvious. The boundary has to be small enough that the systems robustly have internal states, or the FEP doesn't tell you anything. The FEP requires that systems have internal states. But this gives us an important qualitative fact, which is that sensations and actions, which are defined at the boundary, are low-dimensional projections of the general models of the systems, because the general models are implemented by these internal interactions. So when we think about what a system is observing or what a system is doing, in both cases, those are very low-dimensional representations of its generative model. Low-dimensional inputs, low-dimensional outputs. So with this, we can now think about the symmetries of the FEP. So the first symmetry is that if E is the environment of S, then S is the environment of E. So if S's generative model, its internal dynamics, is predicting E's action on the boundary, then E's generative model, which is its internal dynamics, is predicting S's actions on the boundary. And E's actions on the boundary are S's perceptions or sensations. S's actions on the boundary are E's perceptions or sensations. So the boundary is the locus of all of the sensations or actions of S and E. The boundary is the Markov blanket between them, which encodes sensation and action in the standard formulation of the FEP. So both of these systems are constantly acting to minimize variational free energy defined at the same boundary. So this minimization of VFE is always a co-minimization being undertaken by both the system and its environment. And the reason is that both the system and its environment are trying to stay separate from each other. They're trying to keep the environment well-defined. They're trying to keep the boundary well-defined. And the only way to do that is to keep this interaction weak. It's to keep the interaction from kind of blowing up in their faces and tearing the boundary apart. So that's the first symmetry of the FEP. If the system's an agent, the environment's an agent too. The second symmetry is that this interaction being well-defined at the boundary requires that the information exchange be symmetric. So again, this interaction is an operator that acts at the boundary to move information between S and E. And it's the same operator from whichever direction you look at it. And the operator being well-defined is the same condition as the boundary being well-defined. And in fact, we can see that intuitively by thinking of the boundary as a qubit space. Again, as a finite dimensional Hilbert space. And if we think of the boundary as a qubit space, it's just some set of qubits. And the system and the environment are acting on that qubit space using perfectly symmetrical sets of operators. Sort of the S half of HSE and the E half of HSE. And each is doing preparation and measurement of each of those qubits. So the boundary being well-defined, the interaction being well-defined requires this symmetry. And you can think of that just as Newton's third law of equal and opposite response to any imposed force. So this, again, is true of everything. So now let's think about what this means in a couple of examples. First, it means we can always think of active inference as niche construction. S is always acting on E to persuade E to minimize S's variational free energy. Why? Because S's variational free energy is also E's variational free energy. They have the same boundary and they're acting on it with a symmetrical operator. So E acting on S is always trying to persuade S to minimize E's VFE. So the two are always co-minimizing their VFE. So niche construction is niche co-construction. S, in fact, is E's niche. And E's constantly trying to get that niche, i.e. S, to behave itself, to behave in a way that's as favorable to E as possible. So good niches in Mike Levin's language are persuadable niches. They're niches that we can, by acting on them, get them to behave in a way that's beneficial. And that includes, of course, the other organisms in the niche, whether they're conspecifics or not. So a niche of a social organism like a human is fairly persuadable. Niches of kind of loners like tigers, for example, are less persuadable. So the tiger is still acting on its niche, but it's not very persuadable. So it doesn't get as far as we typically do in getting our niche to behave. But the bottom line is that because active inference and niche construction are deeply the same thing, ecology is intrinsically a social science. It's intrinsically about persuasion. So we're starting to cross the boundaries between disciplines now. So let's think about the other example, which is cognitive offloading. getting the environment to help solve some problem for you. So if I'm an agent and I'm acting on my environment by making a measurement and recording some result, and by recording the result, I'm making an action. If I wait any finite amount of time, then my environment's going to have some time to do something with the information that I wrote on the boundary by taking my action on the environment, by making the measurement. So the environment does something, and if I go back and make another measurement, I'm going to see the results of what the environment has done in response to my first measurement. And generically, I'm going to get a different answer from my measurement because the environment's in a different state. So the environment is constantly processing the information that is written on it by observers. So it's not just sitting there. It's never passive. And one particular case of this is memory. If I write some memory on the environment, then in general, the environment's going to process that memory. And when I go to retrieve it, it's going to look just slightly different. And we know that that's in fact the case for episodic memories by humans, and the environment is always acting on our brains. And so it changes our brain states. And when you go to retrieve a memory, it's likely to be subtly different. The same is clearly true with technology. We spend a lot of time and effort trying to get our technologies to modify the memories, rewrite on them as little as possible. So what does this mean? What do these symmetries actually imply? Well, first, it means that systems environments are always co-evolving in time. Separability, lack of entanglement, means that the interaction between a system and its environment can be considered classical communication. They can be considered to be exchanging classical bit strings. But because they're not entangled, because they're separable, they have free choice by the Conway-Kochen theorem or just as a consequence of separability. So the languages that system and environment are using to write on the boundary can be different and likely will be different. So even though the environment's giving me back a bit string, it may be a bit string that's been encoded with a reference frame that I don't know and I can't find out. I just have to make assumptions about it, build a model of it to try to understand what the environment's telling me. So the other implication is that system and environment are constantly processing each other's informational inputs and then giving back answers. So they're constantly trying to solve each other's problems. Whether the answer is actually interpretable or not is always an open question. So in terms of theoretical methodology and also experimental methodology, if we make these physics-based assumptions, then the passive environment assumption is always wrong. And it may work for all practical purposes sometimes, but it's very difficult to say which ones those are. And in fact, the frame problem in artificial intelligence is a statement of the fact that we don't know when the passive environment assumption is actually going to work. We don't know whether the environment is going to generate side effects that we're not able to predict or haven't been able to predict. A second methodological assumption is that we have to assume history dependence. And in classical physics, we often assume that things are not history dependent. That means they don't have internal states. They're not doing information processing. And if systems really aren't doing any information processing, if they really don't have internal states, if they're really no larger than their boundaries, then they're not separable. Then they're in fact entangled with their environments. So if we think something's separable and it looks like it isn't history dependent, we just need to look harder, because at some level of description, we're going to find history dependence. And then the final implication is that if a system is separable, if we can talk about it as an independent thing, it's always going to be getting some extra cognitive resources from its environment. It's always going to be able to do some offloading of problem-solving tasks. But it may not know how to use the answers. And we may not be able to detect, without doing the right kind of experiment, what its environment is actually trying to tell it. So I just want to emphasize in the last slide that we really have only assumed three things here. We just assumed some very basic physics. The Hilbert space description, background time, and unitarity. And so we get a lot of biology and even cognitive science for free out of these very simple physical assumptions. And in fact, we get all the way to cognitive offloading for free just from the physics. And so when we're thinking about physical systems, which we always are when we're doing active inference sort of models, we start with the physics and we get cognition, basically, not just in the system, but in the environment. So thank you very much. And I'm going to turn it over to Bleu to handle questions. And I think I'll get out of the slides and stop screen sharing.
Thank you, Chris. Yes, Bleu, you're welcome to share slides if you want. Yeah, go for it.
Okay, I'll try. First, Chris, I just want to say thank you for inviting me to be here. It is such an honor and a privilege to be thinking these thoughts and co-creating this reality with you right now.
Thank you.
I am, let's see, let's get way back up into here. So Chris and I have been hanging out in the Hollywood squares for a really long time. I think I'll just share this way. That way it lets me kind of do it. So I just want to provide some links so that everybody who wants to have the opportunity can come to our shared level of mutual information. So we've done a number of live streams together, live stream 17, live stream 40. There's this guest stream, which I was not part of, but also highly, I think, relevant to what was discussed here. And of course, the wonderful course that Chris did for the Institute, Physics as Information Processing. And so this coda, this is like 12 lectures and a lot of discussions and stuff that happened in the course. So to study more of Chris's work, I just wanted to provide that background. And so here we are, somewhere in between quantum and the FEP now. I love this slide. I pulled it out of an old slide deck. And in preparation for this talk, this question and answer period, Chris. Yeah, hold on. Let's see. Yeah. Oh yeah, I can still see. Perfect. The pop-out panel is great. Okay, so in preparation for this, Chris, I said, so is there anything I can kind of study or read up on? And Chris sent this recent paper that he wrote with Mike Lennon, and that I think some of the figures that were used in Chris's talk came from. So I just pulled a little bit of notes out of each of the sections in this, but I don't know how far we'll get. I could go so far in asking questions. I have a million questions already. So let's see kind of what pops up. So just from the introduction, I just pulled a little bit out. It says in this first quote, there is instead substantial theoretical utility in viewing objects and processes as complementary ways of describing persistence through time, and hence the possibility of observation and manipulation. This way of thinking highlights the roles of memory as an essential resource for observation and of time as an essential resource for action, and makes it clear that memory and time are also mutually interdefined, complementary concepts that both rest on the underlying notion of an identity that persists. And Chris talked a lot in this talk he gave at Topos about the relationship between identity, time, and memory. If anybody wants to kind of go deeper into that, that link is there too. But really what I want to ask here is about the observer. And so in this paper, you said that mereology, like the distinction between the part and the whole, essentially effectively the boundary is defined by the observer, right? There's no, and this you talked about too, like there's no inherent joint in a system to be carved out. So this boundary is imposed by the observer. And you talked in the paper a lot about what is required for an observer to model itself as a persistent system and model its observations as a historical sequence. So really, I think, we talked about the system and the agent and the organism and the environment co-evolving, but is the observer also co-evolving, and is the observer also a process in this? Or could you maybe like unpack that and help me wrap my head around that a little bit?
Yeah, whenever we're doing some sort of experiment or we're treating ourselves as observers, then we're always interested in observing some interaction in our environments. So if I'm the observer here, say I'm the experimentalist, I'm studying the interaction between, say, a plate of bacteria and the rest of the environment. So I've singled out some system in my environment, and I've given it a name, and I've drawn a boundary around it. And so we're now in a situation where I've divided my environment into two pieces, and I'm interacting with both of them all the time because I'm interacting with my environment. And I'm trying to understand by making measurements what the interaction between those two pieces of my environment is. So the only access I have to the interaction between those two pieces of my environment is how I interact with my environment. So I can interact with the two pieces, but I can't guarantee that I'm interacting with them separately. It's a standard assumption of classical physics, which even carries on over into quantum theory, that in practice, that I, as an observer, can interact only with some particular piece of my environment. So it's an assumption, for example, that I can interact only with this laptop, and to the exclusion of all of the rest of the universe. But if you think about what that exclusion actually requires, it requires infinite energy for me to say that I'm going to interact only with this laptop. I have to keep the whole rest of the environment at bay and make sure that I don't interact with it in any way, and make sure that it doesn't interact with either me or the laptop in any way. And that's what's hard, right? We're sitting in an environment, for example, that's constantly flooded by high energy cosmic rays. They're going through my body and going through my computer all of the time. So I don't, in fact, have the infinite energy that would be required to keep those cosmic rays from flying through my body and disrupting cells, or flying through my computer and disrupting its memory. I can try. I can make sure the bias on all my transistors is high, so they don't go changing state when they receive some slight perturbation. But that's something I can do in practice, but that's not an in principle complete protection from the rest of the environment, or from any side effects of my interaction with the rest of the environment. And again, this has been known in AI for a long time under the rubric of the frame problem, that we can make our best predictions about what will happen as the result of an action. But it's in fact undecidable. The set of all things that are not impacted by my action is a set that I can't decide the membership of, in principle.
Yeah, I had read that in the paper also about, like, you can't even, tell if any perceived object is not part of your own mind. So it's hard to, because you can't define your own boundary, right?
Right.
Okay, let's see. Oh yeah. So we went through this. So maybe here. So as an organism develops, we can expect what it can detect and what it does with the information it obtains to change. So we expect the quantum reference frame it implements to change. Such changes may be gradual, for example, as a child increases her native language vocabulary, or radical, for example, when metamorphosis constructs an entirely new body with new sensors and effectors for an insect. Such changes naturally raise questions about the identity of the system undergoing change and whether this identity itself is changing over time. And I love the modeling organisms as processes, right? So modeling the system as a process and modeling the environment as a process. Could you maybe speak a little bit to perhaps modeling the boundary as a process?
Yeah, and I think there are two ways to think about this, at least. But one way is, and two of these ways are often conflated in thinking about the FEP. So I think it's always important to draw this distinction. The FEP stated in terms of state space boundaries, and we often think of it as mapping those state space boundaries into boundaries in some spatial embedding. So I think of my Markov blanket as my skin, for example. Or we think of the cell membrane as the Markov blanket around the cell. And when we do that, we're faced with a very immediate problem of how we think about, for example, stuff passing through my body, or stuff passing through a cell membrane. And it looks like it's disrupting the Markov blanket in some way to have objects passing through the Markov blanket. But when we think about it in state space, that problem goes away, right? What we're thinking about when, for example, we eat food, or when a microbe ingests some sugar, is the state of some molecule is changing, or the state of some collection of atoms is changing. A chemical reaction is just a change of state. If we think of a molecule as a bunch of atoms that have a bunch of relationships, some of those relationships change. And so the state of that collection of things and relations changes. So we can think of all of these processes as movements of vectors through state spaces, where the vectors are encodings of the states of some degrees of freedom or some system components. So now when we think about, and in that picture, Mike and I drew a picture of kind of the evolution of life, right? As life is consuming more and more of the state space. Life is acquiring degrees of freedom as it develops, as more and more matter is incorporated into some living lineage. We were thinking about the the lineage of all cells that are descendants of some universal common ancestor. So if we think about the development of life, this cell lineage over the last 4 billion years, yes, that picture, that's nice. More and more of the degrees of freedom of the planet, more and more of the stuff that's part of the planet, carbon and oxygen and calcium and so on, is incorporated into living systems. So the whole state space of all of the degrees of freedom, say on the planet, has an evolving boundary where more of the degrees of freedom are now participating in this process we call life and are in life-like states. More and more molecules are in life-like states. Things that were parts of rocks at one point are now part of my DNA, for example. So we can then think of this boundary itself, as you said, as a process, as a thing with a state space that gets larger and larger. And at some point, we reach an equilibrium where life can't become any bigger without completely consuming the resources of the planet. And in fact, life solves that problem by not consuming abiotic materials, but by consuming biotic materials. Right? Most of the molecules in our bodies are in fact molecules that were once in some other living system. So life is now just shuffling stuff around within its own structure, within its own cell lineage, as opposed to taking it out of the abiotic environment. And this is, in a sense, the fundamental idea of the Gaia hypothesis of Lovelock and Margulis, long ago, back in the 70s. So I don't know, does that address your question?
Yeah, most definitely. And I think it leads really kind of nicely into like this next question. So we'll just skip right on ahead. So we're talking about life as a process of boundary expansion. And when we consider modeling the environment as an agent, right? So let's talk about the title of this talk, Modeling the Environment as an Agent, and then the expansion of life in this environment, right? Which also includes all of the agents in the environment. I wonder about the concept of the inner screen, or maybe like the internal state model. So like I tend to think about it like maybe it's like a lava lamp, right? Like the environment is like a lava lamp with all kinds of like little life bubbles bubbling up and merging and coming apart, and like tons of inner screens in the environment as an agent. So like, am I like going too far? Should I rein it in a little bit? But just in thinking about like maybe I am an internal screen for the environment as an agent, as there are tons of internal screens within me.
Yeah, I think it's perfectly reasonable to go up and down the hierarchy and see what it looks like from each point of view, right? And we can look at the cellular level, where every living cell has some environment that's everything else in the universe except it. And its job is to navigate that environment and maintain its Markov blanket. So what does that environment look like? I mean, for your typical bacterial cell, its immediate environment is some biofilm. So its immediate environment is a bunch of other bacterial cells. And if you look at that biofilm, for example, then its immediate environment may well be my intestine. So we can think at all of these different scales and ask, for a system at that scale, its whole environment, is the rest of the universe. But what really matters is its nearby environment in state space, which is, if it's an organism, that nearby environment is going to be populated with lots of other organisms that may be more or less similar to it. But just because they're organisms makes them to some extent more predictable than kind of the wild open environment, which the sort of non-organismal environment is much less like me than the organismal environment. So I know much less about it, kind of in principle, than I know about the organismal environment. And that's true at every scale. So we can think of the immediate environment of any collection of organisms. So your example of the bubbles in the lava lamp, we can think of all the bubbles as one system, and the goo as the environment. Or we can think from the point of view of just one bubble, where the environment is filled with these other bubbles. And we get different perspectives when we do that. But I think all of those perspectives are interesting. And they're all perspectives in which the environment, even if it's the abiotic environment, is an agent. It's just an agent that speaks a very different language than the language of life. And life is constantly, I mean, again, this was the point of Gaia. Life is always trying to turn the abiotic environment into a more hospitable abiotic environment, even though different components of life are constantly competing. So we can think of life as a whole, or we can think of these little pieces. So your cat, for example, has the goal of always being in front of the camera.
Yeah, that's great. And so in the inner screen guest stream, which I watched in preparation for this because I hadn't seen it before, and maybe like this is something that you can't speak to because it was after you had left, but Carl talked about the concept of having an innermost screen, or like a fundamental, undissolvable, innermost Markov blanket. And so I wonder, like in the concept of something like a human, which is, we're just a large composite of millions of other organisms, many of which, or half of which I think, are not human. So in this premise, like, is the inner screen, of this gut bacteria living inside my stomach, like, that's like not that's like past my inner screen, or it doesn't seem to me like that the screens are ever indivisible. So I just would love to hear your perspective on that. Like, is it just screens all the way down, or what do you think?
Well, I think here again, it's useful to make this distinction between informational boundaries and boundaries in some sort of space-time embedding. So if we're thinking of individual organisms, for example, we're thinking about things that are separate in space. But if we're thinking about a human as an information processing hierarchy, as, if you will, a virtual machine stack with some layers doing processing that's very close to the environment, the overall environment of the human, not the environment of any of its cells, but the overall environment of the human. We can think of kind of the surface systems that are processing that surface information, and then deeper systems that are processing more highly processed information. For example, the components of my information processing system that identify objects are way inside the boundary that's just identifying edges and bits of light. And then my processes that are identifying multi-object events and trying to deduce goals and causation and stuff like that is at yet a higher level of abstraction. So now we're not thinking about biological components like cells. We're thinking about virtual machines in a computer. And so the top level from this perspective is the top level of the information processing hierarchy, which you can think of as the highest level metaprocessor in the system. The highest level attention allocator in the system. And its job is just to, its environment consists of all of the lower level processors that are many hierarchical levels down dealing with the overall environment of the organism. So, for example, my overall environment. But the environment of this high-level metaprocessor is just other processors. And all it's really doing is giving them thermodynamic resources. It's saying, okay, you do some work, now you do some work, now you do some work, now you do some work. So its generative model is a generative model of the processors that it's trying to allocate attention to. And we make it the highest level virtual machine just by saying there's no metaprocessor on top of it that's allocating attention to it. But if you were to take that individual, say, take me, and put me in a social context, then now there is some higher level system that's allocating attention to me sometimes and other people some other time. For example, that's what's happening in this conversation. Attention is switching between the two of us and the audience.
So there's a related question from the chat. The question is whether these screens can do anything more than reflect, or if there's a way to actually build up a higher level of structure.
Well, in a generic thing that active inference agents do is reproduce by some means or other. They may get their environment to reproduce them for them. So computers, for example, get us to reproduce them instead of doing it themselves. So what is that for? I mean, what are systems trying to do by reproducing? What are cells trying to do by reproducing, for example? And one way to think of what they're trying to do is just decrease their uncertainty, right? If I make another copy of me and stick it in my environment, then now I have something that's very like me. So to the extent that I know how I work, I know how it works. So it becomes something that's more predictable. So the FEP itself requires systems to reproduce, or it provides reproduction as a way of reducing free energy, as a way of reducing uncertainty. Now, of course, it's not perfect, right? Cells can reproduce, and their daughter cells can do something that they don't expect. And for example, processes like cancer are examples of that. Daughter cells of some stem cell are now behaving in a way that they're not supposed to behave in the body. So they're decreasing the predictive power of their environments, which are the cells around them. So built into the the idea of active inference is this mechanism for creating complexity, which is reproduction and differentiation. So in a sense, you can see the whole natural selection story as driven by uncertainty minimization. And Carl and several of his colleagues have, of course, as we have, published various papers about this, applying the FEP to development and evolutionary processes.
Sorry, so I think it's here. Maybe it's the next slide. Let's see. Hold on. That. Oh, go ahead. Go ahead, Daniel. Was there another question? Okay, perfect. Okay, last one. Let's see. So I'm trying to drag this away. It's this one. So here we talked about individually coherent models of the behavior of a system. What is required for them to be mutually coherent or intertranslatable? And I just want to just talk about coherence. And I know it's like a completely different discussion of coherence, but I was thinking about the coherence that was mentioned also in the inner screen live stream, like about coherence creating internal screens. And I just wonder if there's and you talked about coherence and the importance of coherence in the quantum realm, and you mentioned it here. And I just want to know if you can speak a little more about coherence and what that might mean for active inference and the FEP overall, like just a broad overview, since it's mentioned as so important for so many different processes.
Yeah, well, this is another word that gets used in multiple ways. And when we talk about quantum coherence, we're talking about entanglement, basically. So non-separability, a lack of conditional statistical independence. So there's one sense of coherence that is a lack of statistical independence. There's another sense of coherence, which we're using when we talk about models being coherent, which has to do with intertranslatability, or as in this diagram, has to do with maps being commutative, being able to go from, say, in this picture, M1 to M, mapping from M1 to M2 at T, or waiting some time and doing the mapping gives you the same answer. That's commutativity of the diagram. And that's a form of coherence that's defined mathematically or syntactically, essentially in a mathematical system, but it carries with it some semantic information. So coherence in that model-to-model case is semantics. It's the existence of a relationship between two objects that is preserved through time. So it would be nice if we had multiple words in our vocabulary for this, because it's important not to keep those two senses of the word coherent straight. One means entanglement. One means a relationship being preserved across some transformation.
Thank you. That's super helpful. I guess we're wrapping up. So
yes.
Thank
you,
again.
Bleu and Chris. We're definitely looking forward to the January stream on the book with Glazebrook. So Thank you again, Chris and Bleu.
Okay.
Farewell.
Thank you all.
Bye.
Okay. Ciao.
Welcome
Hello,
back.
everyone.
Go for it, Andrew. Thank you.
Yeah, thanks, Daniel. Thanks, everyone. So we're excited to present some of our preliminary work. This particular project is entitled, a bit verbosely, Hierarchical Active Inference Modeling of Social Trust Dynamics in PTSD, Integrating Qualitative Phenomenology with Computational Psychiatry. This project is largely based around applying the active inference framework and modeling techniques for gaining insights into potential sort of minute real-time inference dynamics that may occur for individuals with or without PTSD. And so a lot of this kind of arises from our work with Active Inference Institute, with a project started by Jeremy Cooper, who did a significant amount of work on PTSD. He is well, actually, I would rather let him introduce himself, but I'll just briefly introduce myself. I've been involved with the Active Inference Institute for a few years. I've been on the scientific advisory board this past year. Some of you may recognize me for teaching tutorials or the textbook through the Institute or a few academic conferences. And I'm largely a programmer and data analyst by trade. And so it's been very exciting to try and figure out how to align the goals of computational psychiatry with sort of research in mental health and actually maybe gaining more insight into improving treatment interventions. And I've just laid out here some of the kind of guiding research for this project, including Jeremy's work and one of our other collaborators, Angelos Kropotos, who's assistant professor in experimental clinical pathology in the Netherlands. And I will give it up to Jeremy now. Jeremy, if you'd like to introduce yourself, and anytime, since I'm controlling the slides, you can simply say like next slide or next slide, please, and I'll change the slide for you. So.
Yeah, gladly. Thanks, Andrew. So, folks, I am Jeremy Cooper. I'm first and foremost a therapist, as well as an adjunct professor at Regent University. And along the side, I usually do phenomenological research. So the idea behind our project here comes from my dissertation, which was a phenomenological study into how individuals with PTSD form/change beliefs. And so it was from that I, well, as you do, I got my results and everything. But along the way, I was introduced to active inference. I did the textbook group a couple of rounds. And then whenever we launched projects, I was very grateful to come along. Angelos, Andrew, and we have been working on this ever since. So it's very exciting to be able to present this. And we welcome any and all feedback. So yes, Andrew, if you want to go to that next slide. What I'll be doing is just briefly giving an overview of what my dissertation consisted of. There is a preprint that's currently published that is a condensed version, much more readable. So that is what this is based off of. So I'd like to introduce or invite everyone to think of things in terms of what trauma-related beliefs might be as opposed to a belief system. And the large idea that I have is, and coming from some of the sources you can see here, that trauma-related beliefs in a way moderate the symptoms that someone with PTSD might experience. That could be because there's a large phobia of affect. That could be an extreme of emotion. That could be a particular emotion. Then also the trauma-related beliefs in a way would moderate their exposure to any sort of intrusive symptoms. And so in essence, what we're looking at is individuals following PTSD. We're looking at folks who have a lifetime prevalence of it. We're not necessarily looking at someone who is a month out from the trauma occurring. We're looking at someone who may have been diagnosed for 5 years or so. There's a good chance that they will develop these beliefs that make way for them to navigate their symptoms, if I can say it that way. So it could be to avoid particularly distressing symptoms, or it could be to accommodate symptoms that they already experience. One of which might be this idea of meaning violations. So the meaning violation concept is that those who undergo PTSD, they suffer a core change in how they see themselves as a part of the world. Andrew, if you want to go to the next slide there. So I became curious about this idea of them in the world, primarily from a phenomenological backdrop looking at agency and how agency interacts with interoceptive processing, and then how that interacts with affect. And I'll say affect, I'm understanding in a different way than emotion. Emotion, of course, we can more easily identify that in relation to something else as sort of a cause effect. But affect, I'm talking about more in the way of how Slaby 2008 talks about it, where affect is a way for an individual to view their world. It's a homeostatic sort of relationship, tells them where they need to adjust, tells them their place in the world, how they fit, how they don't fit. These are perhaps larger, like as we're getting into the winter here and we have seasonal affective disorder, then everything starts to feel a bit more gloomy. Those are the types of affects that can also be synonymous with the idea of moods. So that's the understanding of affect that I'm carrying into this work, as well as the idea of agency. One helpful definition of which is agency requires a cohesive narrative, a sense of body ownership, and a sense of self-efficacy, accomplishment. And so a transdiagnostic concept that's been developed by Sass et al. Is an anomalous self-experience, which would be that one self-experience becomes anomalous. It can be quite descriptive. It's the idea that one is experiencing themselves in a bit of a strange way. And so that's where we looked at interoception to see how that might be occurring. Andrew, if you want to go to the next slide, please. What Ratcliffe discusses in his very transdiagnostic book, Real Hallucinations, is the idea of an anticipatory style. This is akin to the idea of protension, very, very fundamental to the aspect of self. It's pre-given. It is before conscious recollection. But the idea of an anticipatory style is that I expect something to naturally come next. But it's a motive. It is a feeling. It's the analogy that he uses is if you know a song, you're in a way expecting the song to have the right note afterwards, and then all of a sudden it's out of tune or something's changed about it. And it's that sense that something's off all of a sudden. And Ratcliffe talks about whenever it comes to PTSD in particular, the way that the anticipatory style changes is that the individual loses touch with the shared interpersonal world. And so this idea led directly into my research question for the dissertation is, how would it be for those with PTSD to describe their relationship with freedom of thought, liberty to experience spontaneity, or simply assurances of their experience? And then overarchingly, to sum it up with the literature review, is how does that equate to beliefs? Andrew, if you'll please go to the next slide. The study design itself, as I said before, was a phenomenological study using Scott Churchill's experiential phenomenological research method. I interviewed 7 adults diagnosed with PTSD. The semi-structured, the questions composed of 2 broadly overarching categories. What's the impact of diagnosis on yourself, view of others, your relationship? And how has that diagnosis itself impacted how you view the world? So one of which is symptomatic, one of which is impact. And through this particular design, it lends itself more towards these structural descriptions. It's similar coding process, but your end result is a very, very rich, nuanced approach to some of the key phenomenological ideas is the idea of freedom and also meaning making. So that is, I should say, another key aspect to my understanding of symptoms alongside moods is that they help us make meaning of our place in the world. Andrew, if you'll please. The primary study findings that relate to our project, first one, these were sequential building upon itself. First one is isolation. So the idea of isolation, it comes about more as a way to moderate their experience, or rather mediate their experience of hypervigilance. Because the experience of hypervigilance was felt in the increased physiological arousal, the heightened anxiety, the heightened perception, and long-term over time, that perception maintained, and so then they started to isolate themselves as a way to prevent that heightened awareness. From there, the isolated disposition was the attitude of to stay isolated away, because now what they have accommodated to alleviate hypervigilance has also led them to this very, very painful, sharp reality whenever they do come in contact with other folks, that now their experience is different from others. And this led to the idea of self-doubt. And then so the final one where it can be termed a belief system, if you will, is this idea of jadedness. And of course, this is again a phenomenological mood. That is that the idea of jadedness is they have a feeling, a sense that they are distinct in the world, separate from others, that accommodates their isolation, allows them to act purposefully, but doesn't have to encounter the pain of interacting with other folks. And Andrew, if you will, please. This led to the idea of social invalidation and the proposal that perhaps interoception is a social shared understanding, coming back to Radcliffe's idea of a shared interpersonal world, as well as Peter Fonagy's idea of Peter Fonagy and Chloe Campbell's idea of epistemic trust, mistrust, and credulity. The notion that a individual's piece of information they are giving me applies to my world. Now, so much of it's correct, but does this actually fit for my world? And for those that were interviewed as they lived with PTSD, their primary concern was that they would doubt their experience of the world if they did interact with others. So with that, I will transition to Andrew, who will share our inspiration and our design for our model and our agent.
Awesome. Thanks, Jeremy. Yeah, so Jeremy essentially brought a lot of his work to the Institute and to the sort of project that was formalized. And so what we proceeded to do was create a small team of researchers who have this kind of variety of backgrounds, who are all quite interested in PTSD and a lot of sort of adjacent topics. So again, I already mentioned myself, Jeremy, and Angelos, and we've also had a lot of help from a researcher at UCL, Han Sun, and who helped a bit with the programming. And so the goal here, as we already know, was not so much to try and create an active inference simulation to recreate trauma. A lot of work has been done in ethology to try and understand things like fear learning and associations. And whenever we imagine trauma as something very intensive, of course, the idea of carrying out a simulation that might be carried out also empirically, such that we can fit our model to empirical data from real individuals with PTSD, obviously need to follow like IRB protocols and be ethical. And more importantly, the point is not to necessarily understand the original trauma in and of itself. It's much more aligned with Jeremy's work, which is how do we facilitate those who have already been through the trauma or anomalous self-experience? How do we facilitate them to having a higher quality of life, given what they have been through, knowing that actually there's a lot of adaptation to, or maladaptation to the symptoms that sort of follow from the experience of the trauma. So here I've listed out some inspirations. They include a lot of work by Ryan Smith. Has done wonderful work in computational psychiatry, as well as empirical work and fitting the models to real data. And his simulation on simulating the computational mechanisms of cognitive and behavioral psychotherapeutic interventions. That was sort of a core inspiration of simulating an artificial person who might be in a decision-making task. He simulated exposure therapy, which actually recreates some interesting dynamics of fear, learning or unlearning, or extinction, found in empirical literature, and highlights the role of contextual priors, which is, it brings up this interesting case where someone who believes they're safe suddenly doesn't quite know what to do once they perceive they're in danger. And it relates a lot to the idea of like kind of associative learning, but how do we engage whenever we infer that we're in particular contexts, and whenever we're in a particular context, how does that change the ensuing behavioral outcomes? A very important simulation also to bring up was Adam Lenson and Friston's work in 2020, where they more directly were attempting to model psychological stressors, especially with PTSD is sort of a core topic, but again, that's much more ethological. They simulated a mouse in an environment where there can be a real threat in the environment. And so that's, of course, not the direction we want to go necessarily, but their model provides a sort of framework for looking at things like multimodal sensory integration, which is where we consider more strongly the idea of receiving, visual observation, auditory observation, witnessing yourself making actions and reflecting on those actions that you made, and thinking about things like safety and physiological arousal. And then after that, we have Adam's Everything is Connected, Inference and Attractors and Delusions, which is a great work. And actually, if you understand this paper, you understand most of what our model does and what the behavioral task is. We essentially recreated a lot of the dynamics found in that paper. That was more focused on studying delusion, which is more generally defined as just false inference despite disconfirmatory evidence. So it's not to, we're cautious about using kind of stigmatized terminology. It's more about just how can we arrive at a more precise sort of terms for how we understand something like aberrant or pathological behavior. And I also like that this paper was actually not dedicated to understanding PTSD or trauma. It was more dedicated to understanding how delusions arise in decision-making and perception in the case of schizophrenia. And so I like it because it just kind of highlights the sort of translational capacity that we might find in computational psychiatry, where we make models that can potentially, depending on prior beliefs and parameters and model architecture, exhibit a variety of kinds of pathological disorders and might lead to understanding different kinds of sort of transdiagnostic criteria for defining things like delusion or pathological behaviors. Deeply felt affect, and as well as Ben Rameau's role of affective states in computational psychiatry. This kind of just informs some of our decision making of how to model arousal and affect in our model, and getting some insight into the relationship between affect or emotion or mood with decision making and confidence in one's deliberate decision making, as opposed to, say, relying upon habits when someone doesn't know what to do, and so they kind of just repeat what they've done before as a sort of auxiliary. And then finally, Towards the Computational Phenomenology of Mental Action by Samved Smith. This also was a very interesting piece relating to hierarchical modeling and having sort of higher layers in a model, or what we'll call metacognitive layers. The idea that we can perceive ourselves perceiving, as it were. We can have beliefs about our beliefs. So to believe that someone is untrustworthy, and then above that, what does that mean for me to believe that this person is untrustworthy? And in a variety of other kinds of ways that that logic can be applied. So for sake of time, I might speed through some of these slides a little bit faster than others, but I wanted to quickly provide, there's sort of a broader general framework being employed here that you're probably well aware of at this point if you've been watching the other symposium streams. But even more general than active inference are these theories of predictive processing. And so Lisa Feldman Barrett, this is a quote from her that I have used in tutorials to try and provide a sort of intuition for predictive processing and its relation to how we understand sort of perceptual processing in the brain. So here I've just highlighted some different sort of how we understand sensory modalities. So there's interoceptive sensory modalities, what we read from within our bodies, and then there are exteroceptive modalities, and those largely align with sort of the 5 colloquial senses of sight and touch and olfactory and so on. And then proprioception, which I didn't have an example of, but it's essentially related to sort of physical movement and reading of the body in space and being able to sort of coordinate. And then what happens is that we essentially take in varieties of observations of sense data at any given moment, And and from there, we have to infer what does this mean, or what caused this? What are my beliefs about the world that generated this? And this happens down all the way down at a very rapid pace, continuous sort of level. So it's not to say that all of it, probably some of it, but not all of it is necessarily conscious. We're looking at more at the level of sort of neuronal dynamics and the ability of the autonomic nervous system to regulate itself, being able to breathe without having to think about it. So it just gives a little bit of intuition. We have to infer what our sense data means, and then reciprocally, sometimes we use our inferences to try and act to elicit different kinds of sense data. If my stomach is growling, that must mean I'm hungry. If I'm hungry, if I eat food, have caloric intake, then I will no longer be hungry and I will be sated. Is kind of quick and crude example. So from there, how do we proceed to actually model the kinds of phenomena that Jeremy sort of identifies in the structured setting of collecting information from the individuals diagnosed with PTSD? Well, I've taught on this before, but more generally, when we look at things like agent-based modeling, which is a technique that goes back decades at this point, the way that it's done is heavily tied to the kinds of computational resources we have available. And so there are more and more capacities for us to produce more interesting, sort of intricate or complex models, not so much with the focus on making complex models for the sake of it. In fact, it's very important not to do that, but it's to be able to simulate dynamics that have been empirically found in the literature, and in our case, looking at sort of empirical neuroimaging data analysis and modeling of neuronal dynamics at a very fine scale, and building up from there. Nonetheless, here's some traditional guidelines. One, when doing agent-based modeling, we have to apply different kinds of assumptions that should be convincing to readers, most imperatively in relation to empirical findings. If you make a model and no one is convinced by any degree of its realism, then perhaps it should not be employed. Robustness, simple as possible and no simpler. Those who do things like computational modeling or modeling of data are all too familiar with this. You can make a model that is so deeply overfit, it's so deeply specific to a particular case, a particular subcase, that as soon as you start looking at the broader phenomena you're actually interested in, you realize your model is no longer applicable. So it needs to be able to generalize. It needs to be relatively robust to tiny modifications to the model. Reproducibility is pretty straightforward. There's a reproducibility crisis in science, some or maybe many would claim. So it's good to allow others to be able to reproduce your work whenever it comes to settings like this, where there's computer programming and code involved, releasing your code to the public. Finally, non-triviality. The results of the simulation should be non-obvious. I do think that it's always good to be able to reconfirm our previous hypotheses with data. So I'm a little on the fence about this particular guideline, but nonetheless, we do want to actually yield a significant insight from doing this modeling work. We want to see what we could not have seen otherwise. So nonetheless, a classic quote from statistician George Box: all models are wrong, but some models are useful. And so we aim for useful models that kind of follow particular guidelines and can be empirically validated. So more generally, computational psychiatry aims to build what are called computational assays. And so what we do is that we try to find, okay, if you could model the brain, and you use different kinds of, decades of research to try and understand how that could be modeled. And if we know that, theories of predictive processing are all but ubiquitous in at least theoretical, if not other areas of neuroscience as well, then, how can we start to map the parameters of these models to neurobiologically plausible correlates in the brain? And that is, I'm jumping ahead a bit, but I think active inference does an incredible job of that. And that's part of what drew me to this particular framework, looking at the basal ganglia, looking at interconnectivity between the prefrontal cortex and the hippocampus when it comes to memory recall and deliberate decision making, and actually being able to watch more precisely how that plays out such that we can move towards having more precision in psychiatry, whether it be for diagnosis or patient stratification, understanding particular subtypes or phenotypes, we might say, in pathological disorder. And then from there, being able to simulate or test different kinds of intervention treatments in a very safe artificial environment that appears to more or less well approximate reality. So the active inference framework, again, you've heard a lot about it. It largely starts with the idea that everything that changes in the brain must minimize free energy. And this kind of follows from a neural process theory that active inference holds to foundationally. So arising from this kind of work that many like Thomas Parr and Carl Friston and others have done in the past, from studying things like perception. We're familiar at this point with predictive processing, with Helmholtz's idea of unconscious inference, of the mind sort of filling in the gaps in the data that we might otherwise miss, such that it can make more sense to us, and all these sorts of things. And so, and then we also look a lot at the idea of, these are not just brains in a vat. These are entire organisms who at minimum need to maintain some kind of homeostatic regulation. Otherwise, they cease to exist. Again, I recall the idea of me having a caloric intake such that I can stay alive, regardless of all the various inferences and prediction error minimization I'm doing along the way. Hopefully that helps. So with generative models and no simpler, what I love about this is that if we do have this kind of general, potentially universal, so to speak, principle of how the brain works, then the challenge here, or the goal, is no longer a necessity to model, say, several billion neurons in the brain. We're not trying to emulate the entirety of the brain. We're just trying to find the generative model that describes the problem the brain is trying to solve. So that allows us to reduce a lot of the complexity in constructing models and trying to map them to reality. Active inference, again, relies upon Bayes' theorem, relating observations to hidden state beliefs, having a relationship through a sort of Markov blanket relationship with one's environment, in which case it's not so much that you need to know everything, it's that you need to know what are the agent's observations and what are the kinds of actions they can elicit. And so if you're able to sort of establish where those sensory and active states lie in the overall equation, so to speak, between the agent and the environment, then you're able to sort of establish these conditional independencies between the agent and the environment, such that you don't necessarily need to know everything about the environment in order to understand what's going on with the agent. You just need to be able to understand the observations the agent receives and the actions they elicit, and that's about the best that the agent itself can know. So I do bring up this is a policy inference equation that's used in certain implementations of these kinds of models. It's the one that we employ, and I just very much like it. I think that it can sometimes be overlooked, of course, unless you're doing the programming. But this has come up during previous tutorials I've taught. It's simply to make the point, whenever it comes to decision making and active inference, people have related this. I've been asked before, like, how does this relate to something like Kahneman and Tversky's Systems 1 and Systems 2 thinking? And I argue that it actually has this sort of Systems 1, 2, and 3. It's crude, but it's just to say with minimizing expected free energy tied to gamma or policy precision. And then finally variational free energy and E, or habits. It's kind of like we have deliberate decision making and reflexive decision making in the moment for maintaining one's model, and then finally context-free habits, which strongly aligns with a lot of research we find in psychology on how we do frequently rely upon habits or sort of heuristic decision making, especially in contexts of uncertainty. So it's just we do there's I just point that out to say that there's a lot more alignment here with other disciplines than what might initially meet the eye whenever we start looking at the fuller breakdown of negative information gain minus pragmatic value, and getting into all the mathematical formalisms. And then finally, with fear learning, which is a lot of, again, Angelos Kripotos's contribution when we're coming back to PTSD. This is sort of an informative framework. There's obviously been an immense amount of work done, but it relates to the idea of looking at Pavlovian conditioning. And so one way of thinking about this is that we might relate the anomalous self-experience or the experience of the trauma as if it were like an unconditioned stimulus. So the setup in a Pavlovian fear conditioning paradigm is that you introduce an unconditioned stimulus, something negative, some kind of negative stimuli. Unfortunately, using mice, they might use like a kind of mild shock that doesn't necessarily permanently harm the mouse in any capacity, but nonetheless, it's something that the mouse does not very much like. And then that gets paired with a conditioned stimulus that, in reality may have no intrinsic relationship to the unconditioned stimulus. So you might play a light tone, a sound. And so over time, the mouse begins to associate hearing a tone with being shocked. And then through a learned kind of fear-driven behavior, the mouse begins to freeze or potentially try to avoid whenever it comes into contact with hearing the tone, even though the shock may no longer follow it. You might remove the shock component from the task altogether, and now it's just unfortunately, the mouse has this paired association. And from doing these kinds of ethological studies and knowing that there's a very strong relationship in the mammalian brain and in the brains of mice, of cats, and so on with humans, there have been attempts to sort of extrapolate these kinds of findings to understanding how humans sort of process fear and how fear memory develops. And some findings show that memory of the fear's acquisition. So if we think of an individual who goes through a traumatic experience, over time, even through exposure therapy, even through different kinds of sort of fear extinction techniques, the individual doesn't actually have their original memory of the trauma erased. Right? It remains. Instead, they have to form new memories about the relationship between an unconditioned stimulus and a conditioned stimulus. So, for example, for individuals who have been through trauma and then experience, some kind of negative, or rather they hold some kind of negative association between that and, other stimuli that otherwise might not be a problem. Oh, someone sort of benignly lied to me about something, benign just meaning like it didn't have any strong stakes. They weren't necessarily trying to be malicious, and yet that somehow triggers an associative connection that I have to my trauma. And in real time, perhaps not even immediately thinking about the trauma itself, the individual may start to exhibit the learned negative behavior. They might start to avoid that person. They might kind of start showing different kinds of symptoms that they've developed over time. And so we think of things like maladaptive fear, or when fear exceeds the actual threat, generalizes too broadly, or persists after the threat is gone, or prompts excessive avoidance. And again, relations to associative learning, Hebbian plasticity, and then particularly interested in neurobiological correlates to this. So sort of the amygdala has a very strong role in a lot of our dynamics, actually, not just detecting threat, but also detecting sort of general saliency. It's even involved in reward processing. So it's, unfortunately in PTSD, it's often that in humans, the volume of the amygdala may or may not shrink to some degree. But there will very frequently be a different kind of like aberrant circuitry activation going on. There can be a sort of short circuiting. So whenever you think of someone with PTSD being like so-called triggered, what can happen is that there can be a rapid recall of different kinds of memories associated to trauma that then affect what we might otherwise view as cognitive, deliberate decision making that we usually view different areas of the PFC to be related to. So with modeling all of this, the methods overview, we chose a behavioral task, a card advisor task. I'll go into that in a moment, so I'll stay brief here. The optimal strategy for this task, that is this task which is reproducible and it follows ethical guidelines. At no point is the participant actually in danger. There is no confirmatory evidence that an individual would be in danger when playing this task. It is structured like a game where you don't know the color of an unseen card. And so there's an advisor there who's sort of part of the environment, so to speak. They're part of the administration of the task, and they would procedurally tell you what the color of the card is, and then as a participant, it's your job to try and decide, are they lying to me or not? And so the game-winning strategy is to actually engage with the game, ideally play multiple times, and then see if there's some kind of pattern to the trustworthiness or untrustworthiness of the advisor's advice. So they give you the advice, you make a guess, you might choose to go with their advice, you might choose the opposite, and finally you flip the card over and see if they're right or wrong, and it continues. And this has relation to empirical studies that have been done in the past with different kinds of trust-based games, including with the emphasis on pathological behavior. And so they found for a sample of women with assault-related PTSD diagnoses, whenever they played certain kinds of trust games like this, what was interesting was that they actually had similar prior beliefs about trust as the normative sample of individuals not diagnosed with PTSD or other pathological disorders. So it's not so much that they were predisposed to distrust the advisor, but rather once the advisor did lie to them at some point, give them false advice, and then it turns out the color was the opposite of what the advisor said, it was much more difficult for individuals with PTSD to kind of regain the ability to have trust in the advisor again, even if the advisor switched back to being trustworthy again, which says something about sort of the belief formation or evolution or change in belief dynamics. You know, it's that sort of change over time. We can't only rely upon some idea of priors, but actually how they play out over time. With the agent model, we chose a hierarchical, partially observable Markov decision-making process, which is quite a mouthful for those who are not familiar, but it suffices to say they're a relatively kind of powerful, interpretable, almost standard in some ways model that gets frequently employed in computational psychiatry. It's just because there's so many mappable parameters and allowing for different kinds of more discrete decision making. So a model who can actually, you know, infer trustworthy, untrustworthy, can actually choose green or blue as the card color, and so on, while actually being able to play out its dynamics over time. And of course, it's frequently used in active inference. So we're using free energy minimization, and expected free energy minimization is sort of the neuronal dynamics at play. And then we also have multimodal sensory integration, where the agent actually is combining different kinds of observations it's receiving at any given moment to make its inferences. And then after that, given that this is still a purely in silico model, we simulated many different agent variants, 576 of them. And the idea there was simply to get a view of what is this model capable of in the first place, without making too many other assumptions, given that we would like to move in the direction of fitting this to empirical data. So what follows now, I've essentially describe the task, and we have a hierarchical model. So we have a lower layer here that directly kind of interfaces with the sensorium. It receives observations for each trial of the task. One, we check your heart rate. The agent kind of self-observes its own heart rate. That can very much relate to interoception. What does my physiological arousal mean? You know, that this might be read to mean a variety of things in the cases of distorted interoception and potentially pathologically. That is, maybe something good happened and it surprised me, but I'm excited, and so my arousal has gone up. And yet a distortion would say, oh, I'm I have a high heart rate, whether you're actually thinking about it or not, but it's the association between having a high heart rate and potentially feeling that one is in danger, right? That can actually lead to a cascade effect of inferences where someone, for example, might become triggered, right? They misinterpret a situation and what it means for them in their body and their ability to read their body, and then it leads on to other beliefs that may not have any direct one-to-one relationship with the actual scenario that you're immediately encountering. So we check your arousal. There's a covert action by the agent. Do they trust or distrust the advisor? It might not mean much of anything. They haven't received any evidence yet if the advisor is trustworthy or not whenever you start with the first trial. But nonetheless, they might be predisposed to go a particular way with that. Then stage 2, they'll receive advice. We'll check your arousal again, and then they'll actually make a decision. And then we added an additional option. Not only can you choose blue or green as the card color, but you can also choose to withdraw or decline making a decision. We added that because we wanted to see if the agents, or at least some variants of them, would choose that option, given that these are sort of cognitive autonomous agents, right? So we're not forcing them to do anything. We simply provide them with the model, and through free energy minimization, they're kind of making their own decisions. That's that notion of agency to some degree. And so whenever they choose to decline making a decision, what will happen in the final stage is that they'll receive some feedback telling them if they were correct in their choice, incorrect in their choice, or they'll receive a sort of null or non-feedback saying, oh, you didn't make a choice, and so we cannot relate your choice to the correct card color, and so you don't actually get feedback. So it's sort of a process where the agent can decline potentially receiving a reward, decline potentially receiving a loss of losing the game. It's a sort of non-engagement, but you're still in the task. So it's not to say that the participant actually gets up and leaves and they're withdrawing. It's simply to kind of choose to not play the game, but to continue on to the next trial nonetheless. And so we were curious to see how that plays out. And so whenever we run this over many models, we have these different kinds of scoring metrics. We're looking at kind of composite of negative affect, high physiological arousal, a believed sense of danger, or a kind of false sense of danger, and then interpretation bias, which is a very specific case where the agent believes that the advisor is untrustworthy, even though the advisor is in fact trustworthy. And then we also included a delusion score, which follows from the Adams paper, which is more of an aggregate of assuming that the advisor is trustworthy when they're not, as well as untrustworthy when they are. So you have false positives and false negative inferences. Whenever we look at an overview of all of our models, which the brain largely follows non-ergodic processes, so I would take these sort of with a grain of salt. These are Pearson correlations. It's simply making an alignment. Whenever we look at all of the models, all over 500 of them, which of these parameters or different kinds of metrics from each model, kind of aligns with this hypervigilance score. Some of these are slightly redundant because, interpretation is part of the definition of hypervigilance, but nonetheless, we wanted to see what actually arises in our models. And a core takeaway is first, higher order beliefs about safety, which get related back to the agent's belief in the advisor's trustworthiness, as well as their own sense of affect, positive or negative, and how strongly, positively or negatively, they're sort of inferring themselves to be. Whenever safety transitions are very precise, meaning a belief that when I'm in the context of safety, I'm safe, it means it will persist through time. So it's kind of like environmental volatility is one way of reading that. But also inversely, if I believe I'm in danger, then danger will also persist. Whenever that's more precise, it actually leads to higher hypervigilance. It's more than likely related to the idea of once an agent does believe that they're in danger, it's difficult to get outside of that danger. It's kind of getting trapped or stuck in it, so to speak, or you're more likely to. Second, prior beliefs about safety. That one is not particularly surprising, but it is interesting because we know that these beliefs get modulated over time. So we're just looking here at the prior belief about safety, where you start at before you play a single trial. right? But nonetheless, a negative, moderate to weak relationship with hypervigilance. And this was the most interesting takeaway. There's actually, even though it's a weak negative correlation, some agents, by choosing to trust, they actually kind of bolster their mood or their affect. And it's a little kind of tricky to wrap one's head around, but when we start thinking about things like attachment theory and how we might regulate our own emotions through interactions with others, we might say that these are agents who are able to regulate their emotions at least a bit through making deliberate decisions to trust the advisor. We can think of, if there were no relationship there, then it's kind of saying, oh, I'm not able to emotionally regulate myself, not at least in terms of my relationships with other people. A lot of preliminary results, but I know I'm very, very low on time at this point. There's a lot going on, but essentially we're just trying to suss out. There's an interesting thing that happened with a lot of the models. Roughly 2/3 of them almost never withdrew, whereas about a third of them almost always withdrew. And so I tried to see what are the sort of correlations there, what are the interacting dynamics between different pieces. It seemed quite clear here that once an agent kind of surpasses some threshold of negative affect, including how frequent it is in general, how certain they are of that negative affect, meaning like a bad mood versus a very bad mood is one way of saying that. And then finally, the seriality, which is how much do you recurrently find yourself in a bad mood as opposed to having respites of a positive mood in the middle. Past some threshold, agents almost always start to withdraw. And I think it just kind of highlights the notion of the importance of looking at things like affect, interoception, how we read our bodies, how we read emotion, and how, beyond some that information gets integrated sort of with everything else in decision making. Right? And so here, zooming in on withdrawal, it was clear that certainty of false trust strongly aligned with withdrawal. So these were agents who were actually very certain about their evaluations of the advisor, but then also that came with negative affect. It's interesting that delusion score came up, and I'll get into why that is in a moment. But the idea of withdrawal is that by declining to make a decision, you're avoiding receiving disconfirmatory or confirmatory evidence of the advisor's trustworthiness. So we relate this to social withdrawal, right? It's like for many of the agents, they could actually maintain a belief that the advisor is trustworthy by withdrawing from the game. It's like saying, oh, I will just stay away from you. I will not stay away from you. They're still in the game, but I will not engage with you in order to maintain the view of you as trustworthy. And that will help me sort of regulate my emotions, and it will help me regulate my own personal sense of safety, right? We compared a few models in particular, those with lowest, highest, and average levels of hypervigilance scores, with those with the sort of average level of hypervigilance, who almost always, this particular model almost always avoided some interesting things. One, they do align pretty strongly in certain ways with some of the takeaways I have from Jeremy's research, which are agents come to expect seeing themselves not engaging with the game. They basically come to expect that is how they operate in the world, which is to avoid sort of reality testing, avoid checking to see if others are trustworthy or not, or reliable or not. And instead, they also start to further expect the symptoms that they experience. So beginning to even more increasingly expect physiological arousal, expecting, oh, this is my life in a certain sense. And then by withdrawing, again, we get to see this kind of phenomena where the agent maintains a belief that the advisor is trustworthy. Although at the higher order, at the metacognitive reflective level, it's not a precise belief, right? It's very close to 50-50. So it's a very highly entropic belief. It's like, you might be trustworthy, but I'm not going to engage with you, so I don't have to find out, right? And then finally, this is the agent who had the highest level of hypervigilance. There's some interesting things there whenever we look at the modulation and safety beliefs over time. This agent also withdrew very regularly. And so whenever they would withdraw, it would allow for this brief respite from believing that they were in danger. This agent who had the highest level of hypervigilance, they unfortunately did believe that they were in danger at times, even though they of course weren't. And so it's a false inference. But by choosing to withdraw and seeing like, oh, I withdrew, I don't have to find out if I'm in a safe situation. I don't have to find out if this person is trustworthy or not. I don't have to, do much of anything. And so it gives us, this brief moment of respite where their beliefs about being in danger, which are very high, for a moment kind of become more entropic, and it's more like, oh, okay, I'm kind of sailing this uncertainty right now, but unfortunately only to resume playing the game again where danger becomes perceived once again. Nonetheless, again, this is the highest level of hypervigilance, so these are very extreme behaviors we're looking at. And then the agent always withdrew. Another interesting thing is that the agent's gamma parameter, which is aligned in the empirical research. There's a lot of good work by Schwartenbeck and others in 2015, looking at dynamics of dopamine in relation to prediction error. This agent essentially over time loses confidence in its own decision making. And by doing that, it actually starts to rely on its habits of avoidance instead. This is very significant because whenever we actually look at the policy posterior probabilities, whenever it's actually trying to engage in goal-directed or deliberate behavior, it never once actually infers that it should withdraw. It infers that it should play the game. It should choose blue or green, and it even so we can actually look at what it believes it should have done. But because of the loss of confidence, right? It's this reliance upon habits instead. So to wrap up, so sorry, we were going to have some discussion at the end, but I think we're about out of time. Next steps, we would like to kind of increase without making the model too complex. We just want to add one more thing, which is to use more of a predictive coding or hybridic model in relation to physiological arousal. This comes up very frequently in the study of pathology, and especially PTSD and other stress-related disorders, where dynamics of like the activation of the parasympathetic and sympathetic nervous systems leading to hypo and hyperarousal respectively can strongly impact how one engages with the world. Including in extremes of, potentially leading to dissociative behaviors or more activated behaviors on the other hand. And so we think that would kind of overcome some of the somewhat excessive simplicities in the original Adams model, although the Adams model makes a bit more sense. They weren't trying to zoom in so much onto the relationship between arousal and affect in the way that we are, in the same way. So we would like to actually fit this to continuous data, which is the idea why we would use a predictive coding model or something along those lines. Then also we want to move towards making this model useful. In addition to empirically fitting it, we would like to include things like kind of equipping the agent with potential emotional regulation or grounding strategies, maybe in its policy space, maybe at the higher order level. That kind of aligns more with previous neurophenomenological work on metacognition. Basically, if an agent who has been through therapy of some kind or has learned some kind of strategy to help with emotional regulation, giving them the capacity to choose to employ that to whatever minute degree, maybe a breathing technique, not sure. We would like to very much get further into that. We could also look at treatment interventions in the form of SSRIs or SNRIs. We know that noradrenaline and norepinephrine are strongly implicated in aberrant neurotransmission in individuals with stress-related disorders. And so we could kind of simulate that because we can actually start to map that to parts of the model. We want to, of course, further test this model in different ways. We're very interested in the dissociative subtype in PTSD. And then finally, a big part of the duration it's taking to sort of do this work is that we actually committed to using open source tools. And so I've been carefully studying Friston and others' SPM library and MATLAB, and then re-implementing a lot of pieces and auxiliary functions from that into PyMDP, which I hope to sort of re-release, given it has an open source license. More preferably, I'll be in touch with some of the developers, which I have been, so probably the latter situation. And yeah, and then also looking at, I would rather get back into the original PyMDP because it's they're using JAX for GPU acceleration and essentially speeding up the ability to kind of train and test these models. So sorry that I really went over on time here, everyone, but that essentially concludes my portion of the presentation. So
Thank you. Okay. Thank you all. Till next time. All right, we're back with John Boik et al. Yes, thank you, John. To you.
Yeah, I'm sorry, I'm having a little audio trouble. And everyone can see my screen, I assume. We are here to talk about story graphs, which is a part of the CogNarr project. I'm a research fellow at the Active Inference Institute, and one of my main project there is called CogNarr. And there are a variety of links to that project, and also to the to papers that are kind of give the background story to that project. I invite everyone to stop by the Active Inference Institute webpage to look at the project. And today we will be talking about story graphs, and that is particularly discussed in this paper, CogNarr Ecosystem Preliminary Thoughts on a Story Graph Meaning Representation. So what is a story graph? A story graph is a core component in the CogNarr ecosystem. That ecosystem its purpose is to facilitate group cognition at scale. That is, you may have a group of 100,000 or who knows, 1 million people online who wish to communicate their beliefs about some topic, whatever that topic might be for the group. And the ecosystem is used for deliberation and decision making and communication. And the basic idea is that people in a group can share their belief model, their beliefs about the situation. And then by sharing their beliefs, hopefully the group can come to some degree of shared belief, shared understanding of what the situation is and what might be done and what are the promises and what are the dangers and all that kind of stuff. So a story graph is a core component of that. It's essentially an intermediate representation between natural language, spoken language, and a formal implementation of a belief model in a computer, like with vectors and matrices and things like that. So a story graph is readable and verifiable by both humans and computers, and it makes transparent and explicit a storyteller's rich probabilistic belief model about some situation. So in a story graph, a person might convey, about some particular situation, what happened, who was involved, why did it happen, what might happen next, and that is a prediction about the future. And then how uncertain are my beliefs about that prediction, or how uncertain are my beliefs about what actually happened or who was involved or all the different things. So in that sense, a story graph should be, in a sense, executable. That is, you could follow a story graph to see possible ways that this person believes the future might unfold, or look into the past and see possible ways that the events that might have occurred to lead to the situation. A story graph conveys a person's, in the CogNarr system at least, a story graph is intended to convey a person's honest beliefs about what happened. That is, if I honestly believe that cows can fly, that may be what my story involves. Someone else might not believe cows can fly, but the point of a story graph in the CogNarr system isn't to model the real world. I mean, the system does not model the real world. The CogNarr system conveys the user's beliefs, what the user honestly believes about the situation. And very importantly, story graphs are created interactively in the CogNarr system. So it is not the case that that somebody would write out a long narrative and then feed it into the CogNarr system, and then that would become a story graph. Rather, the person would interact with the system to create a high quality story graph. So as an example, maybe I'm typing into the system that something about Bob, and then the system might query me, or others in the group might query me and say, wait a minute, do you mean Bob the neighbor or Bob the baker? Or, there could be all kinds of questions like that. And through those kinds of questions and guidance, the system and the group can develop a set of high quality narratives. And behind the story graph and behind the CogNarr system are a set of ontologies and knowledge bases, which allow for consistency of meaning across stories. So if I'm talking about a cat, we all have an understanding about what a cat is. It might be a mammal, or it might be a bulldozer, but whatever that is, we understand what we're talking about together. And there are applications well beyond CogNarr for story graphs in medicine, industry, governance, commerce. And today, that is the topic of our talk. We will be discussing some possibilities of how story graphs might be used in a variety of settings. And I'm hoping that we have time for taking questions from the audience. We would be very interested to hear of what others might think of, like, oh, that a story graph could work in this situation or that situation. So please do chat with us during the presentation, and we will explore together, hopefully. Just a few more background slides. So how is the story graph related to active inference? In active inference, as I think most people are well aware, an agent, an intelligent agent, is separated from its world, the generative process of the world, through a Markov blanket. And the agent has an internal probabilistic model about how the world works, and that model, in a sense, is what the story graph is trying to convey, the belief model of this person. And in the CogNarr setting, the group cognition could be viewed as sharing and updating belief models, and hopefully evolving towards some kind of shared beliefs. And the purpose of cognition, of course, can be seen as promotion of well-being and the reduction of certainty. And in the active inference world, we talk about free energy reduction. And today's talk. The purpose is to discuss possible use cases for story graphs in and beyond CogNarr, brainstorm with the community, some areas that story graphs might have application would be decision-making, customer service, emergency reporting, public polling, instructions, systems descriptions, education, democracy, and elsewhere. And some of these applications are discussed in the paper that I referenced before. But I suspect that there are many more that we haven't thought of. Possible functions of story graphs could be model verification, model validation, explainability, communicating in a variety of different modes, so one-to-many, a corporation or some other entity might want to reach out to its group and convey some kind of rich information. Many-to-one, many-to-many could be used for record keeping, auditing of a decision process and governance, assessing the accuracy of predictions as events unfold. That is, I may have a story about how I think the world is going to unfold in the future, and that story is then a record of my beliefs at the time. And then as events transpire, one could look back at that story graph and see was John accurate? Did he predict correctly what came to pass? And that could be actually very useful for a variety of reasons, because some people probably are much better than others in predicting what is going to happen next, and then that's knowing who is got a handle on how the world works is a valuable asset to a group. I should also say, too, that I had a word earlier in one of the slides about rich stories. And that is also the idea behind story graphs and CogNarr, is that in the group setting, we would like a person to be able to share a rich story, a nuanced story, a dynamic story. And I will contrast that to, say, joining a group online where maybe someone types in a statement of some kind, like we should do A or we should do B, and then everyone can give a thumbs up or a thumbs down to that. So we're talking about something far, far more sophisticated and have the capacity to convey a very rich story, a nuanced story, conditional story. Like, I think this will happen if this, or maybe that will happen if this other thing happens, or maybe these three things will happen if something else happens. So rich stories. Other possibilities are, for even story graphs could serve as sort of a lingua franca of agent-to-agent communication. That is, as agents are negotiating some topic or aspect, they potentially could use story graphs to convey their belief models about how their world works in that situation. And then lastly, the purpose of this talk is just to socialize the CogNarr project and the story graph idea, and again, to invite participation. Our panelists today are myself, John Boik, Tim Lloyd has joined us, Glen Ropella will speak. I'm hoping Philip Wilson is scheduled to speak, but he's not here in the moment, so hopefully he will be able to join us soon. And then, of course, the audience. So just a couple more items about what is a story graph, and how does it fit into the CogNarr system. So in the CogNarr system, a user would type in a narrative, their story, their belief system, perhaps sentence by sentence or even phrase by phrase. But that would occur in short inputs, and potentially a person could speak this, or there could be other multimedia ways to input a story eventually. A user would, again, type in some kind of sentence or several sentences that would be translated into a story graph fragment. And then as the story graph fragments are input, they would be merged into a larger story graph to convey meaning throughout the narrative. And then once a story graph is completed, once the whole narrative is completed, then that story graph might be translated into alternative meaning representations, of which there's many. Maybe it will be translated into a probabilistic logical model or some other kind of model for querying, or potentially could be turned back into natural language to play that story back to the person. Potentially the system could ask the person, okay, thank you for your story. This is how I understand it. I'm going to tell the story back to you. Is this what you mean? Yeah, so and I think this is my last slide, but I've mentioned meaning representations already. So just a few words about what a meaning representation is. This is just an example. There's from the literature. There's many types of meaning representations for narrative, for sentences and groups of sentences and narratives. And this is called a discourse representation tree structure. And it's for the sentence, a very simple 2 sentences, Max fell, John might have pushed him. And I won't go into the details of this graph, but it's simply identifying the elements of the little story here, and then labeling some of them as events, some of them as agents. For example, John and Max are agents. And also pointing out that there's some time elements to these events. And there's an explanation between the 2 sentences. Max fell, John might have pushed him. That relationship is because Max fell because John might have pushed him. So this is a very simple, I mean, relative to what we aspire to in the CogNarr setting, this is a kind of a simple type of representation. And in CogNarr, this would be much more, in a fully functional CogNarr, this would be a much more sophisticated representation. There could be multiple layers. It could involve ontologies I had mentioned before, high dimensional vectors. The idea that the story would capture the dynamics of what's happening, the changes of state that are happening, and also importantly capture the uncertainty, as I mentioned, of the story in the story, and the predictions in the story. So this you can think of this image here as just a very simple version of what maybe a story graph might look like. And with that, we will move on to Tim, who's going to talk about real-world narratives, model agents that are fit for real worlds. So, are you?
Thanks. I just
Yeah,
share
thanks.
slide. So you're able to see all that? Okay. Yeah. So I guess I've been CogNarr, and on discussions with John and learning from his papers and what have you has really captured my imagination from the beginning. I can say that across a whole spectrum of associations and relevancies and saliencies of the content with other things. But I'm sort of bookending, since there's sort of an industrial applications theme to this, I'm just bookending my brief presentation of where I'm coming from and connect with this with 2 things. I guess one on one end is sort of an initiative to establish a sort of a multi-sector service ecosystem that's capable of trustworthy support in families and close-knit groups to curate and develop real-world stories together. And the other sort of bookend that I get to speak to a little bit here from an industrial applications of CogNarr perspective is along engagement with multi-agent software engineering modeling, coming up with ways to, what's a class diagram for an agent kind of a thing, if you want to put it real simply. So, look at real world narratives as a grounding, sort of a cherished, precious kind of a grounding of what it means to be human, and therefore serves as some kind of resource capable of imbuing AI with sort of things that we would consider more human and would want to see in the ecosystem of agents and systems. And the idea for me in this application is to expand the possibilities for trustworthy and safe AI by actually making it possible for AIs to actually have some concept of the meaning of trust and safety from the beginning without hallucination and fabulation. So, for me, in this respect, CogNarr represents an onboarding to sort of humans in the loop, deeply in the loop, and in the loops of all the loops, etc. So it's a potential for that kind of a thing. And we are. This is the very beginning of a kind of a thing. So, think of it maybe like the beginning of a human phenome project, the genome looking for a code of life and the phenome a code of living. And, this little illustration on the right is a popular illustration or iconography expressing the idea of the universe observing itself through the arrival of life. So, maybe narrative is kind of like the cognitive water we swim in, and like a fish, we don't really notice just how absolutely ever present and it is. And so, yeah, and just I listened to the earlier presentations, and I just captured some quotations here that to me, I kept hearing, narrative again and again, just as a sort of a structural theme, if you like, in a lot of the talks that were across from, motor systems and physiological health and balance. Your life is composed of moment by moment interactions. Sounds like a story kind of thing. Reference are inherently ambiguous, etc., until they require context. So a lot of these quotes these quotes are drawn directly from content previously in the symposium that all, to me, speak to the value and the potential of cognitive narrative. Matt Brown spoke of an active synchronization, sustaining productive, adaptive, and evolving homeostasis. Well, CogNarr represents the similar kind of potential or possibility on a psychosocial, socioeconomic, and sociocultural kind of a plane. More quotes here. I didn't mean to read them all, but they're here to look at maybe CogNarr also, because of the subject matter, opens up onto answering this question about philosophers again being interested in and looking for new potentials here. So maybe it has served some kind of purpose there. More comments from the conversation earlier in the symposium that speak to cognitive narrative. And someone mentioned in one of the presentations this device, this Johari window for understanding people, relationships, themselves, and others, and what have you. And so, which multi-agent narratives are capable or indicative of expanding the transparency as a basis for trust. We want to interact with agents that we can trust. We want to create agents that we can trust. We want agents to trust other agents, et cetera, et cetera. That's a tall order. And we always underestimate how much nature has already done for us, in front of us and before us, and we never quite calculate or appreciate the lift involved in trying to do something that nature already did, like this kind of thing. And so for embodied agents, sort of the taxis of meaning plays out in and by situations. So these purple statements at the top, again, quotes directly from the symposium sessions earlier, and these statements, each one of them could be just as descriptive of narrative. So, agent life narratives comprise maybe like a lifetime of mortal computing. Mortal computing has come up a lot. There's ethical implications that seem to be woven into the mortal computing discussion, along with a lot of other considerations. But, maybe you can go even further and to instrumental or practical ethical considerations in AI, and the idea that an agent without a life narrative does not and cannot have identity, not in any way that people typically would consider accountable. And so just leave it here. Maybe there's parallels, another reference to previous symposium sessions when I saw some of these modeling efforts on NGC Learn, trying to deal with real neurons. Well, maybe part of the software engineering industrial benefit from CogNarr can be richer modeling languages, modeling elements, and methods, methodologies, and processes for real people, real stories, and therefore agents that are capable of trust.
Okay, sorry. So I just wanted to, this is more of like a use case for CogNarr. I'm mostly ignorant of the entire project, but anyway, this seems like a reasonable use case. So this project started out of the Backpack Consortium, which is intended to study chronic low back pain and classify various different patients into groups that might respond to various different therapies. So basically, what we do is we take their clinical trial data, which is about 2,000 variables or so, and we use language models to assemble that data into a narrative. We narrate that data. And of course, that story, that prose document that we show to the patient will then not read anything like what they would tell, a story they would tell about themselves, right? It's going to be anodyne, or it's going to have the character of whatever language model we use. But anyway, so we generate that thing, and then we have a semi-structured interview with the patient. We show this prose document to them. They read it and they react badly to it. And they say, this is not like me. It doesn't use the words I use, and blah, blah, blah. And then we take that transcript, we process that again with actually 11 different self-hosted language models. And we kind of come up with a new one. And then we have another meeting with them where they criticize that one. And so we do this 2 or 3 times. And finally, we get to a validated narrative that the patient actually says, this represents me. It represents my attitude. It represents the things I have to say about that. So the reason we're doing this is we have this working hypothesis that inside the human, there's latent information that our objective measures just don't capture, right? Even with survey data, the self-reported data, there's stuff that we just can't capture with those measures. And so the idea is that a person's story is going to capture this latent information better than anything some committee decides to try to measure on that patient. So that's why we're doing it. It's really for mechanistic knowledge, but it has a bunch of other potential uses as well. So now I'm going to show you a couple slides that I'm not going to talk about, but this is the workflow for data narration. This is how we take their 2,000 variables and come up with a story. Fine. And I want to mention knowledge graphs. We do similar things with corpus of documents, right? We write a paper, we have citations in it, and we put that all up into a big hairball. Of course, the idea is to reason over that hairball, and you can only reason over such things with algorithms. You can't really do it in any kind of human way. But the point I'm trying to get at here is this LPE story, the lived pain experience story, this narrative, and this knowledge graph are 2 kinds of the same thing, right? They're both these artifacts that are very static, and we don't want that. So the important part here is that it's clear that narrativity, a person's psychological narrativity, directly correlates with improved therapeutic outcomes, right? So they respond better to various different treatments if they can tell a story about themselves. And if you find like an episodic, less narrative person, you might be able to improve their ability to respond to a treatment by teaching them to be narrative about tell stories about, write in a journal, tell stories about yourself. And that might improve therapeutic outcome. And then the problem with that is that psychological narrativity is correlated with psychological rigidity. So you can get into kind of a canal structure, right? You get into a rut, and you tell that same story about yourself, like I have chronic low back pain and I can't walk a mile, right? And to get out of that it takes a kind of a heat, a disruption to get out of that. So part of the problem with things like knowledge graphs and ontologies and all those databases of any kind is that they're so static. And the same would be true of any kind of artifact that we derive from this protocol I described. We don't want that. What we want is these stories to be alive, or at least if the story itself is not alive, we want the story to be an actively improved living document, a high fidelity sign of life. So it should be obvious that this is a good candidate for a story graph or such things. So thanks.
I don't hear you anymore, John.
Now, can you hear me? Oh, good. Sorry. I was asking, Glenn, in your use case, the patient would be developing this narrative by himself or herself, or it would be facilitated with a practitioner who would be stepping them through it, or maybe even transcribing their story as it's told, or how does that work out in your setting?
So the patient lived experience story really is one artifact of a class of artifacts that you might have a message from the insurer to the patient, or from the insurer to the hospital, or from the clinician to the patient, as opposed to the patient to the clinician. So the idea is that these messages that are passed amongst this stakeholder graph, if you will, are co-constructed. They're not solely constructed by the source node of whatever message or whatever link they're passing along. They're co-constructed in a way. When we talk to a lived experience panel, like, individual patients, then obviously that's something they would generate by themselves. But in any other stakeholder to stakeholder communication, I think they should be co-constructed.
Right. No, this is a great this would be a great application of story graphs, I think. Daniel, I can't see the board, and I don't know if anyone has posted any comments or suggestions or anything. But if they have, we could address them now.
Yes, I will ask. Oh yeah, please, Tim, and then I'll ask any questions from live chat.
I think I forgot 2 slides, so I'll just throw them up briefly, if that's okay. Just yeah, I think maybe this one, I actually, because I skipped forward, I think, to point out the NCG Learn parallels. And this was sort of an important slide that brought together some of the modeling results being sought when I talked, because I kind of skipped over the connective tissue between these 2 bookends, so to speak. So this speaks then to what we might hope to achieve with agent system modeling that can operate on, with the resource that could be produced in a CogNarr setting. And this idea of fiction, else's ideas, to extend beyond what we're capable of, and maybe more rational, sometimes maybe seen as more capable, but actually not more capable in some instances. Things like philosophy. So Richard Rorty is someone who, in this book, reached out to the insights and sensibilities of great writers to try to ask where do we actually promote genuine sense of human solidarity. And so the question is, how will we write solidarity with among artificial agents into our story? And I had just had this one quote that was worth putting on the screen briefly from Richard Rorty, which speaks to the open-ended evolution of experience and the human phenome. And so being used to developing systems that think they know everything and can anticipate everything and are sort of for closed systems. Again, to the point earlier, we don't appreciate how much work nature does for us when we try to step in and help out. Well, we have to keep these things in mind. That's the idea. Yeah. Thanks. Sorry.
That quote is almost worth a full read, and then I can do any live chats, but I think that is a very salient thing to read, Tim, if you want.
You want me to read it?
Yeah.
Oh, it says the fear of scientism, of naturalism, of self-objectification, of being turned by too much knowledge into a thing rather than a person is the fear that all discourse will become normal discourse. That is, it is the fear that there will be objectively true or false answers to every question we ask, so that human worth will consist of knowing truths and human virtue will be merely justified true belief. This is frightening because it cuts off the possibility of something new under the sun, of human life as poetic rather than merely contemplative. But the dangers to abnormal discourse do not come from science or naturalistic philosophy. They come from the scarcity of food and from the secret police. Given leisures and libraries, the conversations which Plato began will not end in self-objectification, not because aspects of the world or of human beings escape being objects of scientific inquiry, but simply because free and leisured conversation generates abnormal discourse as the sparks fly upward. That's Richard Rorty, Philosophy in the Mirror of Nature, 1979, page 388.
Yes, I'm sort of struck there by the requirements for a computational story or knowledge graph system to have strong typing from like a computer science perspective and to be composable, flexible, all that kind of data operations. And then to what extent would that turn discourse into normal, like Rorty sort of fears, to make it a finite game and say, well, here's our vocabulary set, here's the combinatorics of discourse, or here's what's the allowable discourse. And then there's that spark that takes things out of the normal. And so how to have the story graph also be able to bring in new recompositions and new elements to reflect that open-endedness.
I'll just say I think that's what narrative does. Stories continue. We always make new stories. Stories are being created every day. People are living new stories every day. So CogNarr represents, if you like, that conduit into the real time, emergent, imminent. And so if we can connect to that, in the real generative source being the humans, and always stay attuned to that and not let the one occlude the other. Put it this way, without cognitive narrative, good luck.
One of the things that I've talked about a lot to John, and he's probably tired of it by this point, but it's the idea that any two stories can contradict each other, and that's fine, right? It has to be contradiction tolerant. Whatever structure we end up putting underneath the hood has to be contradiction tolerant.
Daniel?
Which I'll just say also is, sorry, John, it's that's the equivalent or parallel to something, one of the bullet points I put in there, which was scaling the global and the local and everything in between.
Daniel, I don't know if you can share my screen. Is that possible?
Yeah, I have it up.
And I'm sorry, I can't see it though. It says example use case group decision making. Is that correct? Yeah, okay. I just wanted to, this is sort of on the topic, but I wanted to show in the CogNarr system how deliberation might occur on some topic. So it would occur in a series of rounds, as we imagine it, where people would create their story about the situation. The system would assess the set of stories from a group and perhaps report on how similar they are, how different they are, the different elements that the stories contain, the different perspectives that are taken, from the different members of the group. And then those assessments and the stories would be shared with the whole group. So then I can see what Tim is thinking and I can see what Glen is thinking. And maybe on this particular topic, I like something that Tim said. And then if so, I might include that in my story graph now for the next round. And then this kind of circular rounds of editing and viewing and assessing would continue until some kind of ending point. Hopefully, the ending point being that we are starting to develop a shared understanding of what the situation is, and maybe perhaps also what we want to do. What kind of action should we take? But what I wanted to point out is that I'm free, as I had mentioned before about rich stories, I'm free to have a very different opinion from anyone else in the group. I might be far away from what other people are thinking, but my story graph is going to convey that information, and that information is then now part of the group narrative and doesn't disappear. So I may not agree with anyone else in the group, and I may think that, I may be looking at the situation from a very different angle, and that will be that my story will be part of the group narrative and would be available to the group in the future as maybe we look back of what was discussed and who was thinking what, and what did anyone predict what actually happened, or whatever the story is. There should be room in our narratives to convey, not just to convey the same thought over and over again, but to convey whatever a person's true beliefs are regarding some situation. And of course, those beliefs are dynamic. They change with time. As someone learns more, they may change their mind, maybe even greatly change their mind about how they're seeing the situation. So as Tim said, without narrative, good luck.
Awesome.
And you just spoke to the sort of almost sort of re-entrant, sort of composable, can't step in the same narrative twice, and the idea that there's stories within stories and stories about stories and hermeneutics or whatever. The whole, when I mention that, what I'm trying to just highlight is, how they speak about how we learn the language of different mediums. We learn the language of photography. At first they behaved one way and then they behaved a different way, because we all learned where photographs go and sort of how to smile at a picture or whatever. And then we learn the language of television, so the laugh track. We're not like, what the hell is that? We get the idea of what's going on there. So to some extent, I think what you're kind of speaking to is that we already know the language of narrative and stories. We're already equipped with a lot of the machinery that already does the work, the same way that when the earlier software and systems engineering model developers conceived of, from Aristotle or what have you, classes and objects being a more productive organizing concept for all this text of software and layers of translation, etc., so that we could actually make it a tractable process and deal with reliable and maintainable complex systems over long evolutions. We had to reach for that and invent those classes, objects, what have you. Narrative is simply, this is proposing that it can be the backbone of some of that, and it already comes with so many of the affordances that are already natural language to us, that John was just with ease saying, and everyone understood what he meant. And yet it was the complexity of what he said when he talked about the folding in and complexification of narrative within narrative, narrative about narrative, your narrative, my narrative, etc. It was so easy for us to talk about that, but the complexity that's embodied there is astounding.
I'll read a question from the live chat. So this is from Samuel Nerer, who wrote, "Hello, John. Amazing idea. I was just thinking if story graphs could be useful in research with more qualitative aspects, such as psychedelic experiences, dreams, consciousness in general, for example, to make better sense of such subjective experiences, convert it to something which can be better analyzed by standard statistical methods, or just strike a better balance between them. Just throwing the idea out there, let me know what you think."
No, that would be that might be the kind of story where cows do fly. It may be a story that is, if someone is relating their psychedelic experience, for example, the story may have very loose ties to what we kind of consider shared reality. And that is okay. That is, that is acceptable in the system, and that could be useful. Potentially that could be very useful as capturing the narrative of a patient who is experiencing this a very unusual life episode, and then having captured it in a meaningful way that the person can verify that, yes, that's what I was experiencing. This is a correct narrative, and that the computer can understand. So if you had a repository of these narratives, one could do all kinds of statistics on what were some common themes and what kind of transitions happened and what kind of psychological states were occurring, and all the rest. So it would be a great application, I think. Glen.
Yeah, there's currently, as we speak, there's the Psychedelic Lived Experience Symposium, Summit, they call it a summit, that's going on. And they're talking about things like the Mystical Experience Questionnaire, which is another one of those designed by committee survey things where they ask you and the patient would self-report what they saw, what kind of experience they had. And almost without exception, all of the people in the community are like, this doesn't really capture the mystical experience it's trying to capture. And so these stories that they tell, and that the psychedelic community is rich with fantastic stories. So that's to me, that's like the ideal community for this sort of thing.
Yeah. Also, I would like to just mention too, in the CogNarr setting, particularly in the CogNarr setting, one might ask the question, why would somebody want to go through the trouble of working with the system to tell their story? Because, it might be much easier in some other system where you just simply write out some paragraphs or episodes from your life, you write it down. Everyone's familiar with writing things down, or maybe you just speak it and that's it, you're done. It's just captured by voice. Why would somebody want to go through the trouble of kind of working with the system to kind of curate the story, to refine the story, to really convey this this low a story with low ambiguity? Well, the answer, I think, is, I would hope, is because people really want to tell their story. People want to tell their story in a way that their story can be heard. Their experience of life can be heard by others and makes a difference. So I suspect that if the CogNarr is the concept of CogNarr is, we're still at the very, very early stages. So, we're still even conceptually putting together how all of these pieces work and what are the exact elements, the mechanics of a story graph. We're still working on that. But one day, if this comes to fruition, I suspect that many people will want to tell their stories and be heard by a larger group, because our stories are important. Our stories are that's one of the central elements of social life, is conveying our story to others. So yeah, that would be the draw of CogNarr and the story graphs, is like, here's your chance to tell your story and have it be understood and heard by the larger group.
What are the directions for the project, John, for the end of the year or for 2026?
Well, the end of the year is very, very close. We are discussing, now what are the mechanics of a story graph? What are the elements in a story graph? And I don't want to say too much about that right now, because it's still in flux, and we might add or remove elements from it, shortly. But I will say that what we're considering right now is something that would a layered graph, multi-layered graph, and different layers in that graph might represent several different kinds of meaning representations. So I showed one image of a meaning representation earlier on in my slides. Discourse representation theory, meaning representation, and one layer in a story graph could be very similar to that, and then all the tools that work with that meaning representation might be useful. For example, logical forms and various types of logic could be logic programs could be used for that kind of meaning representation. But then there could be other layered meaning representations on top of that. For example, a meaning representation that's really aimed at narrative. There's people are working on ontologies for narrative. And so that could be another layer in the story graph. And there could be another layer perhaps for time evolution and the different types of time that can be conveyed in a narrative. So that's kind of how we're thinking now as kind of the next step, and hopefully I think our immediate goal is to just simply draw up by hand what a story graph might look like for a few simple stories, 5 or 10 sentence stories, to just get a handle on how we want to construct the story graph itself, the functionality of the story graph. And then once we kind of settle on what that is going to look like, then we can start to code up how that actually works, and how we'll probably have some use of a LLM in there to even just in some simple sense of an LLM might be used to say, I'm sorry, you used the word cat twice, in the sentence. Do you mean to use that word twice? Something like that. Yeah, so that's kind of the steps we're going through. We're still kind of conceptualizing what the mechanics of the story graph are, and then we will write up just some hand-drawn story graphs for some simple stories, and then we will start to look at how that is coded, in a more automated sense, and how a user might interact in a real, with a real text box, for example. And CogNarr, if it moves forward, we hope that it does, it will certainly move forward from starting very simple. Sometimes I call our first aims a stick figure CogNarr, just to get the very basic concept of what this is and what kind of interactions might occur. And then hopefully over time, if it matures, it will become more and more sophisticated and have more and more features as we go.
Awesome. I'll read a comment. If any of you have a thought, you can go for it. Love Evolve wrote, hearing more about story sharing, co-storying would be nice. Intentionally collaborative story graphing in creative art contexts.
That's a whole nother use case that we've not mentioned today, is how could these be used for creative writing, for example, or even who knows, game development or something like that. I would think that there would be possibilities there for sure. I will say this, in the CogNarr setting, as it's conceived, the group does not work on developing a single story graph. Rather, each individual in the group has their own belief model, and there may be strong overlaps between the belief models of different people. So as we've conceived it, CogNarr is not working on a single story graph, but rather everyone's story graph. But I think there could be still overlap there and possibilities for, one possibility would be witnessing how, the synthesis of story graphs of a group, what that looks like. And maybe that synthesis changes as the group evolves, as the story of the group evolves. Glen.
Yeah, the concept that comes to my mind is the exquisite corpse. I don't know if everybody's familiar with that, but you fold a paper into 3 parts, and one person draws on one part, the other person draws on another part, and all you have are the little edges of your drawing that hook. And so then that's all they see, and they draw something else. And so then you unfold the paper and you see the whole piece of art. So that's the kind of concept that I thought CogNarr might might apply to.
Yeah, and I'll just say it's not exactly art, but from a creative potential standpoint, intersecting with it, and also addressing Daniel's comment or question earlier in regard to the Rorty quote. It should be open to extension in the sort of phenomenal external reality, new devices, new people, new norms, new things, different cultures, what have you, sort of open to extension of bringing in and drawing in, new things, new language, new words, new terms, and also open to operational observation of emerging communicative elements or modes, and disclosing to us maybe things we didn't have words for, from the collective phenomenon that's emerging as in the content, so to speak. So we might discover there's realities of human stories and narrative and what have you that we actually didn't really notice or understand as fully as we could with the assistance of this. So it's open both sides.
Yeah, good, very good. And just to kind of touch on one of those elements, as we've conceived it, CogNarr, as I had mentioned, would have ontologies behind it, so there could be some kind of shared understanding of what the group is talking about. But those ontologies could be customized for a particular group. So maybe there's a particular group that's talking about, who knows, traffic, and maybe there's some technical terms related to traffic that the group wants to hold in common. Well, the group can have its its own private ontologies to ensure that the terms that they're using are understood within the group. And then, as Tim just mentioned, maybe those ontologies actually evolve over time as the group develops a different understandings of what certain terms mean, for example.
I just have to make a plug for that Rorty book that I highlighted, Contingency, Irony, and Solidarity, because he specifically extends that discussion of fiction as extending philosophy or offering resources to philosophy. He's specifically addressing private language mediating in society between private languages and public languages. So the private irony of anti-foundationalist living, and the public language of solidarity.
And science fiction sort of bridging both, or being a view from both sides, with our technological niche that's able to project and diffuse these different story relationships in ways that we couldn't have said it. I mean, not long ago, music had to be said live or played live. Then we had fixed recorded music. Now we're entering into possible infinite variation on the edge. So then the story is moving from the order of what was said into kind of what it always was, which is something that generates the linear sequence as told and as understood. So it's kind of like, with those first principles of cognitive science, what kinds of representations are going to help us do a lot of the things that I think you highlighted really well, Tim.
Yeah.
Thanks.
With the previous parts.
There,
sorry.
Very brief, but that's okay. Yeah, we hear you now.
You brought up a lot of good quotes from earlier, Tim, and I think that really helps connect a lot of the dots and about this layer of systems engineering and design for cognitive computing. Okay, any last comments from anyone?
I would just like to encourage anyone who has interest in any of this to say hello, reach out. We have bi-weekly meetings on CogNarr, and it would be great to hear from people who think maybe this could be useful in some sense with their projects or their interests. And at some point, we will be looking for stories too. We will be looking for example stories and maybe people who are willing to try creating a story in our, in our system. So all of that is yet to come.
And I guess the only other thing is, Philip, I really looking forward to learning from him, because I think some of the things he wanted to discuss got into sort of the mathematical information theories and what have you, that could underpin very powerful techniques for achieving really what are some core goals and benefits and features or capacities of CogNarr around sort of the the category theory, quantum, what have you, information theories that not something we can go into without him, but if you read those papers, you'll see a whole section of information that really was only scratched on the surface here when John talked about some of the technical approaches, but there's a really exciting, rich kind of substrate of theory that has not even been brought close to this.
Thank you, everybody, for joining us.
Awesome. Thank you all. Bye. We're back with the final of the live presenters, embodied presenters, appropriately, with Adam Safron. And Adam will present for a little bit and take any live chat questions. And then we will play a sequence of pre-recorded videos from a set of other colleagues, which you can kind of contextualize, Adam. So thank you to you for the presentation.
Thank you, Daniel. So, hello, everyone. I'm Adam Safron. I am currently a research scientist at the Allen Discovery Center at Tufts University, working with Michael Lennon. And today I will be describing an ongoing and evolving collaboration with different friends and colleagues in the active inference community and beyond, centered on basically an AI alignment research program, which is centered on an integrated simulation environment under development called Common Grounds. And I'm going to describe some different aspects of what we've been discussing and my own views on this and some promising future directions, and providing an introduction to a series of pre-recorded lectures from my collaborators and friends that will follow, going into the details of different lines of thinking that are coming together as part of a broader research program. So I know that's a lot, but let's just dive in. So I've been interested in AI and AI alignment for, I guess, maybe 25 years now, since I read The Singularity is Near a very long time ago, 25 years ago. And since then, I've been thinking, what would it take to recapitulate the principles of biological intelligence in AI? Is this something that we will ever see in our lifetimes? And what would that mean? And if such systems were created, how might they be aligned to be compatible with human values? And what can we do to help promote alignment? And so towards this end, I've been pursuing this in a number of ways. It's, I'd say most of my academic career was in the background motivated by these interests and concerns and hopes. And in recent years, I've been working with others to basically develop an interdisciplinary research program for biologically inspired AI and alignment. And what in this symposium, I'll be discussing I guess the current state of play of this in terms of ongoing conversations with some of the core members of the active inference community and beyond, where we're planning to do research in a research program centered on a integrative simulation environment called Common Grounds. We're currently, so the hope would be to basically create like a ongoing support for a cohort of active inference research fellows who could both pursue their work independently and in communication with one another, coordinating around testing out their ideas in this common simulation platform for multi-agent alignment. One of the key interests for this research program would involve things like biologically inspired architectures for agent design, having agents that are active inference agents that are embodied and embedded in environments that they interact with in rich ways where they can construct and co-construct their niches, where these environments are open-ended and allow for lifelong learning and meta-learning. And where within these, among the things that would be meta-learned would be coming into pro-social equilibria and acquiring pro-social preferences or policies that will tend towards cooperation, even under circumstances where on occasion defection might seem to be incentivized. Can we create learning curricula for developing harmonious social interactions and robustly pro-social agents? And then finally, in addition to demonstrating these principles in silico, in simulation, through mathematical modeling, can we come up with formalizations and something like guarantees or proofs regarding alignment via mathematical modeling? So I realize that's a lot and very ambitious, but thankfully I am working I'm grateful to be working with some very brilliant people who I think, if we keep going, we can make substantial headway towards these ends. So in the videos that will follow in this symposium, there will be an initial lecture by Nick Hay, my longtime friend and collaborator, who is the designer of the Common Ground simulation environment. He's everyone's quite brilliant and wonderful. He got his PhD with Stuart Russell, studying meta reasoning, and went on to study robotics, or to work with robotics at Vicarious, and is now dedicated to pursuing this line of research and developing a simulation environment that he will describe. Alex will present on ways in which the simulation environment can be used to demonstrate some of the principles of active inference, the foundational principles, including the natures of agency and value from an active inference perspective. David Hyland will discuss how such an environment can be used for demonstrating alignment of multiple agents who each, rather than thinking of AI alignment in terms of things like the major companies developing monolithic superintelligences, rather, what would a world look like where you had an ecosystem of intelligences that were more restricted in their scope, still quite powerful, but not necessarily super intelligent. Within such a world, what would alignment look like with an ecosystem of evolving, interacting intelligences? David also has a co-presentation with Mao, and Mao will be describing work on something called path flexibility and the ways in which this promotes resilience. Or when an agent acquires challenges, can it come back into consistent behavior and harmonious relations? Dalton will describe work on the formal modeling of alignment, specifically discussing ways in which you can model the development of an agent in its preferences and its value and its action, where the free energy landscape that it follows, the value function or the value landscape governing its behavior becoming canalized, or where you develop deep pullback attractors for self-stabilizing value regimes. I've, in my own work, called these value cores, and in Dalton's work with things like path formalisms and free energy, and gauge theoretic interpretations of the free energy principle, you can even describe these as singularities within free energy landscapes. That's a lot, but I'll leave it to Dalton to go into those details. Zara Shipahi, who I've been working with a number of years, where she's been teaching me about principles of machine learning, and I've been trying to teach her what I think I know about systems neuroscience. She's been developing really impressive biologically inspired architectures for flexible intelligences that could be deployed in various alignment protocols that are themselves biologically inspired and realistic. And then Honju in her symposium presentation will be discussing artificial consciousness, the nature of affect and its roles in alignment, and even how principles of adult development and psychological maturity, as she calls it, can be used for developing models of what robust alignment might look like down the road. In this presentation, I will describe in addition to providing a little bit more overview, I'll describe some of my own vision. My background in affective neuroscience, where the ways in which I think biology gives us guides both to the nature of how we might develop advanced intelligence, and not just advanced intelligence, but alignable intelligence. The notable thing about biological intelligence is that we are basically existence proofs that both something like AGI is possible, because we are very general, and alignable AGI is possible because biological agents and human beings can be robustly pro-social. They can be stably benevolent, even under conditions where it seems like this ought not be expected. And so can we basically reverse engineer benevolence and recreate this in artificial systems, or use this as a guide? And so this is some of the, there's other friends and colleagues who have been in discussion and who will likely be involved in this research who are not part of this presentation. But in addition to them, question would be for anyone listening, if you're interested in this kind of research program, please get in contact with me, and potentially can find ways of collaborating. Across these presentations, the goal is to show different lines of thought on alignment and active inference that can potentially fruitfully intersect. And I think there's a whole greater than the sum of its parts here, and maybe your work is part of this whole. And a whole towards what? Well, basically the whole towards what would it take to develop artificial intelligences that have the properties of biological intelligence in terms of their power and flexibility, and also their alignment. So common grounds. Nick will go into more details on this, but in brief, it is an artificial life-inspired simulation platform that allows one to deploy and simulate richly embodied agents at scale, where this rich embodiment can include things like complex internal states, respiratory dynamics, digestion, metabolism, vulnerable embodiments where there's that need to be protected and maintained as they interact with environments, and where the body itself is part of the intelligence and valuing, where some of the, just as exists in nature, a lot of the intelligence of natural minds is actually in the embodiment itself. The way bodies are designed can be thought of, allows for many fruitful properties that help to scaffold minds and enhance their power. In this environment, there is realistic and interesting physics, which allows for things like niche construction, which both in learning to navigate those is of interest for places where things like active inference can potentially demonstrate its value, for having systems more skillfully interact with these complex environments. But also the environments allow for, as I mentioned before, basically niche construction and co-niche construction as structure is built up and modified as agents interact, and in the process come into various forms of cooperative or competitive interactions. There are other approaches to multi-agent alignment using simulations such as metagrid, and the common grounds environment can be viewed as complementary with these, and that while an environment like metagrid allows for maximal scale of simulation, common grounds allows for simulations which are scalable, but more detailed in terms of what can be modeled at the level of the individual agent, in terms of the agent having a rich embodiment that embeds it in its, or rather a rich embodiment that embeds it in its environment. And part of like the richness of these embodiments could include things like bouncy and rhythmic dynamics and soft morphologies of a kind you see in biological systems. And as I'll discuss in a little bit, I actually think rhythmicity, and others have think this as well, might be actually quite important for understanding the natures both of the way in which bodies are controlled in their rhythmic character with rhythmic nervous systems, but also how shared rhythms can be part of the way in which agents can be aligned with one another. And finally, for common grounds, it's the intention is for it to be something that allows for gamification, where people can engage in basically an enjoyable activity of modifying the agents and their interaction with the world and interacting with them such that you can promote their alignments. So Nick is trying to make it fun and enjoyable and relatable for people to interact with artificial agents in a virtual world and see if they can help promote their alignment and their prosociality. So that's a brief common grounds, and then we'll go into more details. And so now I'll discuss some of my own interests briefly before opening for questions, and then we can people can see these other videos, because these are extremely sophisticated thinkers, and I'm not going to be able to do justice to their ideas. They should speak for themselves. So in my own work, I find common grounds to be very interesting because of come to a view which I've tried to express in a number of publications, that embodiment is fundamental for minds. And I think this is a view that's common within the active inference community and particularly appreciated. And so I'll sometimes say that, and others have said that, the body is a prior, and that the body allows for, in the process of minds bootstrapping themselves into increasing degrees of sophistication, bodies provide particularly important toeholds in this bootstrapping process as an agent engages in structure learning and complexifies its models of self and world. And so part of the reason I think bodies are so important is because I think they provide a learning curriculum that has many desirable properties for learnability and for this bootstrapping process. So if you think of, for instance, like an agent of an infant observing its own hand, as opposed to, for instance, like in contrast, let's say, like a deep learning system doing vision by looking at a pixel array from a world it never interacts with. In this case, the thing to think of is an infant learning its own hand as a kind of prototypical object and causal system. And so this hand is basically always there and present for being observed and learned. It can have action-driven perception, where by moving it around, you could resolve your ambiguity, and where the movement itself will generate corollary discharges or efference copies, which themselves can be thought of as a kind of cross-modal prior. And respect to cross-modal priors are the sensors around the hand, through the proprioception and the tactile and the warmth. You're having many correlated data streams, and the visual appearance, and maybe the sound, even the smell, taste. You have converging multimodal inputs, which each can serve as constraining priors for one another, so further helping with learnability. The bodies interact with themselves, a further source of mutually constraining inferences. There's affective or salience. It feels like something to have a hand and move it around. And so this salience will be part of why this information will be attended to and will help to structure learning. And where the hand itself, because of its morphological properties and what it affords, allows basically perception to be structured according to affordances, things like manipulability, reachability. And then finally, thing about biological embodiments is they're designed, or they're structured such that they're remarkably learnable or controllable. If you think of something like like a hand, the way the joint angles work, it grips naturally by its morphology, or the way in which the shoulder joint has a limited range of motion. Rolf Pfeiffer has described, like, for instance, like this itself is useful where if you're reaching out in front of you and not in back of you, the things you reach and you grab are naturally brought up to also be seen. And so things like hand-eye coordination. So I think bodies are fundamental in the process of bootstrapping minds and developing basically rich causal models, and where this bootstrapping is remarkably efficient. Doesn't require, even though there is a lot of experience for biological learners, you don't have to necessarily, biological learners are remarkable in how efficiently they can learn and how much they can learn from so little. So this is part of the reason that I have interest in common grounds, is I think can be used to demonstrate such principles by providing agents with interestingly rich embodiments, which can be part of their learning process. I've also suggested that embodiment is also important for alignment, and others have as well, in terms of shared rhythms, where rhythmic activities are potentially special for the ways in which they can entrain neural dynamics and attention, and through positive feedback between entrainment and attention, how rhythms can allow for intense focus on those rhythms. And where at their limit, they can lead to various states of mind where through this intense focus, agents can experience both deep affective states and even things like self-transcendent states, as you might describe in terms of flow, where the intense engagement with the rhythm allows for some self-processes to be downregulated, potentially allowing for an openness to the environment and to others, and maybe in particular others who you are also sharing rhythms with. So I think this is, if you think of the conditions for bonding in animals, particularly mammals, but not just, you'll have things like mating song and dance and the mating act itself, where engaging in shared rhythmic activities, or in humans, things, also birds, but humans, things like music and dance. These are, or another context like in militaries, people marching together. Basically, shared rhythms seem to be an important part of co-selfing, or developing a shared interest with others. So finally, or not quite finally, among the things that I think would be important to simulate, and what we're looking for in alignment, is something like the development of robust preferences, something like orientations. And so some of my own work in affective neuroscience and the nature of preferences and motivations, I've described how basically you can arrive at something like robust self-sustaining preferences or orientations as pullback attractors through iterative action selection and reinforcement learning, or in active inference terms, iterated policy selection and updating of priors, where the idea is that if an agent as it's in the world engages in selecting different policies for what it thinks will be more or less likely to realize value or minimize its expected free energy, you then this then results in updating of your policies based on how well things worked or not in terms of their likelihood of deployment, which then influences what the agent does, resulting in likely patterns of behavior, further going to those areas of value space, further engaging those behaviors where even more model evidence can be achieved. So the idea is you learn this is what works, this tends to be good, and you begin to learn this, you select actions that would be consistent with this, and then you can acquire further evidence in this way. And if this happens within sensitive periods of development, even if not, you can get this like critical mass of model evidence where you have a pullback attractor where this is just a robust model or paradigm of this is what I ought to do. And it's self-stabilizing. The agent doesn't think to try other things because what is overlearned to be valuable or is overlearned, and so becomes robust. So in terms of this idea of like developing and so on Dalton's talk, we'll get into details of actually how this potentially could be formally modeled in terms of the canalization of free energy landscapes. So, but what is it that we would want to canalize? What values do we want to select and make robust? So things like mutual care, tendencies towards cooperation. Some people discuss this idea of like an infinite game, or ways of being in the world relating to others that allows one to continue to cooperate and coordinate over time and co-realize value. Can we, through this, come up with models of and formal models, even of what we mean of seemingly ethereal and fuzzy concepts like love? Like, could we model love as the co-empowerment of agents and use formal frameworks like empowerment to actually describe mutual care? others like Rutger Golkupas have suggested also that within active inference, you can get views of moral orientation of a quasi-Kantian variety, in that if an agent is pursuing policies in the future that require deep temporal sequences to be realized, this will tend to necessitate cooperation with others. Like for a value to be realized and for an agent to be able to predict itself realizing value, it must be able to, under optimal circumstances an agent is likely to learn that this is more likely to be achieved via cooperation, that actually the selfish thing to do is to cooperate. This also relates to some of, I'd say, Mike Levin's work in terms of light cones of care, and David and Mao will discuss some of that also. And so finally, Zara and some of the architecture she's describing and some of the ways she's hoping to deploy them connect to some proposals from AI alignment of how you can have protocols for alignments from people like Stuart Russell and others for cooperative inverse reinforcement learning, or having agents basically learn to optimize for the preferences of others, to basically develop things like joint intentionality, as someone like Tomasello would call it, where agents learn to have shared or common goals. And then finally, as I was mentioning earlier, in terms of the case of shared rhythms, I think looking towards the mechanisms of the ways animals bond, or attachment as it occurs in mammals, this can potentially give us a guide to understanding the nature of alignment in biological agents and potentially artificial agents that work by similar principles. And then, well, definitely more finally, and both speaking to Zara's talk and Hanju's symposium, there might even be an importance of things like artificial consciousness, depending on how we mean it, in terms of having different senses of theory of mind, or mentalizing, or being able to understand the mental states and experiences of others by reference to your own experience. So that was a lot, and there's even more, but I will leave it to my friends and colleagues to describe their work. And if you have interest in getting involved with such a research program, and want to know more about what we're planning, please get in contact with me. I and the team would be grateful to talk to you about what we might be able to do together, and I'm grateful for any suggestions you might have. So thank you so much for your time and attention, and I will take questions.
Thank you, Adam. Okay, I'll read questions from the live chat, and then we'll play the videos from the mentioned people. Okay. Mundane Bloke wrote, "What are the infinite games about?"
So there is a book called Infinite Games, and it's contrasting them with, so like finite games would be something like a tit for tat situation, or like a prisoner's dilemma situation, where something like Stag Hunt, but basically games from economics, where the equilibria, the Nash, or the what's incentivized, depending on the context, might be either cooperate or defect. The idea of an infinite game is, how can an agent how can you show up in a way that allows the process of playing games to keep going? Games that don't terminate, where you just realize value as a one-off, because in one-offs the Nash equilibrium is oftentimes the effect, but rather games where by continuing to cooperate, you can continue to get non-zero sum setups and mutually beneficial interactions where everyone comes out ahead and people become basically co-empowered or can realize value more effectively by helping each other to realize value. So how can, if it's an infinite game, the idea is you play the game such that you will keep playing with each other and keep wanting to cooperate and co-realize value, as opposed to more narrowly trying to achieve a win, but then have this be at the expense of the possibility of future cooperation. So this idea of an infinite game is, in some ways, could be viewed as a kind of, I guess, moral realism, and that the idea would be that an ethics of, or a kind of moral of cooperation and other concern might actually be a selfish thing also. That this could be thought of as a kind of convergent instrumental value. If you want to be if you want to be most likely to be empowered into the future, configuring yourself and your policies you're likely to select, making those cooperative might be the best way of minimizing your expected free energy or realizing value into the future. I don't know if that explained it, but that's roughly the idea as I understand it.
Awesome. And several of the team members applaud you in the live chat. So if you have any other comments, feel free. Otherwise, I will then go to play the Common Grounds videos and then the last few videos. Any final comments, Adam? Go for it. Otherwise, thank you.
No, just thanks so much for providing this platform and for I should have actually mentioned you in terms of we've been in communication with you about what has been done and what we're planning, and to what degree that within an active inference is what we're doing, the ways it can intersect with other ongoing efforts like Metagrid, and basically grateful to be in the symposium now and to be thinking about these things with you, and thank you.
Thank you, Adam. I'll ask one final thought-provoking question from Obadax. Adam, would you be able to emphasize the dichotomy of it all?
The dichotomy of it all.
I don't know if they're trying to break you out of your non-dual frame.
So you can think of, there are actually among approaches to alignment, there's interesting suggestions that actually the world's wisdom traditions and contemplative traditions, such as found in Buddhism and other worldviews, could potentially be guides to something like alignment and even superalignment. That overcoming dichotomous thinking or self-other distinction might actually be one of the things we're looking for in aligning minds, and one of the ways in which minds like ours, when they're aligned, they're successfully aligned. I think there's a lot of merit to this, and this is, I think, present in some of the thinking I've described in terms of ways in which, for instance, rhythmic activities can potentially, and shared rhythms can allow for basically self-transcendence as part of alignment. But I would also suggest that there are other ways of thinking about alignment that don't necessarily involve beforehand dissolving dichotomies. So for instance, the nature of compassion could be thought of, you potentially arrive at it by having some sort of like oceanic state of non-difference from the world and others. But you can also arrive at it as you just learn that when you're good to others, they're more likely to be good to you, and that potentially the most selfish thing you could do is to love others. And so instead of initially arriving at this sort of transcendence of dichotomy between self and other and world up front, maybe it comes afterwards from a process of just learning what works or what tends to work for making you feel good, for when you interact with others in the world. So that was an attempt at addressing dichotomousness and how it can play into alignment or not.
The more open the question, the better. Okay, thank you, Adam. I will now play 1, 2, 3, 4, 5, 6, 7 videos. It'll be a septuple header coming right up. So, thank you, Adam. Bye.
Thank you.
All right, here come the pre-recorded videos related to Common Grounds. First is going to be the video by Nick Hay. It is a 15-minute video. Here we go.
So I'm going to describe the Common Grounds project in general terms. Adam and others will connect it in more particularly to. So I'm going to describe the Common Grounds project in general terms. Adam and others will connect it in more particularly to active inference. So the general goal of this project is to build an artificial life simulator, which is designed to simultaneously support several things at once. First, building virtual worlds, games, that can be used to bridge humans and AIs through play rather than work or other things like that. It's important. And secondly, developing a new range of benchmarks for studying within this sort of playful artificial life context, the social and cultural effects of bringing AIs into the mix. And then third and more broadly is supporting research and nurturing developing benevolent embodied AI and all the different ways we might try to do that. So the simulation and benchmarks will be released open source to maximize the ability to do good research, and there'll in parallel be a game demo and the same simulator released on the web and on gaming platform Steam to sort of just test the waters to see if this is an engaging and interesting thing for people. And then basically the idea of the project is to iterate and improve on all of these three things: the broad simulation, the benchmarks, and then the game. So I'm going to talk about the artificial life simulator, the world, the nature of the bodies of the creatures in it, and their embodiment, and then several sort of directions you could take it in more of a morphogenic developmental direction or evolutionary direction, or multi-scale life, and touching a little bit on the 2D versus 3D question, and ending with a demo. So here's some concept art depicting the world and the creatures in it, and the sort of kinds of things that are going on. We have here we have one creature investigating this tree here, which has got a little worm on it. Over here we've got some obstacles, a ball that's come and blocked their little houses here, which they've built for themselves. And then these two creatures are trying to remove it. This one is just kind of chilling and not being very helpful. So there's various kinds of coordination and cooperation problems that very naturally emerge. here's someone exploring the cave, maybe trying to find some resources, and then I don't know what this one's doing. It's sort of staring at some crystals. And when it comes to nighttime, so think of this as sort of like a 2D physics-based Minecraft, then or kind of world like this. Then here, all these creatures have gone into their homes with some nice warm fire, and then yeah, they're he's still up there. So one can build worlds in the simulator that have different granularity scales relating how the environment that can be modified by the creatures in it and the creatures themselves relate. So here's sort of like a kind of intermediate, or here's a scale where the parts of the world are quite large compared to the agent. Now here's one where they're quite small. So this is sort of like the world is a bit more like mass-like than sort of discrete atomic pieces, and here sort of kind of a middle ground. So one could choose the level of granularity that makes the most sense for the kinds of things you're trying to study. So a major motivation of this work is being able to have a credible but simplified form of embodiment, and in particular wanting to have analogs of all of the senses, some sort of simplified form. So here we have kind of something depicting here's sort of a scene with from before zoomed in with the creature holding a part of this plant, the little worms up there eating some fruit, and it's sort of depicting a picture of their internal state. So for each piece of them, maybe there's energy levels, there's some sense of temperature, potential for damage, nutrients. There could be internal organ states. There could be various forms of visceromotor and interoceptive control, hormones. This is sort of like, and then we also have things like proprioception, sensing the configuration of the body, the angles of the joints, forces being put on it, and dually motor control, like the ability to control the desired pose and posture of various body parts, and stiffness. It's also touch that comes from interacting and colliding with the environment. That's sensed on the different parts of the body. There could be smell, which is in this kind of mesoscopic range corresponds to something like a sense of the quality of the environment around the creature, which could just be like a weighted integral of the kinds of materials that surround them. So vision works quite naturally. You can imagine it as sort of a ray casting thing where you can sense the distance and material along different directions. One can add arbitrary amounts of noise or not have distance be directly observed and so forth. This, you can kind of visualize it in first person. Looks like kind of a Wolfenstein 3D on its side. But here you can sort of see this part here is corresponds to observing the hand. Here's the part of this tree they're holding on right there. Here's some distant ground, and there are some other balls right there. And then finally, sound, which is generated by interaction with the world and collisions and so forth. And there's various natural ways to represent that. So maybe here, the creature's hearing some sounds coming from touching and manipulating this thing here, but then also simultaneously hearing some munching from up there. So this form of embodiment is rich enough to represent pretty comprehensive range of senses. So as another thing, this is sort of, the simulator generally is a fairly flexible particle-based system. And so one thing you can look into is exploring development and evolution of creatures, starting from simpler things, which perhaps bud off other cells that are connected to each other and communicate with each other, and possibly even have a more biochemical sense of how the motor control works. So another thing you can explore is intelligence acting on multiple scales. So here we have two creatures synchronously trying to carry an object that's too heavy for one of them. And one can go out from there to consider the behaviors of groups, cooperating groups of creatures, and then one can go in and consider the creatures themselves being made of cells that are cooperating, and further those cells as being made of molecules that are cooperating to achieve certain homeostatic ends. You can imagine sort of literally simulating various biochemical processes in like a kind of balls bouncing around and having chemical reactions. So for example, here's a picture of a food particle absorbing into the cell and then interacting with various of these different kinds of molecules inside. So a question I often get is, why 2 dimensions? Why not 3 dimensions? The main reason is 2 dimensions seems rich enough to support a very rich embodiment, and is quite a lot simpler to deal with, easier to visualize, computationally cheaper, so you can get more done for the same amount of compute. There are properties of 3-dimensional space that 2 dimensions doesn't have, but I think a lot of these are good enough 2D approximations, especially if you have 2D on its side with gravity. So I don't want to argue for 2D too strongly, because there's a natural 3D world that's analogous with 3D balls instead of 2D balls, basically, and would be a natural transfer domain for showing things that maybe have been developed in 2D, then showing that they still continue into 3 dimensions. So I'm going to demonstrate some features of the simulator from the inside out. So this visualization shows what 2 creatures are feeling, in a sense. So the line segments connect their bodies and are colored based on how stretched they are, and the green segments show where touch is occurring. So at the bottom you see the feet touching the ground, and here, yes, you can see some contact between the joints of the body on the arm. And so this is a frozen tableau of a creature reaching for fruit there in a larger scene with kind of a worm. And this is in a kind of fully modifiable world. You can there's this crystalline structure of tiles you can pick up and move, and they follow gravity, and they influence each other, and can be used to build up structures in the environment, like kind of homes and some such, and can also be the sources of resources. So this sort of can be kind of a ecological system in here, where maybe this pink resource is needed for as one kind of food that's there, and they have to go into the mines to find things. So there are various ways of interacting with this world to demonstrate things. You can create moving particles, which will do things to the world, and particularly you can play around with the destructive forces of very large objects. So this shows a worm being piloted, and the controls are modifying sort of the shape of the creature, and it is trying to reach those little fruit berries on the tree and knock them off, sort of demonstrating part of what could be the life cycle of this sort of creature. And this is sort of a zoomed-in view, again, showing the body sensors of stretches and touch on along the worm's body. So this next part shows how visceral the world can be when you have a body which can be pinned down and stretched and deformed by other parts and potentially injured. And so there's sort of a very core source of value and motivation that comes from preserving the integrity of your body and protecting it and helping others that are having some trouble there. This part is more fun. This is showing the emergent physical properties you get, or the material properties you get from having particles that have different kinds of interaction. In this case, the particles adhere to each other. So you get sort of something which is feels a little bit like a metal or some kind of magnet ball structure, and has properties of deformability and malleability, forgeability, and so by varying the basic interactions between the particles, can create a wide variety of a very rich set of kind of possible situations. And this includes also being able to specify, you can see some on the right, some of the material properties of the objects. And this includes things like reactions where particles of certain materials will connect and collide and then form other particles like that.
Hi, this is Alex Kiefer. Thanks. Hi, this is Alex Kiefer. Thanks to Adam for inviting me to this mini panel or symposium on the Common Grounds project, which I think is very interesting for modeling some of the things that I'd like to model and do some experiments on related to agency and alignment and so on. So I wanted to start out by sort of framing why I think this environment's interesting. So grid worlds actually are fairly interesting in themselves. So you can use a grid world, by which I don't mean necessarily like a literal grid, but just a simple simulation with some discrete states. You can use these to model a number of things in fruitful ways. So obviously, like even in a literal grid like this, you encode basic spatial relationships. You can have simple to moderately complex, tasks that agents can execute. You can run batches of agents that you can vary in various ways. And importantly, you can control the conditions of experiments in a pretty easy way because things are fairly simple. And you can also examine the results. So these are interpretable models in part because of their simplicity. Although, not all of the behaviors you get out of these models are simple. So in fact, like cellular automata, you could argue they're not exactly usually thought of as grid worlds, but with a fairly simple set of rules and a grid-like setup, you can get some interesting emergent behavior. But generally, grid worlds are good for like coarse-grained, interpretable models of how agents interact with their environments and with other agents. And then on sort of the other side of the spectrum, you have full-on like 3D game engine type physics simulations. And these are interesting, obviously, if you just want to see like how, drop a car from 30 feet and see what happens, or, more usefully, if you have a robot and you want to figure out like, you're trying to build a model of how fine-grained spatial manipulation and control works, then these types of environments are great for that. But of course, they're fairly heavy computationally, and they certainly don't abstract from irrelevant detail in a lot of cases. Depends on your use case. But they're great for like realistic models of interactions with the realistic world. So one way of framing what I think is cool about Common Grounds is that it's sort of a middle ground between these approaches. And I also see it as in particular, it's like a very good fit with like the niche of research that I want to do on, you might say, the sort of psychophysical aspects of agency, which I think are suitable for studying in like an artificial life type of environment in which you have. So I guess the main salient feature of this kind of simulation is that the agents have bodies, not just in like a nominal sense that like they have some properties that you keep track of in some arrays, but they actually have there is a it's a physical spatial environment, and the internal structure of the agent, or at any rate the structure of the agent, and including its internal structure potentially, is modeled in the same way as the environment. So here you've got sort of like a cool hexagonal type of grid made of spheres. I mean, I'm not making claims in fine detail about how Common Grounds works, but this image depicts something like that. And the body of this worm-like thing here is made up of the same types of stuff you'd see in the environment. So I think this idea of there's a lot of ways of looking at why embodiment is important, but one reason it's important is just because the structure of the agent is continuous with, and it's a part of like this. I mean, that's true in a full-on 3D physics simulation as well, but here things are still kept simple enough that you have discrete elements you can play with, and a fairly small number of knobs you can turn. But I'm particularly interested in this from the point of view of like basic research on things like agency and policy selection, because you can model how internal like mental or cognitive structures are physically realized. So we often talk about like mental action. So that suggests that there's like really an internal mechanism that performs an action kind of in a similar way to how you might perform an action on the external environment, except it's internal. And I think that's the kind of thing that you might be able to model in this paradigm. So generally the physical foundations of agency. So zooming in a bit on some of these ideas, you could use this kind of simulation environment to model preferences, for example, of agents, or homeostatic set points as actual attractors in an internal dynamical system. And I think for some purposes, it's fine to just specify them as like a C vector, as a list of numbers, but you might get really interesting things. And I'm certainly interested in particular aspects of how it would inform your models of agency if you explicitly model those things as attractors, which of course in the bigger picture, in the background story of the free energy principle and so on, that's what they're meant to be. You could also, and this is probably one of the things I'm most excited about, is that you could model the physical realization of mental or psychological structures. Things like perception, percepts, beliefs, mechanisms for policy selection. So in this kind of environment, you could literally build like an internal machine that executes some task like policy selection, for example, or belief updating. And then once you had that machine, if you also set some physical parameters and tied them to the way that these atoms in this universe bounce around, then you could, so you could look, for example, at how the conservation of energy, physical energy, impacts belief updating and policy selection. Sorry for the kind of ridiculous illustration here, but I rolled with it. So another theme here that I think is important, this is almost the end, is a short talk, is this idea of cross-scale composition. So you could take that in a purely physical sense, like agents are built out of physical things that are built out of other physical things, but a more adventurous avenue might be to explore how agents are composed out of micro agents. And there's some really interesting work already showing, for example, that like the phase locked decisions of micro agents can sort of lead to emergent behaviors at the macro level. And I think that's an important principle for understanding. So I use the term inner alignment on this slide. I realize that has a narrow meaning in like AI safety literature, sort of about ensuring that agents learn internal, mesa optimizers, or they sort of ensuring that the results of their meta learning remain consistent with the goals that the designer of the agent had for them, or the objective function that was explicitly specified. So I think more broadly, though, you can think of this as inner alignment is sort of a matter of just being able to what internal control structures are necessary in order to enable agents to have goals, goals that they really own, not just targets that are sort of imposed from without, but like actual goals that they adopt. And to my mind, making progress on that requires understanding something about the internal organization of the agents and how it relates to their behavior. So I've argued that this is important for understanding that the differences potentially between digitally simulated agents and biologically realized ones, but whether you agree with that or not, certainly these principles of cross-scale composition might be interesting for understanding how value and desire and things operate in living agents. So thanks for including me in this discussion. These are just some papers I've worked on that are in this kind of space, but importantly, a lot of them don't have much modeling work associated with them yet, and it's not easy to create an environment like this. So I really I do hope to see Common Grounds become like a really cool, useful tool in this space. Thanks.
Hi, I'm David, and I'm going to talk briefly about bounded rationality and multi-agent alignment. So to begin with some motivation, a lot of focus in alignment research is centered on this question of how do we align a single, potentially superhuman level AI with humans or humanity. The big issue here, aside from how we define these things, is that there is no agreed upon solution to this problem, and it seems like a very difficult one in general. On the other hand, a lot of focus in capabilities research centered on the question of how we build a single superhuman level AI system. The reality is that for such systems, there are significant trade-offs between performance and cost. Moreover, AI agents are increasingly being deployed on the internet to carry out tasks autonomously over longer and longer horizons. Fundamentally, we existed and are building towards a multipolar world, which is an ecosystem of many AIs, humans, and organizations all interacting with each other. And so a central question here is how do we ensure that this ecosystem is aligned, beneficial, efficient, and resilient? The hypothesis I want to explore here is that we start from the fact that a major source of risk from advanced AI comes from this extreme uninterruptible optimization towards specific goals. Now, if a significant proportion of the AI agents in this ecosystem are highly capable, have access to significant amounts of resources, and are insufficiently aligned, this could create destabilizing, undesirable outcomes. And so perhaps complementary to working on alignment, maybe we should also think about limiting capabilities and resources within such ecosystems until and as we progress with alignment. So what could this lead to? Well, one of our essential hypotheses is that this could lead to an ecosystem of specialized, efficient, and reliable agents all working together alongside humans to solve problems, much in the same way as we would see organizations or societies do. So how might we reason about such systems? Well, one concept that we propose that's potentially useful is that of bounded rationality. So what is bounded rationality? Well, the fundamental idea here is that real-world decision-making is subject to limitations. These limitations can come in the form of limited time, energy, money, computational resources, attention, memory, information, etc. And crucially, decision-making needs to take these factors into account if it is to be effective in the real world. Now, bounded rationality was originally intended as a descriptive model of human decision-making, and then was later expanded to encompass both biological and artificial decision makers, as well as to bridge the gap between both normative and descriptive theories of decision-making. The key mechanism here is that of satisficing, which is related to finding the optimal solution in a simplified model, or finding a good enough solution in a more realistic model. And we see these kinds of trade-offs manifest in the modern day in the form of cost-performance trade-offs, especially with the rise of test time inference. So here we see several graphs from major AI companies, researchers, and also public benchmarks that are increasingly focused on the trade-off between performance on a certain task or benchmark and the costs in terms of test time or training time compute, or in terms of dollars for inference, etc. So, just for a brief timeline of bounded rationality, the concept really got started with Herbert Simon, who introduced it in the 1950s and wrote a lot of seminal works on this. Then in sort of the 1970s and 80s, it was later extended and really fleshed out by Amos Tversky and Daniel Kahneman in their research program on heuristics and cognitive biases, as well as their distinction between System 1 and System 2 thinking. Then later in the 90s, you have Gerd Gigerenzer, who introduced concepts of adaptive toolboxes and ecological rationality, as well as Stuart Russell, who worked on bounded optimality. And then ever since then, especially in the 2000s up to now, there's a proliferation of approaches and ways of modeling this, some of which I'll talk about next. So one of the key concepts here is computational rationality. And the basic idea is that we want to select the optimal program for some bounded machine to execute. And so you can imagine in this diagram on the left here, you have some sort of utility function and environment from which you select an optimal program within a space of feasible programs. And you can study the optimal behavior for such programs and connect it to observed organism behaviors. On the right here, you see another way of thinking about this idea of computational rationality, where you have your utility, which is diminishing with a cost of delays. And this trade-off means that there's an optimal time for you to run your computation before you select an action. And a key concept here is that of meta-level reasoning, which focuses on considering the current uncertainties, the time-critical losses with continuing computation, and the expected gains in precision of reasoning with additional computation. Now, another concept that's been increasingly popular in recent years is that of resource rationality. And the key idea here is that we were trying to find the optimal way for an agent to use its limited resources. So you can imagine this triangle here representing a space of possible minds that are implementable with our brain's limited resources. And on the y-axis, you have performance of these different minds. The resource rational approach is to find the optimal one within this feasible set. And some of the key steps associated with resource rational analysis is that first you define the problem at the computational level. Then you postulate a class of algorithms that the mind might use to approximately solve the problem, the cost of computational resources, and the utility of accuracy of the algorithms. After that, you want to find the algorithm in the class that best trades off resources and accuracy. Then you evaluate the predictions of this algorithm against empirical data. And if there's a gap, you go back to step 1 or 2. Now, another concept within this space is that of information theoretic bounded rationality. And the key idea here is that we account for the cost of cognition using tools and concepts from information theory. In particular, agents start with some prior probability distribution Q over choices and does some computation or information processing to transform it into a posterior P. And you can measure the cost of this transformation as a KL divergence from the prior to posterior. And so the agent optimizes an objective, which is an expected utility term minus a regularizer, which represents the information cost. So the key questions related to bounded rationality and alignment in this context of ecosystems is, first of all, how do we build these specialized, efficient, and reliable agents? Secondly, how do we coordinate such agents with each other and with humans or organizations to reliably and safely solve more complex problems? Finally, how do we mitigate the risks that might emerge, particularly in the context of these multi-agent systems? Now, our view is that this is an important research agenda, and we hope that we are able to dedicate resources and talent towards solving these important problems. Thanks for listening. Hi. So Mao and I are going to be presenting some thoughts and ideas that we have on path flexibility and collective alignment. So to start off with some motivation, why path flexibility and what is it? Our starting point is essentially that approaches to alignment should address some key properties of the real world, which include non-stationarity of the environment, non-stationarity and diversity of human beliefs and preferences, bounded rationality and imperfect execution of plans, collective and system level properties, and also the embodiment and embeddedness of agents within their environment. And so to address some of these issues, we suggest that we focus on paths and processes. And these things would include the alignment of beliefs and preferences in terms of how they update and not just what they are, the ability to efficiently adapt and recover when environments or goals shift, and also the maintenance and flexibility and optionality over time, rather than rigidity and narrowness. And so a simple example of this is a lava world example where the agent has to go to its goal and traverse this pathway where there's lava on either side. And the basic intuition here is that the agent should expend a little bit of extra effort to traverse the middle path, because this provides them more flexibility and resilience in case they accidentally slip to either side. So some of the key objectives that we hope to achieve within our work. Firstly, to demonstrate the value of our alignment formalism. Secondly, to study how path flexibility and empowerment lead to resilience. And finally, to develop methods to promote path flexibility and empowerment. So some key concepts that we find useful to study and address and define. Well, first of all, there is path flexibility, which we refer to as the quantity and ease of shifting between viable trajectories for an agent or group. Then there is empowerment, which roughly relates to the degree of influence that an agent can exert on its environment. There is resilience, which is the ability to recover from and adapt to adversity through mechanisms of redundancy and degeneracy. And there's concepts of attractor difference, which is roughly the distance between agents' stable belief or preference trajectories. And the key idea here is that the closer aligned agents' attractors are, the more similar their trajectories will be. And there is plasticity, which is roughly the degree to which beliefs, preferences, or policies can update in light of prediction errors and changing circumstances. There is planning horizon, which is also related to the cognitive light cone, which essentially measures the effective temporal depth and breadth of active inference or planning into the future. And finally, precision control, which is the capacity to modulate uncertainty, including sensory, policy, or belief precision. So some key questions that we want to address. First of all, how do coordination and communication contribute towards path flexibility and system-wide resilience? Here we hypothesize that these things come hand in hand. Second question, how do high attractor difference and low plasticity lead to lower collective path flexibility? Thirdly, how is plasticity related to the ability to recover and adapt after shocks? Fourthly, how do the breadth and depth of planning horizons affect resilience, and are there diminishing returns? And finally, how do precision asymmetries and precision control influence the power to shift attractors? And so with that, I'll pass on to Ma to discuss some of the experiments.
Thanks. So for the experiments, for now, they're explained in grid worlds, but they're meant to then be made a little more complex to fit the common grounds. So the first experiment is meant to establish a baseline of coordination benefits, i.e. is there even a point to coordinate and align? And so here we have a setup with 2 agents and 2 resources with optional communication at a cost. And we're hoping to manipulate the communication and the shared observations to show and to measure whether there's a higher cooperation rates, to measure the energy expenditure and the path returnability, i.e. We expect to show that communication increases path flexibility and shared reward. In experiment 2, now that we've shown coordination leads to better outcomes, we must show how it might arise from our chosen formalism, so aligning attractors. And so we hope to demonstrate that alignment emerges from adaptive preferences rather than just identical goals. So here we have 2 misaligned agents with variable preference update rates. We're going to manipulate the plasticity of their preference. And so ultimately we measure the attractor difference, the time to coordination, and efficiency over the long run. And we expect that higher plasticity means faster convergence and ultimately higher joint resilience. I think the videos are struggling to run. So do you want me to wait a bit?
Yeah, we can skip this.
All right. And so in experiment 3, we're trying to demonstrate that plasticity promotes recovery and adaptation after shocks. And so we want to show the mechanisms that underlie the plasticity in question, i.e. what do the agents learn and from where? So we hope to show that it leads to higher group resilience and path flexibility, which means recovering from shock and continuing to thrive. So the setup here is multi-agent grid world with periodic shocks, so resource relocation and noise. And the agents learn online from prediction error. We're going to manipulate high individual or group plasticity, social posterior sharing, so belief sharing, and redundancy versus no redundancy, i.e. whether agents can do the same thing more or less, or do they have more degeneracy, for example. We're going to measure the recovery time, the prediction error, the free energy slope, and the group resilience index, i.e. are they more resilient as a group or not. We expect to show that learning from errors and sharing those corrections creates faster, deeper recovery and turns resilience into a group level property. In the next slide, we ran a short experiment on top of a paper that Rudy, Pitlia, Zhang, and Tim Verbaelen and the rest of their team at Versus ran on theory of mind with 2 resources. And basically, we were able to show that through theory of mind and belief sharing, the agents are more able to recover quickly from a shock. In experiment 4, we want to show that we need to think in terms of paths and extend the planning horizons such that we can maintain path flexibility over time. We also want to show that planning as a group yields more rewards because planning is metabolically costly. So doing it as a group reduces the individual cost. So the setup would be agents with variable planning horizons facing unexpected resource shocks. We would manipulate the cost of horizon expansion, the shock magnitude and frequency, and measure the recovery time, the performance degradation, and the path survival rate. And so we expect that extended horizons yield better adaptation, but at a metabolic cost. So it's better to do it as a group. And finally, we want to show that these are not just chance outcomes. We can actually manipulate paths and lead to alignment. So here we test whether power in multi-agent inference arises from prediction control rather than just force. And so we can show that one agent can modulate another sensory or policy precision via environmental actions. So the manipulation here is the control strength and the target precision type. And we would measure induced policy shifts and cooperation rates to show that ultimately we have the ability to change the attractors for the agents to lead them to potential similar paths without necessarily losing path flexibility. And so here we have an expectation of asymmetric path precision distorts the path flexibility of one of the agents, which generates a dependency or a domination here and basically just control of one agent over the other.
Great. And so just as a synthesis and some next steps, obviously these are very preliminary ideas, and there's a lot of empirical work that remains to be done. In particular, we want to study the connections between path flexibility, resilience, and energy efficiency in more detail. There are a lot of conceptual questions, for example, linking our findings to empowerment, particularly on path flexibility, fed intentionality, and other alignment metrics proposed in the literature. For implementation, in order to bring in the embodied aspect, we want to build a prototype in common grounds with some basic features to demonstrate how spatial properties and embodiment affect questions of path flexibility and resilience. And finally, the deliverables we hope to achieve include theoretical formalizations of the concepts that we discussed and introduced, and some mathematical results relating them to each other. Further empirical analyses both in grid worlds and in common grounds, and then some data visualizations. Thank you.
The purpose of this recording is to show you a sort of new view on engineering systems with provably beneficial or aligned behaviors, as the title suggests. And it will mainly look into how do we actually predict what systems do, and how do we use that to our advantage. So I would normally begin this presentation with a small demonstration. This is a recording, so I can't give the demonstration in person, but this kind of lecture would begin with a demonstration where I would roll up a sort of tube of paper and make it into a kind of canal shape, and crumple another bit of paper into a ball and roll the paper down the canal. And you would see it drop into the canal and roll out. I would then take the canal and turn it upwards so that you have a sort of hill, and the ball would drop onto the top of the hill and then fall off. And what that demonstration would show is that there are actually differences in the way that motion is constrained by geometry. So the forces that guide a system to move are simultaneously geometric features of the system and the environment in which it's moving, and also dynamical features such as the forces that are shaping their motion. One can see this in the distinction between stable equilibrium and unstable equilibrium states. So if I have a ball at the top of the hill, then it could roll off the hill one way or another. I don't know which way it'll go. It'll depend on some kind of fluctuations. So that's U1 there. If I have a stable equilibrium like S1 or S2, it's at the bottom of the hill, then the geometry is constraining the motion. So the pathway that the system will take over time is dependent on the setup of the environment that it's in. This sort of tension between geometry and dynamics is captured really well by gauge theory, and correspondingly gauge theory gives us a way of speaking about how one quantity varies another as it moves on space-time. So in gauge theory, this often records the way that a force field varies the motion of a particle, and it records the coupling of bosons, which are force-carrying particles, to fermions, which are particles that comprise matter. And a really instructive example is that of gravity under general relativity. The principle of general relativity is that special relativity, the relativity of motion with respect to the speed of light, can be extended to any expression of motion which is accelerating relative to some other expression of that motion. A consequence of this view is that all non-inertial motion is identical to inertial motion on a curved surface which causes some acceleration. This is called the equivalence principle. And the equivalence principle was properly introduced by Albert Einstein in 1907, when he observed that the acceleration of bodies towards the center of the Earth at a rate of 1g, g being the acceleration due to gravity, is equivalent to the acceleration of an inertially moving body, meaning not accelerating within a frame of reference, that would be observed on a rocket in free space being accelerated at a rate of 1g. So if you have a thing in motion and it's not accelerating within a frame of reference, that's perceptually the same as if it were in motion and its frame of reference were accelerating. So again, this is the equivalence principle. Accelerating reference systems are physically equivalent to gravitational fields. As such, the curvature of space-time is gravity. One sometimes hears truisms like there is no experiment observers can perform to distinguish whether an acceleration arises because of a gravitational force or because their reference frame is accelerating. So the curvature, the warping, the acceleration due to motion is not distinct from a constant velocity, no force motion within an accelerating reference frame. Another truism due to John Wheeler is that space-time tells matter how to move, matter tells space-time how to curve. And we can see this is most, let's say, impactful when one looks at a black hole, the path of a photon, a light-carrying particle on space-time, is warped so strongly by a black hole that it, or rather, the path on space-time that it takes is affected by gravity so strongly that it looks as if gravity is completely taking space-time and pinching it and pulling it way, way down. So we have this interplay between geometry and constraints and dynamics and forces. This interplay has also been useful in the field of biophysics. So in the work of Ken Dill, for instance, it was discovered that one of the organizing principles for how proteins fold is if you set up a kind of energy landscape and you look at what are the transitions in states that the protein can achieve as it goes along dynamically, the geometry of the energy landscape turns out to constrain what the protein does, and it allows you to make predictions about how the protein will fold as it continues to go along and experience conformational changes. This was a big advance in the 90s in biophysics, in protein folding, because there were no good overarching principles for how proteins fold. But the work of Ken Dill gave us one such principle, which is that the loss surface, so to speak, between energy and entropy is determining how the protein folds, and it looks as if it's sort of a bunch of skiers going down a hill. So they take the path of least resistance. They take the most natural path afforded to them, and the interplay between energy and entropy and the geometry, the curvature that that interaction evinces is what actually guides the notion of resistance. This is true also in genetics, in the theory of epigenetic expression. There is the notion of Waddington's landscape, and it looks like a marble rolling down a hill. What people often use this analogy for is saying you have set before you a bunch of possible paths of genetic development, and your system is the marble. And as it's rolling down the hill, it gets caught in one or another canal. And that canal it gets caught in is what determines the epigenetic expression and therefore its phenotypic traits. But underlying the actual curvature and therefore underlying the dynamics of gene expression are a whole web of interactions that determine what kinds of expressions are allowed, what kinds of expressions are admissible, or which kinds of expressions require a large burst of energy that would be needed to get you from one free energy canal in the landscape into another one. So you can see in this figure there are a whole bunch of pegs and trusses shaping. In some recent work, I proved a theorem that says that actually inference in general has this property, when you are trying to infer the probability being assigned to different states, if you have a sense of the constraints on the probability, or the constraints on the preference of how likely or how desired a state is, then that constraint function gives you a surface. And there's a very nice, very well understood one-to-one mapping between the geometry of the constraint surface and the resulting probability density over the state space. So you can see in subfigure A, I have my constraint landscape. It's a sort of distance function. It says that as I get further out from the center, my penalty increases. It becomes much greater. If I look at subfigure B, I have all these level sets of equiconstrained states. So states with similar preferences. And those are the states that are available to me if I designate a level set of constraint value. I say my preference for the state is going to be such and such. I have whatever tolerance I'm going to give myself for getting away from the center. And then these rings are all of those level sets of equal constraint value. In figure C, I can see myself projecting those rings down onto the state space. So now these are all of my states of equal constraint value with the constraint surface overlaid on them, highlighting those rings. And then in subfigure D, I see how the idea of maximum entropy is actually a geometric procedure that converts the geometry of these level sets into a probability distribution, so that the equally constrained level sets are equiprobable level sets. And the curvature that affects my sort of how radical the change in preference as I move in some direction is, that gets converted to a log probability gradient, or in other words, a surprisal. So what is afforded to me by this technology is a deeper understanding of how systems which are making decisions about what states are preferable and what states are not, and then evolving according to those decisions. What is afforded to me by this technology is a description of such systems as though they were marbles rolling down a hill. I'm afforded some geometric description of those systems. So before I move on to that, I just want to say the ultimate goal is to then map out the geometry of such spaces and start to make predictions about how complex systems are going to move in their state spaces using the knowledge afforded to me by the mapped out geometry of those state spaces. Some other interesting things that this gives me access to are, you'll recall, we made this analogy to gauge forces. Well, gauge forces, they are sort of abstract mathematical things that relate curvature to forces. They relate geometry to dynamics, but they're physical things as well, right? The notion of a gauge boson is a physical force-carrying particle that actually tells you how a force creates a curvature. How does a force being applied warp space-time? How does geometry get created by dynamics? So these are things you can go out and measure in nature. And that means this gives us certain knobs to turn. So, for instance, if we're looking at engineered biological systems, there are observations of localized excitations in those tissues that actually look like what mathematicians would call solitons, and solitons are a type of boson. They're a type of topological excitation. They're a type of gauge boson. So this gives you a knob to turn in the sense that now you can go look at, here's the excitation corresponding to this kind of intended evolution. If I want to bring about a different kind of evolution, what do I need to modify in my observed excitations? And how can I continue to probe and change the excitation being expressed until I get my system into the right canal? A lot of parallels are drawn for me to Michael Lennon's work on bioelectric signaling networks, where it is shown that the thing that mediates how systems evolve through morphological space, the thing pointing to states in morphological space, and the thing mediating transitions between those pointer states, is a bioelectric signaling network. And this is something that is very easily accessible by human beings, by scientists, experimenters, and so on, and can be directly modified. If we can model it as an electrical circuit, then we can ask, well, what happens if I pass a current of this voltage with this direction through the circuit? How does the system then evolve? And if we've mapped out morphological space, then we can go on and start making predictions about how that mapping carries the modification through. With respect to alignment, I'm very excited about the prospect of looking at complex systems and saying, I'm going to map out the geometry of this system's possible evolutions. I'm going to infer some utility function or some constraint function telling me, well, what does the system prefer? What are the kinds of states the system wants to visit? How does it want to visit them? Once you have that geometry, and if you have physical knobs to turn relating to a description of that geometry by some mediation, some dynamical mediation, gauge bosons, for instance. If you have that and you have a knob to turn, then you can start manipulating that geometry. You can start coaxing the system to evolve towards other states, right? If you have the preference function derived from mapping out this geometry, and you also have the knob to turn, then you know exactly what you're doing. You know exactly how to tell the system to say, I would rather prefer this over that. So as an alignment problem, when we refer to engineering systems with provably beneficial behaviors, what we really mean is figuring out what is the preference or reward function determining those behaviors, getting that out of the geometry, inferring that, mapping that, and then taking some intervention that reassigns those preferences. So if we can find the preference function, we can modify it to say, for instance, to avoid a paperclip situation, to say, I want you to pursue world peace, but don't just have pure pragmatic value. Don't just say, okay, the path to world peace is to eliminate all humans. No, we have the preference function. We can see what would it take to introduce some sort of Asimov's 3 laws or something. What would it take to make the system think, pursue world peace, but don't harm humans in the process? So ultimately, this is all about mapping the evolutions of complex systems with an eye towards understanding what does it look like to teach and mentor artificially intelligent systems. How can we increase the synergy between biological and artificial intelligence? So I hope this was compelling. I'm personally very excited by this research program and the way that it involves a lot of very pure mathematics, very pure geometry and dynamical systems, and very forward-looking futurism, and tackles some of the biggest, most important existential questions of our time. So thank you for listening. And if you have any questions, please write me an email or get in touch with me some other way. I'd be happy to chat with you about anything that might have piqued your interest.
Hello, my name is Zara Shekhbai. Today I will talk about Maple, a specialized modular architecture for collective intelligence, and briefly about Hello, my name is Zara Shekhbai. Today I will talk about Maple, a specialized modular architecture for collective intelligence, and briefly about our in-progress stream to explore world model architecture. Both projects are inspired by active inference and aim to build social and uncertainty-aware agent that can better align with human values. This work is a collaboration between the Institute for Advanced Consciousness Studies, MILA, and University of Montreal. Instead of chasing abstract AGI in the usual way, my work focuses on what I call social neuro AI and brain-inspired architecture. We take the brain as a modular parallel system, and we use active inference idea to treat each module as an implicit model of the world and other agent. The big idea is that human compatible intelligence must be social from the start, with architectural prior that favor pro-social behavior, theory of mind, and mutual modeling. Let me start with how complex social behavior emerge and how has been studied today. In OpenAI hide and seek environment, which was published in 2020, self-play creates an auto-curriculum of strategies like run, chase, build forts, use ramp, defend ramp, and so on. Team learn to use tools and division of labor, but each agent still uses a single monolithic policy network, and the internal structure of these strategies is opaque and it's not interpretable. Roma take a step toward a structure by explicit modeling roles. Each agent sample a role from its observation, condition its policy on the role, and regularize the by that, and push roles to be identifiable, compact, and specialized. This allowed them to have more interpretable division of labor, but roles are still imposed in a top-down way rather than emerge directly from a modular architecture. Our core idea is that big monolithic network entangle everything, so any change becomes risky and unpredictable. If one part breaks, the whole system can lose its ability. In contrast, true collective intelligence from ants to human relies on diverse experts, decentralization, and knowing who needs to track whom. We want systems that look more like a team of specialized mechanisms that share only sparse information, so adaptation stay local and robust. To get this kind of specialization, we built on recurrent independent mechanism or RIMs. Instead of one big recurrent neural network, we use several small recurrent modules, and each module has its own hidden state and its own parameter. At each time step, we run an input attention phase. Every module sends a query. The input gives keys and values, and top case selection decide which modules actually receive and process the information. Only those active modules update their hidden state through their recurrent self. For example, a small GRU, while the inactive ones simply keep their previous memory. Then we run a communication attention phase where active modules use query, key, and value over each other's state, so they can exchange a small amount of information before going back to mostly independent dynamic. This gives us a sparse activation, a sparse communication, and a natural way for modules to be specialized. Our first Maple architecture that we introduce here is the RIM-only model, which is also our best performer. Each agent gets an egocentric pixel observation for the policy and a global observation for the value, which we pass through a normal CNN encoder. The encoder features then goes into a RIM, and the combined state is used to produce both policy and the value. Over time, different RIM can specialize in tracking different aspects of the environment or other agent, giving us a modular social policy. We also use independent PPO as our multi-agent architecture base. The second architecture aims for a stronger interpretability and object-centric reasoning. Instead of a standard encoder, we use slot attention to factor the scene into a set of latent slots, where each slot tends to represent an object or entity. We then feed each slot into its own recurrent module, again a RIM unit, so that objects are tracked over time through dedicated memory pathway. This makes it easier to say things like this module is tracking the opponent and this slot holds the shared resource information. For this to work, the slot features themselves must be high quality. We pre-train a slot encoder using reconstruction and a compositional consistency loss on data collected from the environment, so the same object is mapped to similar slot across different scenes. The Tesseny plot in the latent state of the slot here shows the initial result. Slots are starting to separate, but clusters are messy and overlapping, which push us to design a stronger inductive biases. To sharpen these representations in the latent space and make them more clustered, we introduce our perceptual orthogonal projection loss, or POPL. POPL encourages different slots to be distinct, push class center to be orthogonal, and pull features towards their center. Different object type or roles should sit in orthogonal direction in feature space, and each type should form a tight cluster. After adding POPL, the Tesseny plus in the latent space should clean, well-separated cluster, which gives our RIM a much more disentangled object-centric input. So this avoids the interference between what gets inside each of the RIM module. This object-centric is not tied to a single game across very different melting pot environment like allopathic harvest and territory room. POPL still produce clear clustering and disentangle feature in each slot. This suggests that we are learning a shared object vocabulary that can transfer across social games and can later be reused in benchmark like Meta AI and Common Ground. Once a single encoder is pre-trained, we copy it to all agents and allow only the high-level representation to be fine-tuned, but we face a classic stability plasticity dilemma. What does it mean? We want to adopt the high-level features of a slot during the RL task, but we do not want to forget the useful objects structure they learned during the unsupervised pre-training. To manage this, we freeze low-level feature and fine-tune only high-level selected layers, which by adding elastic weight consolidation, POPL, weight clipping, and normalization, these tools protect important weights, keep a slot representation disentangle, and still allow the policy to adapt to each social environment. Here we compare our two maple structures side by side. The rim-only model uses a simple encoder plus rim, and it's fast, lightweight, and very strong in performance. It's good default when you care mainly about robustness, sample efficiency in complex game. The slot rim model is more complex because it requires pre-training and carefully fine-tuning, but in return it gives us interpretability, object-centric slot, and clear specialization of modules from end to end. So we think of it as a model for analyzing, auditing, and reusing a skill, especially when safety and alignment are priorities. We evaluate Maple on Melting Pot, which is designed to test generalization and collective intelligence. We focus on three environments that form a ladder of social complexity. First, the territory room as low complexity spatial competition with 9 agents, mostly working in isolation. Repeated prisoner dilemma as a mixed motivated game with 8 agents, and allopathic harvest as a high complexity coordination problem with 16 agents. If modular architecture really supports social cognition, the benefits should be most visible in the harder environment. This slide shows reward over training for each architecture. Our rim only model is green, the slot rim model is yellow, and monolithic baseline like GRU and transformers, which are used as memory in the policy networks, are in the other colors. In both territory room and prisoner dilemma, the modular model learn faster and reach higher return than baseline. In allopathic harvest, the gap is the same. Modular agent achieve a stable high reward, while monolithic network mostly fail to coordinate in the complex environment. Now we are testing the scaling law, and we ask whether performance is just about adding more parameter. We vary the number of rim unit and how many can be activated at once. We find that more modules helps only when activation stays sparse. When everything is activated all the time, performance drops slightly. So it's not just capacity, but capacity plus sparsity. Structured interactions matter, much like having a bigger team of experts who do not all talk at once and they can communicate efficiently. To look inside the network, we evaluate our model with using conditional mutual information as a metric. CMAI asks how much information a given module K in agent I holds about the actions of agent J beyond what is explained by its own actions. In other words, it quantify how much a module is modeling another agent's behavior, which is a proxy for theory of mind processing. As social complexity increases across these three games, we see CMAI value rises and spread across more modules, showing that the network allocate more capacity to more complex environment and more clustering and specialization between agents. We can visualize this as heat map where rows are modules and columns are other agents' actions. Some modules light up across many agents and look like coordination between agents. Other track a specific partner or norm violation like monitors and sanctioners. Some are more sporadic like freerider. This connection back to Roma, instead of adding explicit role parameter, we see role emerges from interaction of modular dynamic in the environment. So we move from black box emergent strategy to monolithic interpretable picture of collective intelligence inside our multi-agent system. So again, putting this all together, Maple gives us a small toolkit. If you want maximum performance and efficiency in complex multi-agent tasks, RIM architecture alone is usually the best choice. If you focus on interpretability, object-centric, and reusable scale for alignment and auditing, a slot plus RIM is more attractive. I see them as complementary. Simple RIM for everyday deployment, a slot-based RIM for probing, intervention, and safety research. These architectures are also well matched to upcoming benchmarks like MetaAI and Common Ground. MetaAI aim at open-ended multi-agent cooperation and alignment with agent embedded in the nested social circle. Common Ground emphasize richer embodiment and multi-scale models of bodies and its rhythm dynamic. To succeed, the agent needs both a strong internal world model and modular social machinery, which leads us to the second part of talk, our dream to explore aiming. Maple gives agents a social brain at the policy level, but they still need a deep theory, like generative model of the world itself. Aiming, our dream to explore architecture, is a single agent world model that learns to imagine possible counterfactual future trajectory and plan in this latent space that it learns through learning a world model. It follows active inference idea. The world model is trained by minimizing free energy objective, and control is learned through imagination rather than risky real world trial and error. With Amy, an agent can dream thousands of candidate future trajectory in its latent space, including bad and catastrophic one, and learn to avoid them without even enacting them in reality. So Amy provides the explicit generative model and imagination engine needed for robust planning, while Maple provides an implicit model for modular social machinery needed for social cognition. Let me briefly sketch AMI architecture instead of a simple Gaussian prior, which is usually used in variational model, and it suffer from mode collapse. We use a Dirichlet process Gaussian mixture model as the latent prior. We also add a bottom-up attention posterior from the current image and a top-down attention prior for the latent state and context to mimic an attention schema process. During training, we ask the prior and posterior attention to agree, so the model learns both what will happen and where it should focus next given current action. The non-parametric prior can grow new mixture component when the environment become more complex, so it can represent futures like either outcome A or outcome B instead of one blurry average, and it gives better uncertainty under distributional shift. For dynamic, we use variational recurrent models, and we add perceiver inspired temporal context model. The perceiver reads full trajectory through a and use its bottleneck as a context vector, which condition both inference and learning the transition dynamic. During training, we use a variational posterior and teacher context, and during imagination, we sample from Dirichlet process Gaussian mixture prior and roll out future using a learned causal student context predictor. On top of this word model, we train adversarial guided active critic purely in latent imagination that produce with this generative word model, and it improves exploration and robustness compared to a standard dreamer style actor model. So to wrap up, we have two main pieces. Maple give us modular, brain-inspired, implicit word model architecture for multi-agent system with clear evidence of emergent specialization and increasing social modeling as environments become more complex. AMI gives each agent a rich probabilistic explicit word model that can imagine and plan over uncertainty of the future trajectory in the latent space instead of acting blindly in the real world. So many existential risk stories assume a single opaque monolithic superintelligence that we cannot interpret or control. Our work points to a different path, an ecosystem of modular interpretable agents with strong inductive biases inspired by mammalian brain for cooperation and mutual modeling. If we design these architectures carefully from the start, alignment can become an emergent property of the whole society of agent, not just the patch we add at the end. So I see these modular world model based architecture as a concrete reason for hope, a path toward AGI that is plural, understandable, and fundamentally built for cooperation. Thank you for your attention.
Hello, everyone. This is Song Jupei. Thank you for being here. It's a pleasure to share this talk with you. First of all, I would like to take this opportunity to express my gratitude to everyone who has worked hard to organize and prepare this symposium. Thank you so much. So the title of my talk is Modeling the Emergence of Perspective, an Active Inference Account of Intentionality. But before getting into the main part, I have to admit that I spent quite a bit of time thinking about what I should show and share with you today while preparing this presentation. Since this month, I have officially joined the Active Inference Institute as a research fellow. So I wanted to share some of the research agendas I hope to pursue as a member of the Institute, but also wanted to make sure that this talk resonates within the spirit of the symposium, and which feels engaging for everyone participating. So after much thought, I decided to shape this talk not as a report of any finished results, but rather as a reflection on why I have come to walk this path and what kind of inquiries I wish to continue exploring within this community. So rather than diving immediately into technical details, I'd like to focus on a few broader framing questions that include why should we study consciousness, why consciousness matters, and how might phenomenological insights meet computational modeling under active inference framework, and why this convergence is crucial for addressing the agent alignment, the social alignment problems, including the AI alignment. And most importantly, how can active inference serve as a framework in this process? It's hard to answer exactly what will emerge through the work, and somehow I think perhaps that uncertainty might be part of the process, but my aim here is simply to be honest, as I have always tried to be in my own research journey. So I often introduce myself as a consciousness researcher. And I think it's worth now to share a bit about how I came to walk with this path and why I continue to stay on it. So personally, I have had a kind of lifelong question on why can we never fully access another's inner world, or why such subjective and personal experience are ineffable and unreachable. This question began from reflecting on the isolation of experience. That is, no matter how deeply we empathize, we can never actually know what is it like to be someone else. Each of us is enclosed in our own private qualia, so to say. So I started to wonder, how does this subjective living experience arise in the first place? And is it truly something that can never be shared? And why do such subjective living experience, like including suffering and joy, seem to have such purely intrinsic and private origins? So those living phenomena are clear to me that they cannot be simply reduced to behavior or mere functionality. So there is something irreducibly first person about it. That is, experiencing is something about having a perspective of mind. So to have subjectivity is to have a perspective, and to have a perspective is to inhabit one's own universe. Each of us, in that sense, lives within a world model that is uniquely of our own. And then communication, what we call understanding or alignment, or even attunement, is, in its heart, a meeting between your universes, I would say. So it is not about controlling or synchronization, but it's about resonance or attunement between perspectives. So even though we can never become another person, we can still affirm their universe. We can recognize the limits of our own world models and respect the plurality of values and perspectives that arise from this. In that sense, alignment is all about perspective taking and resonance. So it is less about governance under law and order, but more about honoring the uniqueness of each way the world can be experienced. And this, I believe, is where consciousness research and the alignment problem truly meet. So, for instance, people who rescue refugees in the Mediterranean often say that Even though they know, rationally speaking, their work may be futile in many ways, by many reasons, but yet once they meet and resonate with the sheer urgency of the refugees, by looking into their eyes and share that physical space together, they say that they simply can't stop doing what they do. But, well, I'd like to say that this is not unique to the case of material refugees. So if we look across a wide range of social conflicts, from the struggles of underrepresented minorities to the realities of war, we often find that what's missing is precisely this experiential resonance. So many conflicts arise when we fail to realize in a lived and a felt sense that the other is also a human being, someone just as real and alive as ourselves. So here one could, of course, imagine developing a program of something like a phenomenology and practice, quote unquote, to cultivate such resonance. But for the purpose of this talk, for now, I just want to emphasize that this is exactly where my own research on consciousness began. And it is also why I believe that understanding consciousness is indispensable for addressing the problem of social alignment, well, pro-social alignment, or what I sometimes call pro-social attunement. Again, understanding consciousness is ultimately what allows us to imagine aligned and coherent agents, whether human or artificial. So when we talk about alignment, whether in social context or in artificial intelligence, the discussion often centers around rewards, goals, and accuracy. But I believe alignment is at its core not just a technical problem of control or optimization, it's more of a problem of orientation and maturity. So most of social discord and misalignment arise not because people lack information, but because they lack perspective. So there is a kind of poverty of perspective, which is essentially a failure to grasp how another mind or another world model is structured and felt. So if we really want aligned systems, we need models that encode perspective, that reflect epistemic norms on how agents come to know, and effective stance on how they care and feel. So here, the science of consciousness grounded on phenomenology gives us a way to understand subjective experience in a principled and non-reductive manner. Through agent-based modeling, especially within the framework of active inference, we can simulate the agents that self-organize intrinsic value and perspective, rather than being externally controlled by rewards or imposed objectives. So this would let us able to model how agents evolve and adapt together, not through reduction or one-sided control, but through mutual constraint and resonance. So in the long run, my research vision, I would say, might be closely linked with integrating phenomenology and active inference in a computational manner to explore sentience as something emergent and relational and situational and bound in context. And eventually, for future artificial systems, this could mean modeling how perspective forms, how epistemic autonomy develops, and how the effective embedding, that means the capacity to feel with, becomes an integral part of intelligent agent. Now let's take a look at what might be required to realize the computational phenomenology. In some of my previous work, I proposed a framework that attempts to unify 4 different major theories of consciousness based on phenomenological analysis. That is, many theories tend to describe only partial aspects of consciousness, almost like the blind men touching different parts of an elephant. I won't dive in too deep here, but the paper's point was that all the 4 different theories are, in fact, describing different features of conscious experience. That means none of them are entirely wrong in an ontological sense, since each captures a partial truth of conscious mental process. So building on this unified framework, what I now hope to do is to model the minimal conditions of mind or of perspective itself as a step toward active inference framework-based computational phenomenology. Okay, so before I go any deeper, I'm sure many of you are already familiar with this concept, but let me just start from very briefly introducing what is the phenomenology when I speak the word out is. I argue phenomenology is important in doing the science of consciousness because consciousness essentially is an umbrella term. So it is important to discuss what exactly is the conscious phenomena that we are interested in and want to describe. And I argue conscious phenomena is not just the qualia or not just awareness, but every aspect of the entity of the experience. So basically, phenomenology is a philosophical view that begins with phenomena, which means the living experience as given. So taking the experience as given means that we should analyze the experience as a self instead of pre-implying anything before the existence of our experience. So for conscious agent, the experience is equal to the world, and it is not something that should be described through some external framework. So this intuition is from the discovery that first-person view always exists before the objective third-person view, that we cannot essentially escape from the first-person view no matter what we do. So intentionality here means that every conscious experience is constructed through the first-person attitude and situation. For example, if we are in a pessimistic attitude, actually, let me bring the framework figure here. Half filled cup of water here would be seen as half of the water has gone. So the blue colored part represent pessimistic attitude, and the yellow colored part would represent optimistic attitude. So, pessimistic attitude, half of the water has gone. Well, under optimistic attitude, that this half filled glass cup of water would be seen as half of the water is left. And this difference results in totally different quality of experience. So our experience cannot really escape from the intentionality. Specifically, phenomenology by itself explains the embodied nature of mind by always starting from the experience itself. So I would say this also plays huge significance to emphasize phenomenological discoveries when studying consciousness. And this is the framework that I propose, which is basically built upon the properties discovered through phenomenological research methods that I just introduced. So this diagram here illustrates a conscious agent finding themselves in a lab environment and spotting a half-filled glass of water, which is their current focus of attention. While on the one hand, perceiving it under a pessimistic point of view, and on the other hand, perceiving it under optimistic point of view. So this different point of view is depicted as different intentional quality, which give rise to different conscious experience, left and right, while having same objects as the intentional matter. So here, conscious experience A, B, and C is also different to one another, depending how much this agent is deeply interacting with environment. So if the agent is closely interacting with the cup of water, like holding onto the glass and observing it, that experience would depict the cup of water in a much more vivid manner. And as it's quite literally or graphically presented, the vividity of the cup would mix in and decrease when the agent is not actively engaging in the cup of water. So here I point out 4 big properties of consciousness that necessarily should be included and investigated through any theories if that intends to explain conscious phenomena. So the first is pre-reflective self-acquaintance. This means every conscious individual recognizes their own conscious experience as belongs to their own. Whatever experience it could be, that very experience always belongs to themselves or ourselves, which means not to some other person than I. So importantly, this does not require any secondary or higher order reflection in realizing. So the name pre-reflective self-acquaintance. Second is contextualized and environmentally situatedness. Basically, consciousness is a dynamic process of interpreting the surrounding environments. So our experience is rather relative than being absolute. So this would naturally lead to the third aspect, which is called the spatiotemporal expandability. This points out that our conscious experience is something that is continuous and expandable with regard to surrounding environment, both spatially and temporally. So the conscious experience could be depicted as the layered contour graph, more specifically the contour surface of this diagram, putting bodily self or the pre-reflective self recognition as the very core. The last part basically describes agency. The conscious being, those can apply reflective analysis to their own experience, would inevitably possess the agency of shifting attention and the ability to apply selective attention under their own volition. This could involve multiple levels of shifting from simple perception to meta-awareness. Now let's talk about active inference. In my opinion, active inference framework provides a powerful foundation for applying phenomenological discoveries in an effective way, because it offers a way to formalize systems that are self-organizing and valence-forming. That means systems that maintain themselves through intrinsic preference formation rather than being driven by purely external rewards. So within this framework, intentionality, which is basically a key concept in phenomenology, can be understood as a kind of hyperprior that shapes an agent's behavioral dynamics. Similarly, pre-reflective self-acquaintance in phenomenological terms naturally connects to the body schema, or bodily up to bodily sensation. So active inference framework based on a free energy principle specifically provides a computational handle on this, suggesting how embodied states continually update the agent's generated model of self. And as the models evolve, an agent's world model naturally expands spatio-temporally, contextually, and socially, reflecting how perspective unfolds from immediate sensation to broader situational awareness, and including shared meaning, which is essentially what it literally means by active inference. So I kind of skipped over this part when I was talking about the theories of consciousness earlier, but to be specific, active inference-based predictive processing framework doesn't directly explain the formation of process of qualia itself in full detail, but what it can do is model the conditions for qualia and subjectivity. So basically modeling the self-organizing dynamics that makes subjective experience possible in the first place. And since what I'm trying to do as a first step is to model intentionality, or so-called perspective, as a minimal form of subjectivity, I believe active inference framework offers significant theoretical advantage for that purpose. Also, this is a whole another branch of research that I didn't go through in this talk, but it's worth noting that This framework can coexist conditionally with integrated information theory, which directly address the formal structure of qualia. So following active inference framework doesn't mean rejecting or ignoring the existence of qualia. Rather, I see it providing a theoretical space where the dynamics of subjectivity can complement the structural explanations offered by IIT. Another benefit of modeling according to active inference framework is that it allows agent alignment to be handled in a more natural way within a simulation environment. So active inference allows us to model artificial agents without hard coding their behaviors. So instead of scripting what an agent should do, we can simulate the environment, which includes the context in which the agents act, learn, and adapts, and let the agent, well, basically agent itself emerge from the dynamics of self-organization. So in such simulations, agents don't simply follow the fixed set of instructions. They adapt and grow within the context-defined environments, continuously updating their internal models in relation to what surrounds them. So in other words, their intelligence and value model is situated. And the same logic applies to the social dimension. When multiple agents interact, their goals and values begin to co-regulate over time. Through repeated interaction, what we might call empathy or altruism can emerge/evolve in a natural sequence as each agent learns to attune its internal model to others in its social environment. So in this way, active inference allows agent alignment to be handled much more naturally within a simulation environment as an emergent property of relational dynamics, not as a constraint arbitrarily enforced from the outside. Now we move on to the step 1, perspective modeling. So when I use the word perspective, I refer to something that deeply tied to what phenomenology calls intentional quality. I describe this as being, optimistic versus pessimistic from this illustration. In computational terms, we can think of this as how an agent assigns the informational value to the things it encounters, like different subjective experience arising from the same intentional matter, which is the half-filled glass of water. This difference technically can be roughly captured by assigning task-dependent loss functions, but that approach still requires hard coding the agent's preference structure in an arbitrary way. So instead, if we decide to explain this regarding active inference grounded in the free entry principle, these kind of preferences can be modeled as arising spontaneously through the agent's own inferential dynamics. In other words, instead of prescribing whether the agent should see the glass as half full or half empty, the active inference framework would enable the agent to develop its own epistemic and affective stance based on how it minimizes surprise in its unique environment, so that we could computationally model the perspective as an emergent property of self-organized intentionality. So here I believe this diagram would better depict the sequence, what I just explained. So here we can model the experience of different quality. So intentional quality under context like, dislike, indifferent, just as like the context of being optimistic versus pessimistic. We can model each experience being different sorts of probability distributions. So here the whole idea is that we could represent each different intentional quality as certain probability distributions. So here the subjective experience of same intentional matter, which would be, half filled a cup of water, probably, over different intentional quality is simply put as the conditional probability. We can essentially express this as different generated models under active inference framework. So here, each generated model should share the same hyperprior, which would resemble the bodily sense of self of this agent, or pre-reflective self-acquaintance. Also, please note that prediction error minimization and Bayesian update is not specified on this diagram. So if we ask how perspective can be modeled computationally, perhaps the simplest way to describe it would be something like this. So if we draw an agent network based on a generated model grounded in the four properties of minimal consciousness, it could be illustrated roughly like this, I would say. As you can see here, both of the exteroceptive dimension and the proprioceptive dimension operate through a chain of prediction minimization, where the loss function is formulated as a minimization of the prediction loss across both exteroception and exteroception would be the world model, basically, and proprioception, which is the body schema. So these two dimensions would jointly act as variables within the generated model, determining the agent's policy, which then leads to action. And of course, that action in turn would influence the inputs of the environmental input, which would act as a full loop in a dynamic sequence. But the key point here is that I intentionally granted the generated model with a latent structure. This latent structure encodes information, basically that's equivalent to possessing perspective in a valence-like form. So in other words, the worldview of the agent, being either optimistic or pessimistic, can be designed to stem out from these latent variables so that perspective itself becomes an emergent feature within the model. So this is still an ongoing project, but the goal for now is to implement this as a kind of wrapper function that could be applied within simulation environments like Python Gymnasium, which would make it available as a Python package applicable for simulation. Now, next step 2 and 3 that I'm going to introduce are not just about realizing phenomenological properties through active inference, but about stretching this framework further towards the problem of alignment. After all, as I mentioned earlier, my own motivation for studying the science of consciousness in the first place has always been deeply connected to the question of self-sufficient social alignment, after all. So this next strand of research is really about extending that inquiry from modeling minimal consciousness to exploring agent alignment as its natural continuation. So let me touch on a point that I find quite important, something about how we often misunderstand what alignment really means. So to me, equating training accuracy with maturity level is a kind of category error, because acquiring specialized knowledge and developing the ability to truly take another's perspective are two entirely different functionalities. So a system can be extremely, precise in prediction or classification, and but still yet remain completely blind to the lived realities of others. So in human terms, that's like being highly intelligent, but emotionally or both morally immature. So if you're serious about addressing AI alignment at a more fundamental level, then perhaps the discussion shouldn't be about training accuracy at all. Instead, it should be about maturity and specifically the capacity of perspective taking. Because it's at its core, social alignment is all about respecting the unique conscious experience of the other. So that should be the basis of all true attunement, whether between humans or between artificial agents. So when I say maturity, I'm referring to processes like perspective taking and meaning making grounded in metacognition. So maturity requires a certain subjectivity at the very least, which means the ability of an agent to reflect on its own standpoint. So here we can think of greater stages of ego development, or Keegan's notion of the subject-object shift, where growth is basically defined precisely by one's capacity to take what once was me and hold it as object, which means turning one's own worldview as just one among others. So what exactly do we mean by high maturity? In development psychology, this idea is closely tied to adult development theory and has also been extensively explored in meditation research too. So in those contexts, maturity is often evaluated through language patterns, essentially. So that means that how people describe themselves and surroundings and how they reflect on their inner life. So it is less about what we know and more about how we relate to what we know. At a deeper level, higher maturity seems to correspond to the ability to affirm the plurality of conscious universe, and to recognize that multiple perspectives can coexist without collapsing into one single truth. By linking these findings from the phenomenology of meditation to the model introduced in step 1, I would say we can begin to ask very concrete and testable questions, including what kinds of environmental interactions would stimulate an agent's growth and maturity, and within a simulation environment, how might we detect or quantify the markers of maturity as they emerge. And this becomes especially relevant when we think about self-sufficient social alignment. So if we want to cultivate alignment that doesn't rely on external control, we need to understand what factors can route these type of effective stances like empathy, care, and openness toward higher levels of maturity and perspective taking. So insights from this approach could extend far beyond our artificial systems. So they could inform not only AI-human alignment, but also human-human alignment, which means how understanding and attunement evolve naturally in social contexts. And importantly, this idea is particularly applicable in active inference framework-based multiple agent environment that will be described from the next step. Those settings would allow us to simulate the emergence of maturity as a property of relational dynamics. So now let's take a look at how the concept of maturity can be applied within a multi-agent environment. In development psychology, maturity is typically measured through language markers, as I mentioned before, but that doesn't necessarily mean we have to apply human language directly within a simulation environment. So even without language, when the communication is non-linguistic, it still functions as a form of information transmission and sharing. So whether agents use words, signals, or actions, the essential process is that the information is being exchanged and interpreted and also transformed through such social interaction. From this standpoint, it is able to define certain type of informational flow as a proto-linguistic maturity marker. In this view, communication can be modeled as each agent reinterpreting a raw message through the lens of its own world model representation. So that reinterpretation process would tell us a lot about the maturity status of the agent's cognitive behavior. For example, if we wanted to test certain dimensions of cognitive maturity, such as reflective judgment and integrated complexity, reflective judgment, RJ, could be understood as the ability to interpret a raw message objectively, which means with less with less bias coming from one's own perspective. So, say an agent with high RJ can recognize its own standpoint as just one possible lens among many. And while integrated complexity, IC, is the ability to consider and incorporate the world models of other agents when receiving or generating a message, that would mark agents with high ICs as more likely to adapt its interpretation in response to diverse perspectives. Now, using these measures, we can identify signatures of alignment failure modes. For instance, an agent showing high prestige bias, that is, overvaluing certain sources or hierarchies, is likely to have low IC, interpreted complexity, because it's not genuinely integrating multiple viewpoints. And if an agent seems trapped within its own world model, unable to update its interpretations, that would indicate low RJ. Now, to actually test these ideas, the next and for ultimate step is to set up a simulation environment that follows the active inference framework, that it would allow us to examine how maturity and alignment dynamics emerge through these agentic interaction. For a simple implementation, using the RxInfer package being developed from Active Inference Institute as a foundation would be one possible method, I would say. Especially utilizing the package within a relatively lightweight environment such as Gymnasium or Pygame would be a good first step, where these platforms are ideal for building early prototypes in terms of visualizing how agents adapt and coordinate in real time. So good on visualizing. For a more complex configuration, I eagerly look forward to multi-agent simulation spaces like Metagrid or Common Grounds. These frameworks are particularly useful because they support context-sensitive social dynamics, meaning that agents would adapt their behavior based on changing social or environmental contexts. In particular, Metagrid is a project that is currently being developed within the Active Inference Institute. So if it turns out the perspective architecture can be applied within this Metagrid environment, I believe it could strongly highlight the parts of the simulation that could benefit from active inference principles. And as for Common Grounds, which is basically a 2D Minecraft-like gaming platform where humans can directly intervene in the civilization building sort of processes of agents, artificial agents, I find it especially interesting because it allows us to design testable scenarios of pro-social alignment. And by the way, from my understanding, there's a live chat scheduled about this project as part of the symposium. So I would recommend attending it if this line of work interests any of you. So in any case, testing self-organized pro-social behavior based on maturity dynamics within such platforms is something I'm planning to work on as part of my research activities at the Institute. To close the talk, modeling consciousness leads us to understanding perspective. Understanding perspective, in turn, enables mature alignment, and while active inference is serving as a bridge by linking phenomenological insights with computational realization. Ultimately, alignment begins where understanding becomes empathy. May we act and infer and share. Thank you for your attention. If you have any questions or would like to share your thoughts freely, please feel free to reach out using this email. Thank you.
Greetings. Hello, Maxwell and Patrick. It is November 2025, and this is the Thermodynamic Brains discussion for the Applied Active Inference Symposium. So let us begin with whichever order you'd like, little introduction, and then we'll jump into some questions and discussion.
Awesome. Patrick, do you want to go first?
Yeah, sure. Thanks a lot, Daniel, for the invitation. My name is Patrick. I'm a physicist by training, now working at Nominal as a researcher, and we're trying to combine thermodynamic computing and active inference, probabilistic inference, to advance, let's say, robotics and other applications.
Awesome. I'm Maxwell Ramstad. I'm a co-founder at Nominal, active inference researcher. I've worked closely with Carl Friston. Very much interested in the intersection between information theory and thermodynamics, in particular non-equilibrium thermodynamics. So yeah, very excited to tell you a little bit about the thermobrain and what we're up to at Nominal.
Amazing. Yes, let's get right into it. So, what does it mean to say that a brain or reasoning in the brain is thermodynamic, or that it's a thermodynamic process or computer?
So, I mean, if you think of taking a few steps back, maybe from thermo itself, if you think of the free energy principle, what the free energy principle basically tells you is that basically in the presence of boundaries, what would ordinarily look like diffusion dynamics turns out to look like something a little bit different. I mean, in effect, what the free energy principle tells you is that the dynamics of systems that are separated but coupled by their Markov blankets will look as if they implement some kind of parameter estimation where the systems that are coupled but separated through their Markov blankets end up, I mean, effectively tracking each other's statistics or estimating each other's parameters. I mean, this is in effect a thermodynamic process. Although in the free energy principle literature, we tend to, emphasize the dual information theoretic description. This kind of coupling is ultimately a kind of thermodynamic equilibration. So what we think is striking, really, is that almost all physical systems that learn through this kind of coupling and gradient consumption, where when systems kind of find a dynamic equilibrium or reach a non-equilibrium steady state, they end up becoming parameter estimators for each other. I mean, yeah, the claim is essentially that all physical systems that end up learning the structure of what they're coupled to learn through this kind of thermodynamic process, with the exception, and I think it's a very important exception, of the actual digital machines that we've built that should be, the main kind of learning machines. These kind of machine learning stacks. Hinton calls these immortal computers for a reason. But I guess the paradox is that in architecting our digital computers such that they can execute instructions in well-governed deterministic ways, and hold on to pieces of information for a long time. In kind of architecting these systems, we've forced them to learn in a way that's unlike the way that anything else in the universe learns. So I guess part of our ambition here is to allow our thinking machines to learn in the same way that everything else in the universe does. Patrick, do you want to maybe like add on to that, or expand, or disagree?
No, I think it's a very complete picture. Yeah, I completely agree. I would totally second that.
Okay, where do you think reasoning fits into that? Is that process reasoning, or is it another layer beyond that that would make something reasoning as opposed to doing something prior to or below reasoning?
I think an important thing to point out is that, what we're talking about here is kind of implementing algorithms using the physics that naturally maps onto the algorithm. So this isn't necessarily about reasoning as opposed to perception, as opposed to learning, as opposed to policy selection. This is another kind of approach to, co-design in effect, right? So co-design is this idea that algorithms, so software, right, and then the devices that run those algorithms, hardware, should be designed together. What thermodynamic computing allows you to do, in effect, is to replace the simulation part in a lot of these sampling-based algorithms like MCMC with the actual physics that you're interested in, right? So MCMC, Markov chain Monte Carlo, right? The Markov chain part is the part where you specify the causal structure of transitions in the world using a Markovian model. And then the Monte Carlo part is about actually simulating the dynamics over time. And it turns out that, this kind of stochastic algorithm is extremely useful in the context of machine learning. I mean, if you've been on Twitter recently, like everyone is now talking about diffusion models for everything. And I think Elon Musk recently talked about like diffusion models for reasoning and this kind of thing. So the important thing is that all of these stochastic algorithms depend on simulating these kind of stochastic dynamics. And this is where I think the fundamental contradiction of the current R&D landscape for AI like enters into the picture. So on the hardware side, we spend a lot of time and energy to make sure that our digital computers are not stochastic, that they're fully deterministic, right? Like we drive the energies of these components to very high degrees to make sure that the bits are distinguishable in a reliable way, that they don't bit flip and so on. So on the hardware side, what we're doing is spending a huge amount of energy to drive the stochasticity away, and then we end up from the algorithm side reintroducing it. So the idea is to design a hardware stack that is more apt to the kind of algorithms that we want to run on them. So design a chip basically such that rather than simulate all of these stochastic dynamics, you can just have physics as computation. And that's really the key, I think. Patrick, do you want to add on to that? I've been talking a lot. I'm sorry.
No, I mean, so I think also maybe it's important to say that this idea is not that new. I mean, a lot of people have heard of quantum computing. No, you use a quantum system to do quantum simulations instead of running it on a CPU, which we know is very inefficient. But then there's also this idea of like analog computing in general. There's people, I don't know, using water pipes to simulate some systems. Also, even like actually putting a car in a wind channel is somehow a form of like doing physics-based computation. Instead of doing these simulations in like a digital computer, you use the actual physical object and wind and maybe some smoke to do these simulations. No, so these ideas are not like fundamentally new, but the evolution or the technological advances of the last years in like especially CMOS design allow us to actually build sophisticated devices that actually do this physics. As like that, I think that's the biggest change. Yeah.
I mean, maybe to address your question a little bit, because I think what you're asking is like, where does this fit into like current stacks? Like, what, you know, you mentioned reasoning, but like, why would you want to do this? And I mean, in effect, you know, a lot of so in the context of active inference, since we're talking to, you know, the founder of the Active Inference Institute, I guess on one level, the math of the free energy principle rests on these kind of stochastic thermodynamics, non-equilibrium thermodynamics formulations. So if you open Carl's monograph, which is, by the way, going to be published with Springer, I think either later this year or next year. I'm sure you've heard of it. It's now called the free energy principle on the nature of things. Well, so if you open the monograph, which is on archive in 2019, I think the original title was the free energy principle for a particular physics. So if you open that monograph up, literally the first equations that pop up are, you know, the Langevin equations, the Fokker-Planck equation. This is fundamentally stochastic thermodynamics. It's based on this kind of stochastic approach to you know, understanding dynamics. These are like fundamentally non-equilibrium formulations. So this math is important for the foundations of the free energy principle, and it's also very important, I think, to more applied work in the active inference space. So, I mean, as I'm sure you know, by now, it's turned out to be very difficult to scale active inference, in part because it's so purely Bayesian. It verges on the puritanical sometimes. So, in some interesting work that has allowed us to scale active inference up, what we do is we create hybrid systems that employ active inference, sure, but also, you know, MCMC family algorithms to perform, for example, policy selection. So Zaf Funtas has this very cool paper, or rather set of papers, where where he and his team explore, you know, implementations of sophisticated inference that use, you know, MCMC to finesse the policy search aspect of that, to avoid kind of like having to deal with the computational explosion. And obviously the bottleneck there is you have to run the Monte Carlo steps on, you know, a CPU or GPU or whatever, you know, is your favorite digital hardware stack. What this kind of technology, the thermotechnology, promises is to, you know, make those steps in the hybrid algorithm like dramatically more efficient. So, you know, the early numbers that are being reported here, you know, there's something on the order of like 10,000x less energy demanding. So that's significant, right? It's significantly more than, say, like a 50% decrease. We're talking about like orders of magnitude efficiency increase. So, you know, I mean, to put it a bit more simply, what this allows you to do is cheap sampling. And you know, for those in the audience who are machine learners, your ears have probably pricked up at this point, because, you know, sampling is very expensive, and it's arguably one of the main bottlenecks in, you know, just general deployment of machine learning technologies at scale.
Thank you, Maxwell. Patrick, do you want to go into a little more detail about what's happening inside the algorithms, inputs, outputs, what languages, or what similarities or differences with other kinds of toolkits that are available today?
Yeah, this is like probably one of the questions we get asked mostly, is like, yeah, what do you actually program on these devices? No, I think the simple answer is that we all aim in this community of thermodynamic computing to abstract this away. So in the end, if you're familiar with, I don't know the active inference community that well, but it's more like probabilistic machine learning, let's say, these frameworks like NumPyro, Stan, PyMC. If you're familiar with those, it's going to be very similar to them, if not even the same, no? Because NumPyro allows you to say, hey, I want to run this on a CPU, I want to run this on a GPU. Maybe in a few years, we just can change the backend to a thermodynamic computer. Because fundamentally, it does the same thing. It just does it in a very different way. Same as if you change from a CPU to a GPU, you don't mind just by using it in Python where it runs, but you will feel it in the difference of like how fast it's going to be executed. And then, yeah, obviously what happens in the backend is fundamentally different. So the sampling then really occurs through a physical thermal process instead of like some digital emulation of it. But to answer your question, for the end user, like most people in the field that do not care about writing their own compilers, nothing will change. Maybe 2 lines of code, just like send it to thermal or yeah, whatever we're gonna call it in the end.
Yes, interesting. So, I mean, what are those sorts of building blocks? How might you connect that to maybe Mars levels of analysis? Where does the cognitive part come into play? Or what granularity do you think about a system or a problem? And which pieces could you swap out and model?
Just to interject quickly, I'm not sure Mars level of analysis is an appropriate framework to think about this, because that framework supposes that there's a tight decoupling between the different levels of analysis, and in particular between the algorithmic and the physical implementation layers. What we're kind of saying is like you don't want to ignore those connections actually between the algorithm and the physics. The idea is to build a physical system whose kind of intrinsic physics, if you will, implement the algorithm that you want to run. So yeah, I'm not sure that kind of detachable or kind of separable concept is like as informative as it might be. I mean, what we're trying to say is like it's probably a mistake to separate the software from the hardware in such a dramatic way as we see in today's stacks, and things would be much better if we went the other route, which is to actually try to couple them more fundamentally.
Yes, I hear you on that. A little like an enmeshed, codependent, Marian,
yeah, precisely.
synthetic
and to Patrick's
stack.
Point, from the point of view of a software developer, this just changes the hardware that is actually running your software. So why you care is you're gonna have a radical efficiency increase. Like things are just gonna run faster at the end of the day. But I mean, you'll still be using the same kind of algorithms that are being deployed right now in software. It's just that the actual physical routines that the system goes through to compute those algorithms is just going to be that much more efficient. And this also opens the door to a kind of more extensive co-design approach to algorithm development. So if you're developing for thermo, then knowing about the thermodynamics of a TSU, a thermodynamic sampling unit, and how that works is going to be pretty important. So yeah, I mean, I think that your knowledge of how the hardware works is now going to possibly contribute to how you're thinking about software development. But in terms of model building, as Patrick was saying, it's pretty much plug and play. I mean, you might, as he was saying, route your algorithm through another kind of chip, but ultimately, this is more going to be a game changer from the point of view of performance and long-term co-design than just like in an immediate day-to-day kind of thing for developers.
And I mean, just like adding to that, it's like there's a lot of people on this planet that care about CUDA kernels and optimizing them, but a lot of machine learning practitioners have never touched pure CUDA, which is still a relatively high level language if you think of like actual transistors and the GPU, you know. So, but even that level of abstraction, which is already pretty high, most practitioners never touch. That's the job of like really specialized folks, and this still will exist. This kind of profession will continue existing, and people will have to think of like, hey, we have this particular subroutine that people really care about in, let's say, active inference, like this specific way of sampling something. Let's try to make this more efficient. And then there's also really like the hardware level where people think of like actual single transistors and how to communicate them together and so on. These kind of professions exist also now in CMOS. It's just like no one really talks about them in machine learning. You know, these are abstracted away, fortunately. Otherwise, you would not be able to do any meaningful machine learning if every machine learning engineer has to think of bits and transistors.
Yes. So to fuse a few questions together, let's say you were setting up a research and development lab over the coming few years timescale. What does that lab look like in terms of skills and hardware? And what kinds of problems, what sectors is it tackling, and why?
Hello, I'm Michael Lennon, and I am a member of the Science Advisory Board at the Active Inference Institute. I live in Washington, D.C., have an academic affiliation with a couple of local universities, and am by training a... Hello, I'm Michael Lennon, and I am a member of the Science Advisory Board at the Active Inference Institute. I live in Washington, D.C., have an academic affiliation with a couple of local universities, and am by training an economist and a technologist. And today, I'm going to share some reflections that, through the mostly lens of an economic technologist, you could say, about the impact of AI. About a year ago or so, I co-wrote a book with 7 others about the possibility in the future of AI. It was mostly optimistic. I was one of the skeptics. You can see the chapter I wrote there, Dancing with AI Fire. But it's been an area of interest for a long time, the kind of tensions that exist with artificial intelligence. And over the past year, some of these have simply continued to sharpen. One of the ways, certainly within not just economics, but from the mindset of economists, two mindsets about the future impact of AI on economies and on humanity. And one is that it will take over inefficient humans, that it'll shrink the bad in the world, but really it's going to be a kind of, this some would say is a techno-utopian vision of hyper-efficiency. A different techno-utopian vision is that we'll help grow the good in humans and amplify human capacity for meaning and contribution. And this debate is going on in many circles. One of the ways in which I have found talking about impact with folks is can be illuminating is using this particular diagram. I developed it a while ago for comparing investments in different technology projects around the world and comparing where they were targeting. The institution that I was doing the work for had a global portfolio, and one that wasn't just economic, but included social and other kinds of impacts. And yet all the reporting was done through an economic lens. And by asking people to talk about whether they were trying to address finance or experiential life or the larger systems such as the... Hello, I'm Michael Lennon, and I am a member of the... was one way of fairly easily contrasting these different projects, but often these projects also had two very different kinds of objectives. One was often a shrinking of a problem, and the other was often growing a new capability. And just like fixing a broken arm relieves your misery and helps create a sense of being better than when you were miserable, it does not make you an Olympic athlete. And so often these, by distinguishing between what are interventions that shrink harm versus growing good, one really gets much greater clarity about what is the invisibilized impact of the project that one is undertaking. And so often in one class of political mindset, there's the growing the good is often solidarity type economics, folks that are trying to grow the solidarity, the well-being, and such. Whereas often for efficiency and minded folks, the idea of shrinking waste is at the heart of what there is to do, and where, for example, neoliberalism often finds, and people who self-describe as neoliberals often find themselves setting up the focus of the work that they're doing. And so one of the things that both these narratives are useful, and they represent perspectives on realities. One of the things that's been interesting about the emerging science of predicting economic futures has been that it turns out that one of the most influential aspects of predicting a country's future economic performance is its networks. What kind of networks? In which kind of, it's learning networks, frankly. Learning cities, learning relationships between the cities, all of these, and the complexity and sophistication of these all are much more accurately predictive than many of the what have been traditional indicators used to look at what the future will hold. And that these particular networks operate at different levels, that there's both networks of people, individuals, networks of groups, networks of firms, and that each of these are like layers of a living system that each are learning in their own way, at their own level, and all are contributing in their own ways. And so really beginning to understand how the economy is often could be looked at as a kind of learning system that is learning how to do things better in the place where the economy is and add value based on what is there in the economy. That life does that often with the energy and nutrients that it receives from the living ecosystems in which it's in. And so a takeaway could be that a priority for AI in the future is to boost the learning capacity of networks, that we do this for ourselves, that we do this for the groups that we're in, and that when we're having conversations with others, that it's like, do we understand what are the networks and how can we boost the learning and interlearning? And it's really important to sharpen our understanding of what these different learning units are, because we have vocabulary that is mostly individual. And it turns out that as a group or a collective learns, it happens in a different place and in different ways. So I learn within my brain, if you will, to oversimplify things, and a hive of bees learns by interacting with other bees, signaling where is the honey, where are the flowers, and then responding as a group. And so we can be talking about learning and be referring to what is happening within an individual, or we can be talking about learning and be talking about what's happening across a group of individuals that are a self-organized group, or it can be between groups of groups, and so on. So the learning edges, whether they are within, whether they are between, or whether they are beyond the group, all of these are different learning edges that can be adding value and can be step points. So back to the original prompt for this particular presentation. There was last year in Barcelona a group of creatives and technologists and activists and civil servants, a variety of different communities, all in this vibrant city, that were hearing that generative AI was going to change the future. And they weren't sure whether it was all rainbows and lollipops. Some of them were skeptical. And so they were kind of, how do we get smarter about this? And how do we begin to grow the civic conversation about co-parenting a shared vision forward that is grounded in the information that we each have, our own individual perspectives, and woven together into a larger narrative. So each of these communities each brought their puzzle pieces, and they tried to assemble into a simplified map that became then a discussion board for moving forward. And it did help demystify and kind of build a greater pool of knowledge, as well as surface some of the tensions and controversies that exists. And among some of the outputs, if you will, was to identify 21 topics that they identified were affected by this emerging phenomenon of generative AI. They had under each of these topics whole bodies of additional content, but one could summarize these, and they did in the following way, that this phenomenon of generative AI was magical was the word they used, perhaps oversold, and that there were fascinating and dazzling things about it, and hidden harms, and that some of the pattern of accelerating harms that they saw were that extractive practices of data resources of humans, exploitation, particularly in foreign places, the invisibilized, the amount of humans in faraway places that support the cleanup of the data and the delivery of AI is just starting to come to the surface. And they were beginning to recognize the hidden human factor in AI, environmental destruction, as well as the concentration of economic power. All of these things were being intensified by this process. And so as a group, it started to kind of feed a kind of maybe we need to update our myths about what is possible, that it's not just all about being smarter, leaner than what we were, but also recognizing how is this affecting the groups and the intergroups in interesting ways. And one of the things that I would assert here, some additional limitations of LLMs that are known to have problems. For me, the one that I want to build upon in this conversation is the architectural failure of chatbots to support nested learning of networks, this kind of the different parts of the being and the different layers of the being. Still, the work was very, very fruitful, and it was well built upon. The EU incorporated whole aspects of it into its vision for the AI Eurostack. In China, several organizations, learning festivals, and such have built upon it in different ways. It's been translated, I think, in over 7 languages, and is being elaborated, evolved forward in many, many ways. And so I had as an aspiration, because our community is a learning community, how to bring, if you will, not just the engineering techno-savvy perspective, but also other non-US perspectives on the macro trends, and how might that serve or feed our own active inference community. And I think one way of summarizing that would be to say that people are also infrastructure, and so it becomes an invisibilized aspect of really optimizing the place and space if one sticks to the tools and the automation without really accounting for how the humans are part of that living infrastructure. And so with that, as I opened up conversations, I ran into some problems. I was engaging in bioregionalism, supporting this environmental movement called bioregionalism that looks at kind of what are living areas, that it might be a watershed, it might be a forest, that are self-contained unique living systems and often adjoining each other, and that this might be another way in which humans can be in relationship to the places that they are, that they're not just in a for example, the state of a political state, but that, for example, I who live in Washington live on the Chesapeake watershed, and I'm in an ecotone that is three different bioregions. The South Atlantic, the North Atlantic, and the Appalachian Mountains come into a kind of confluence and create a biodiversity hotspot. That is not how most people talk about Washington, D.C. So this movement about orienting to life and living systems has been a growing movement worldwide. And then one of the questions was, how can AI be talked about in those spaces? And some of those conversations turned out to be what it would trigger the, AI is going to kill everybody, or AI is, the usual. And so after a couple of attempts, I have landed on these 3 topics as ways to both talk across different communities, and this is part of what I'm testing here in this delivery here today. That the following 3 themes are ways to think not exhaustively but usefully about human and AI interactions and learning. So about data. Data is a well understood phenomenon by many, and yet most of us are. The data of our own lives, for example, is managed by others in other places away from us. And so I think of, in this picture, you see a picture of my Gmail inbox and my communication patterns. It turns out that relational dynamics are predictive of your happiness, of sales effectiveness, of a whole variety of things that people tend to explain and figure out through other lenses. And if you're able to take your communication patterns and render them in a social graph, you're able to see dynamics about your relational patterns that enable you to choose differently than you might when you're using linear and rectangular presentations of your own data. And this is a really important notion to get, because it's this whole systemic relational data is something that happens in layer after layer after layer. And sometimes we have to see it at the level of me in order to then feel more skillful or more confident about talking about and how does this play itself out in other spaces. So this level of seeing our systemic data and taking ownership, having support for easier ownership and integration of our data so that it's not fragmented across Google and Yahoo and 20 other thousand places, but that we have tools that enable us to mine our own insights about ourselves instead of it being corporations that are selling things to us, is one of the ways in which a civic platform can help make our lives easier and see our own data in more novel and useful ways to ourselves. That pattern repeats at the level of groups. This representation that you see here is 7 different data coding teams that all used the same architecture, the same platform on GitHub to code a solution to a particular problem. And what you see represented there is their data calls, the components that they used, the pattern, how they solved the problem, even if they were using the same tool sets in a sense. And you begin to see that there are additional ways to see how the living sense making is happening, whether it's at the level of individual, at the level of teams, et cetera, et cetera. And so a third dimension of data that can be of interest is what I'm calling intersubjectivity. Now, we all have a sense of our bodies naturally give us sensory information that we then translate into our own actions. As groups, we also use language to get synchronized and orient towards common goals. One of the things that science is helping sharpen is, let me reframe it this way. A Nobel Prize was won by Elinor Ostrom, who recognized that when groups organize, that economists used to describe it as either as hierarchies, institutions, as marketplaces, and she recognized that there was a different kind of human grouping. She called it a commons, a group that self-organized and practiced shared care. It could be like fishermen around the fishery, and that their rules were not hierarchical or marketplace, but were others, and that these kind of self-organizing groups, these natural groups, were everywhere, and that they basically operated according to 8 principles if they were sustainable and functional. And these 8 principles can be used to gauge perceptions of how functional are we being, what is our level of symbiotic cooperative fitness, and that becomes a way to support the evolution of groups forming into from baby groups into mature adult symbiotic groups, and that this is a class of data that pays attention to interiority in ways that also builds relational spaces between humans. So, switching now to the next topic, away from data and onto compute. Here, I'm just going to talk about what for me are some of the interesting. For me, have been some of the interesting insights from active inference. It is far from complete, but when I try to talk to people outside of the community, some of what's in it for me that might be different from a computational perspective. And perhaps one of the hardest to both intuit but most useful might be the idea that AI that everybody gets is kind of like pre-trained. It's like canned beans. They were harvested, they were prepared, and now you can eat them as prepared, but they're not going to change or evolve in any way. It is pre-trained. And so these chatbots are things that can ingest the entire web, and if you want them to be current the next day or 3 days later, you have to re-ingest the entire web. They are not really, they're capable of doing the ingestion, but they're not continuously adapting and learning. And so the architecture of active inference is one that both these types of computation have learning methods, but in a sense, the ChatGPT, and this is an oversimplification that many in this group will probably debate, is that not only is it related to only the past, in a sense, not the present or making predictions about the future, but it completes its training loop and then works for whoever the user is of that particular canister, that cognitive capability. Active inference can behave at the clustering level, and so it crowdsources what are the predictions of the group and what are they predicting, and then based on errors is readapting or re-evolving forward what has been accurate or inaccurate about the group's crowdsourced prediction. And what that enables is it means that as the group faces stable conditions, they stay on course, whatever course that they were on. But if new conditions change or new circumstances arrive, then the updating of expectations and the co-synchronizing of behavior all happens in real time, which is how living systems kind of stay attuned and adapting forward continuously. And so it's a kind of distributed learning that that is not present in these other forms of what I call pre-trained GPTs. A second is that dynamic capability allows for new degrees of freedom, is how I describe it, but it allows for new capabilities to emerge, a new creativity, which we see over and over and over in the ingenuity of living systems. And in part, the logic of this is that in order to, in system thinking, there is a rule, some would say a law, that says that in order to control that system, let's say it has 10 dimensions to it, then you must have control mechanisms that either match the number, like 10, or exceed it. If you have fewer, then you're only able to influence, but you cannot control the complexity of that system. And so matching the complexity of the system that you're facing is an important aspect in developing greater and greater mastery over things in the world. And one of the things that language allows for groups to do together that they cannot do alone is that as groups, new language can be developed to describe what is being seen collectively, and then that terminology can be used to then co-behave differently, co-adapt. So it allows for groups to also perceive together and then synchronize and do as groups what they cannot do alone. And so this linguistic development is the mimetic, or the linguistic, the development of the vocabulary is what enables the creation of new forms of competence. And that active inference has algorithms that, when we were looking at the previous diagram on the previous screen, that the ability to evolve its assessment of what the error was, and then how does it weigh correcting forward, means that as a group, the co-correction can become a new shared capability that allows for the group to do at the level of group what it can't do alone. And so this is part of the miracle of adaptive learning, you could say. It allows for the continuous adaptation the way that life does. Last thing I'll talk about computation is that there are new classes of learning metrics that become available. What is learned by which actions? What is the information gain of any particular learning activities? And in the environmental space, for example, there have been new ways of talking about the thresholds of planetary carrying capacity versus individual. And how does the relationship between the individual, for example, consumption of water, and the capacity of the watershed, how are those two related? And those enabled for new quotients, new ways of measuring, new ways of monitoring the sustainability of, let's say, a watershed, the use of a watershed, water footprint or carbon footprint, that become these vocabularies that we now use to understand the flow of water, the flow of carbon through a system. Similarly, this idea of agentic learning and the field learning can have baselines and thresholds that are related to each other, so that these become benchmarks that one can begin to make new kinds of comparisons, new kinds of metrics for the learning of groups and groups of groups, and their overall, the value and totality of their learning. So jumping down to the third topic, the final topic, and I know this is running a little longer than expected, is paper. And all of these different data types, different informational sense-making types, all create new ways of learning and new ways of weaving new learning to add value to the new economy. And whether that is to make faster cars or leaner cars or cheaper cars, or whether it is to interact with other social systems and ecological systems in entire new ways, there are a whole new set of job opportunities arising from these new competencies. And so positioning to provide some of these advisory services, these knowledge collection services, these knowledge curation services, is all part of the reason why this idea of a net zero from AI is entirely plausible. I'll just share an anecdote before moving to the next screen, which is there's a variety of countries, and I think of the richest region of Italy, Emilia-Romagna, is composed of almost over one third of it is cooperatives. And as they went through digitization and automation over the last few decades, they did not lose any jobs. They continued to lead in productivity and performance, but it was a commitment of the community and of the co-ops to keep people employed. Germany has a similar kind of approach to labor development. They outsource the if you will, the simplest work, and they keep the most knowledge-intensive work locally in the design and the engineering of the work. And so they stay at the learning edge, and they stay wealthy as a result of moving the needle and staying on the edges of the knowledge economy, retaining their people and their human networks as having a component of that adaptive learning as much as the codified knowledge in systems. And so this kind of learning is happening in level after level after level. And two examples here from developing economies is some fishermen who had some reporting to do on the fishery in, I believe this was Latin America. It was a bit onerous for them, and they started pooling resources and activity to both track and monitor their data together. And they started both becoming more effective at their reporting, as well as developing visibility into the kind of things that help them manage their own fishery better. And this kind of self-organizing at the microcosmic level is thing that happens over and over. It's not just the globalized systems that can benefit from these AI systems, but each of us can be tailoring at our local place. And so whether it is health data co-ops, patient-owned platforms, other forms of co-ops, these are coming up left and right. And there's as much a revolution going on in the development of machine learning capabilities, whether it's translating linguistically in different ways or tailoring these capabilities to the characteristics of the place that they're in. So there's a whole range of opportunities for prototyping ventures, for adapting the governance of these, and for bringing things like GeoInfer to the GeoInfer, which is something Daniel prototyped as a synthesis of active inference and GIS data sources to bring the capability of active inference to GIS databases. And so these are just three of the methods. I was going to show a list of allies, but had not consulted. There's, of course, I already talked about this service, so I'll move along. Active inference can help with sense making through its human networks, through traceability of AI, which is a real problem for LLMs, recasting digital footprints, which we talked about, this idea of having methods for how meta-learning happens, as well as these additional tools. Finally, I'll throw out that a consortium of social impact investors in the US have pulled together $500 million recently in the last few weeks to drive three levers that they hope will influence the present and the future of AI, expanding the groups of people that participate in AI design and development, strengthening the organizations that play these coordination roles, and supporting the creation of public goods. So we are wonderfully positioned as a community to help with these. And this is one of the questions that I like to throw out about what comes to mind for people as opportunities for action. So I'll leave as a closing thought, how to better enrich how can AI better enrich the learning networks in which we are all in? And I'll stop there. If you have questions or would like to reach out to me individually, Lennon at caipp.org is my email. Thank you very much.
All right, this is going to be the final pre-recorded video. It is Active Inference for the Social Sciences State of the Art with Avel. Here it goes. It is a lengthy 1 hour and 43 minutes. Enjoy.
So, hi, I am Avel Guénin-Carlut, and this is the roundtable about active inference for the social science for the Active Inference Symposium. So we have, myself presenting it, of course. We have Tadeusz Zawadzki, we have Andrew Pashea, we have Rémi Tizon, we have Mahault Albarracin. And what we will discuss tonight is basically go over what active inference does for the social sciences, if it does anything, which we may discuss at some point. We will each try to give a very broad impression of what our work is about, and each of our work is relevant to this question, hopefully. And then we will discuss, what do we do with active inference? What can it be used for, etc. Such questions. So first of all, I want to go over a very short, very accessible, hopefully, presentation of active inference, which I guess people in the symposium will not need very strongly, but we are trying to make this an invitation for people who are not necessarily, cognitive science people to collaborate and to think together what active inference brings to the table. And so I believe there is a large proportion of the audience that will necessitate primary to active inference if they are to follow anything that we say. So for those people, welcome and thank you. And I will now go over the state of the arts. So first of all, I will define social sciences very broadly as the study of societies. I know it comes as a shock. You have many kinds of social science with different methodologies and different topics. For example, by convention, due to historical contingency, anthropology is mostly interested in stateless societies, while sociology, political science, will be more interested with societies with states, large-scale organization, parliament, election, etc., etc. And there are other disciplines that are interested in stuff in the past, that has material culture, respective history, and archaeology. There is a very broad variety of social sciences. This is why we have a plural to the term. I will not try to define specifically what they do, but I would say in broad strokes, social sciences are interested in social phenomena, and they're interested in finding patterns in social phenomena. And they tend to hold that those patterns are actually meaningful and explanatory. And this is where the notion of social structure comes into play. Most social scientists, I would say, would agree that there is such a thing as social structure, and that are, from the very basic Wikipedia definition I found, it is the aggregate of pattern social arrangement society that are both emergent from and determinant of the actions of individual. It's something that explains individual behavior in the context of society, and that is not, really inside individuals. So this notion brings a lot of questions, actually, foundational ones. First, if there is such a thing as social structure, how is it implemented in human minds? We are not born with a sense of class or with the specific arrangement of French. This is not something that is implemented in our brain at birth. So at some point, we integrate those notions, and there is a specific process by which happen, and this process necessarily will be limited in some way. So the question of how specifically structure is implemented matters quite a deal. Relatedly, there is a question of what is the relation between social structure and agency. So if structure, that is something that is not really inside our heads, can determine our behavior, it does not entail that we are just mindless robots. It does not seem we are. So there is some level we can decide what we do, and some level we are determined by society. This is non-trivial. The articulation between the two is non-trivial, and it is a widely studied topic in sociology specifically. And third, if there is such a thing as social structure, it seems to change over time. We are not in the same societies as our ancestors 20,000 years ago. And the specific rules that apply to social interactions, to engagement, they seem to change between contexts. You do not talk to your boss like you do your drinking buddy, hopefully for you. And these questions, I believe you see this coming, I think, can be approached through the lenses of active inference, which is the product we're selling to you right now. Sorry about this. So let's try to take a look more specifically to what is this active inference thing, which I did not define at any point so far. Let's get back to the basics, which is the concept of predictive processing and the friendship principle. So in 2006, a British neuroscientist called Carl Friston proposed a very basic principle for cognition. That is basically the idea that we do Bayesian inference. I will not get into it, but Bayesian inference is the optimal way that we can mathematically determine what kind of stimuli, what kind of object out there would cause a sensation. Here, H corresponds to hypothesis and E corresponds to evidence. And the hypothesis is, the concept of what's out there affecting us, and the evidence is how specifically it affects us. Imagine if I hear meowing, maybe there is a cat, but maybe there is a audio box that meows all the time, and I can use the probability that a cat would indeed meow, and the probability that audio box meowing would be out there, and determine the specific probability that there is indeed a cat, given that there is meowing. That's the core idea. So, and the slides are frozen again. sorry about this. We have a recurring technical issue with Google Meet. Hopefully this will arrange itself. So you don't need to get about. I just want you to know there is mathematics. The fact is, when you consider complex problems with a lot of parameters, just calculating Bayesian probability of something is not possible. But what we can do is compute what we call versional free energy, which is much simpler to compute under realistic circumstances. And that has the nice property of binding surprise, which means if you minimize free energy, this is a hard upper limit on how surprising the world can be to you. So this is as good as it gets, really, in terms of practical inference. And the idea of Carl Friston is that neurons do that. They minimize versional free energy over models of what is going on out there at the scale of the brain and within the brain at the level of lower neurons on the neuronal hierarchy. So assuming that there is indeed nested layers of neuronal activity that's organized so as to be able to infer sensations and predict what's next, then yeah, there is a strong case that the brain could indeed be able to understand the world and navigate it in the way we do. So this is very abstract, at least for people that are not already into neuroscience. I will ask you to do a very small exercise to get better grip on the idea. There is a text on the screen that says, please do not look away from the screen. I will ask you to look at this text and not to look away from the screen until instructed otherwise. And while very carefully looking at your screen and not elsewhere, I will ask you to pick out something in your peripheral vision that is outside of the screen, something around you, and something that you believe you know what it is. And then, while still looking very intently at the screen, try to retrieve specific details from it. For example, I can see the box to my mic. I know it's the box to my mic, but what I can see now is very much nothing. I can see it's vaguely square, I can see white, I can see there is dark in the white, but practically the sensor information I can retrieve is much more limited than what I need to infer it is the box of my mic. The only reason I know it is because I knew it is before I looked, because I know I put it there, and because there is only so many things out there that could be white and placed there. So you can now look away from the screen. Hopefully, most of you will experience the same thing I did. Pick out a thing, believe you know what it is, and then realize that you just do not have the sensory information necessary to make this inference. At some point, you had necessarily some prior model of what was going on that allowed you to recognize what it was. And before I made you look the exercise, it seemed seamless. You just knew what it is. And that is at core what predictive processing says. So I forgot a bit of a slide. This is a phenomenon that is well known to philosophy of perception and to neuroscience, and it has been for a while. So this, for example, is a rabbit and duck illustration from Pegende Blatter, I do not know how to pronounce this, that was made very famous by the philosopher Wittgenstein, using it to show the, let's say, duality fleetingness of human perception. If you are like most people, you can see a bird, a duck specifically, or you can see a rabbit, but you cannot see both. And the point I believe Wittgenstein was making, and the point I'm making now, is that it kind of goes to show that perception is not purely information processing. It is judgment, it is decisions. You can apply the concept of a rabbit to this, and you can apply the concept of a duck to this, and you will just see a rabbit or just see a duck. And this is something that will be constructive of how you engage with the thing at a very, very basic level prior to your conscious experience. So, let us get in a bit more detail about active inference. Active inference is that it is the idea of predictive processing, as I presented to you, but because of mathematics, I will not get into. Friston and most of us here, I believe, hold that not only agents engage by predicting what causes their sensation, predicting what is out there and cause you to see this white blob on the wall or whichever it is that you picked, we also select actions the same way. The idea would be that we not only predict sensations, but also actions. that we maximize the Bayesian coherence or minimize variational free energy over both, and that therefore both perception and action are guided by near-optimal prediction of ongoing sensory-motor flow. So this idea, I believe, is very powerful, and this idea, I believe, solves lots of very foundational problems in the cognitive sense. I could go on about this for hours, which we do not have, so I will not do that. But I will tell you one thing. As an engineer, I'm former engineer, physicist, technically a physicist. I'm interested in models, I'm interested in mathematics. And something that is very important in most fields of engineering, at least signal engineering, automatics, this kind of thing, is the inverse problem. If you have a forward model, you know exactly how a hypothesis would shape the world. Maybe you can run this through and you can know exactly how a given object would how would your given object would look like to your perceiving robot or something. But knowing what object is out there, given the array of vectors that your seeing robot would see, requires the inversion of your forward model. And for reasons I will absolutely not get into, it's not practically possible for the widest category of models. Let us take a look at this very concretely. And this unlinked again. Sorry about this. This is a painting. I believe you can see a shape that is orange under a dark background. I do not believe you could practically recover what the painting is, unless you know what it is, from this picture. And actually, I know you can't. The painting is this. And, okay, linked again. Sorry about this. The painting is this, William Blake, The Ancient of Days. And just because of the nature of the process, which is a very simple blurring process, well, you can know precisely how this picture will be affected by blurring, but you cannot recover the picture from blurring. And this kind of problem is the kind of problem that we have to resolve every single day. Every time we try to pick out, perceive something, to decide on a motor plan. And there is no way that we brute force it. We have to work around the problem somehow. And this is what active inference. Okay. This is what active inference proposes that we do. This is at the most basic level why I believe that active inference is a correct model of the world, maybe not, specifically precise in the most metaphysical way, but it seems to capture something very important, which is how we use prior information and we use self-organization in the brain to circumvent the inverse problem by anticipating what it is that we will do and what it is that we will see. So let's hope that it did not unlink. It did not unlink. It is incredible. So what this means for our experience of life as active inference agents, I believe you have a experience of life as an active inference agent because I believe that we are that. But when I do sense, we need to put words on things. And I would say the most basic level, if active inference is verified, then we experience the world as a landscape of affordances. Affordances being a technical, ecological, psychological term that says actual or perceived opportunity for action. So, for example, this is a very nice picture of a path in Galicia. That's towards an archaeological site we'll not get to see. Sorry about this. And if I removed it briefly, you remember mostly there is a path and there is green. Because the way it is structured, it is the possibilities for action this image entail that, jump to your eyes. And so you see the path and you don't see that much else. And in addition to that, if active inference is verified, there is not only the prediction of states outside you, which is called exteroception, but also of states inside you, which is called interoception. And because the two are predicted in a dual manner, just like because sensory states and active states are predicted in a dual manner, there is a very efficient use of context. There is a very efficient way in which our bodily perception will shape what we look for out there. If it's thirsty, we look for water, etc., etc. And all of this, again, runs at a very basic level, far prior to our conscious experience. And this entails, I would argue, the dissolution of agency as we know it. The idea that there is a little thing inside of us that has opinions on what we should do and that, neutrally analyze the world out there and takes decisions for us. It is not the case. The world as we experience it is loaded with value, it is loaded with affordances, and a lot of the processes that shape our activity exist outside our conscious grasp. We flow in technical terms along our predictions of what the world is, our world model, and our prediction of what it is that we do, our self-model. And this is a very fundamental insight that has many applications to the social sciences, which I hope we'll discuss later. Here, I will only take a very quick look at what was canonically done to relate active inference to the social sciences. The first paper that I believe qualifies as social scientific-ish is this paper by Brunberg and Rietveld that analyzes, that says basically what I just told you. If the active inference story is verified, then we experience the world as a field of forensics, a field where we can do stuff. And due to version energy minimization, we strive to maintain an optimal grip on it. And it happens to be structured by social and cultural resources. So this is basically everything that active inference sociology people did relies on that framework, skilled intentionality framework. The first major paper that I'm aware of is the Ramstedt et al. Cultural affordances that tries to get into more detail about how we can specifically integrate and perceive such culturally and socially shaped affordances. And their argument is that there is a thing called regimes of attention, which is way of paying attention, way of finding out what cues out there matter and what sense to give to them. And that the inaction of those regimes is basically forced by social activity. So when you participate in social activity, you follow along a regime of attention that thereafter you can mobilize to pick out cultural affordances. From there, there was the thinking through the minds framework that basically agrees with the prior Ramstedt paper, and that further opines that the transmission of culture, as in the sense of human-specific culture, there is a lot to be said about animal culture, this is not what we're talking about, is enabled not only by participation in social activity that are embedded with regimes of attention, but also, and perhaps most importantly, by the ability to think through other minds, by the attitude of when we are confronted to a situation, to a problem, to a thing that calls action, to wonder what would someone else do instead of us, which entails a coupling mechanism between ourselves and other people that's mediated by expressive capacities, and that essentially entails a runaway evolution of culturally embedded cognition. And then there is the paper by Mahault and me, Automated Narrativity, which is interested more in the role of material culture in shaping human society. And our argument is that because of the normative nature of perception and direct inference, because of this affordances thing, material landscape are direct participants in cognition by the fact that they constrain activities towards certain perceptions and actions, which is the essence of cognition, if the regime of attention picture is correct, and which is the basis of behavioral regulation. And also there is other more out there stuff I did, where I argued that such constraints over regimes of attention collectively constitute forms of life, strictly speaking, biological things, biological if not biochemical, that are embedded in patterns of human activity. I don't know if we will get into it a lot because this is perhaps a bit abstract, but I thought this was an important thing to say. Because if it's true, we have two levels of autonomy, ours as biological individuals and collective autonomy of this form of life that we collectively enact. So let us run over core message, core ideas that are relevant to social science very quickly. First, active inference, if it is correct, validates some ideas about within social science. It basically provides a framework that proves that if our nested of cognition is correct, then this idea is true. It also grounds society in the sense that it provides a way to do very specific models and very specific predictions according to those ideas. So this is, in my opinion, a pretty interesting thing, if not a relation of direct constraints. So the first thing that active inference, I would argue, validates and grounds is the idea that social structure, it is not something that exists out there. It is embedded in systems of cultural meaning in a way that we have to attribute, well, meaning to stuff out there. And those systems exist prior or within our basic phenomenology, our experience of the world. And this idea is a very central idea to anthropology, to at least second half of the 20th century anthropology, because it was popularized by Claude Lévi-Strauss within his Anthropologie structurale. The second idea, I think, active inference validates and grounds is that, and I need to put here on the slides, is that social interaction is embedded in such systems of cultural meaning, in the sense that those systems are constraining, but are also expressed within social interaction. And social interaction is not only determined by such systems of meaning, but it also participates in making them evolve. And this is, I would say, very broadly speaking, the point of symbolic interactionism, which is another of the major mid-20th century sociology school. Well, this one is both sociology and anthropology, actually. And third, the same applies to material landscapes. The way in which our physical reality is organized, it signifies stuff, it constrains our attention, it participates in constructing systems of cultural meaning that may or may not be, strictly speaking, life forms. So this is it. Once again, we want this session to be dedicated to inviting people to collaborate on the project of building active inference for social science. And so I will leave you with these two QR codes that are respectively a link to the Discord channel of our project and a link to the course that some of us, Mahault and myself, organized, I think, 3 years back to give a much more extended perspective on what we can do with active inference than we'll possibly do during this roundtable. So I thank you for your attention, and now we'll go towards this presentation of the different participants of the roundtable, starting with Darius. And I hope you got the QR code because I will stop sharing now.
Allow it to share. No, that's not right.
It's fiddly.
Excuse me, sorry. I got it. I think I hit the wrong thing. Wait. Okay, hang on a sec. Share screen. Allow to share screen. Where is it? No. Allow to share window. Okay. Why is this not working? I'm having some trouble here. Sorry about this. Oh, wait, show all windows. There we go. All right. Where is it? There it is. Okay, can you all see this? Hello?
We cannot see anything.
Share this window. Hang on. How about this? Can you see this?
Yes. Yeah.
Okay. All right, I'm going to get started. Is everyone ready?
Yep.
Yes.
Okay. So I love Abel's presentation, and I have a lot of work that bears a close affinity to what he was talking about. But today I'm going to talk about a new direction in which I'm taking active inference in my thinking, and it's about. I think it provides the resources to critically interrogate some very old and classic assumptions about human thought and action embedded in the European philosophical tradition and offer an alternative to them. So intuitively, there is this distinction we make between patterns we find in nature, for example, laws of nature that science finds, and patterns we make, cultural phenomena, mainly music, architecture, dance, technology, language, and so forth. And this distinction has a very old provenance in European philosophy. Aristotle made a distinction between theoria, which is a capacity to discover patterns in the world, and praxis and poiesis, which is about making patterns. And he even hypothesized two different cognitive processes, the theoretical syllogism, one the practical syllogism, underlying these two capacities. This has been taken up in more recent European philosophy in terms of the distinctions in direction of fit. So some cognitive acts and speech acts have a word-to-word direction of fit. What does that mean? That means if there's a discrepancy between what you say and the world, you alter the world in some cases, but in other cases, there's a word-to-world direction of fit where you alter the word to respect the world. So Elizabeth Anscombe has a very memorable illustration of this with the grocery list. Suppose you have a list and you're doing your groceries. There, the word is regulating the world. So if you don't have what you want on the grocery list, if there's a discrepancy, you change the world in order to match the list. But you can imagine a private investigator following the person around and making an identical list, but there the direction of fit is in the opposite direction. The list is modified in light of what the person puts in their shopping cart. Searle marked this distinction as the distinction between declarative and imperative speech acts. Some speech acts, declaratives, aim to track the world, and if they don't track the world, it's the speech act that has to be changed. Other speech acts, like commands, imperative speech act, aim to change the world, and if there's a discrepancy, it's the world that has to change. This has been applied to models, classical cognitive models of the mind, where there's a distinction between belief modules and desire modules. Hume is very explicit about this distinction. Peter Carruthers is a contemporary example where belief modules aim to track the world and desire modules produce states that aim to alter the world, primarily the body. Now, the interesting thing in active inference is that the proposal is the brain doesn't work that way. Here's Andy Clark's very interesting recent article where he writes, desires and motivations are fluently accommodated within the unifying predictive processing schema, where they emerge as webs of prior beliefs that sculpt probabilistic predictions, some of which become positioned so as to bring about actions. Importantly, a single construct here plays the role of belief and desire. So it's a departure from this classical dichotomy between states that have a word-to-world direction of fit and states that have a world-to-word direction of fit. Now, what I find interesting about this is it can make sense of certain phenomena, linguistic and cognitive phenomena, that don't fall neatly into either category. And one such example is the concept of ideology, which has gotten expression in any number of thinkers, including Marx, Foucault, Nietzsche, and Freud. But basically, what I want to suggest is a kind of quick, fast definition of ideology is that it's pattern making and masquerading as pattern finding. So we think that we're discovering a pattern in the world, but actually in believing in that pattern, we are making the pattern where it becomes a sort of self-fulfilling prophecy. The pattern wasn't there, but by believing that it's there, it becomes true. So in ideology, the basic idea is you promote the interests of the powerful by concealing true patterns with masking patterns that victims unwittingly work to reproduce, at least partially. So you might think sort of the Christian belief that the meek shall inherit the earth, or God will redeem our suffering. These help make patterns rather than track patterns that are there independently of these beliefs. Or example from Foucault, it's only natural for men to desire women. Again, it's pitched as a description of a pattern, but it functions more to make a pattern true. Okay, so I think active inference is a really nice way of making sense of a phenomena like ideology. And that is because, as Avel pointed out, What active inference says is that all that matters is that the discrepancy between a prediction or an expectation and an observation is minimized, but there are actually two ways that one can minimize these discrepancies. One can adjust the prediction so it better fits the observation, or one can adjust the world through action so that it better fits a prior prediction. Now that raises the following question. Why don't we just adjust expectations, always adjust our expectations in response to differences, discrepancies between exteroceptive feedback and expectations? Well, the idea is that some expectations, for example, those related to fundamental requirements on survival, like your body temperature or levels of blood sugar, are sticky. And the only way to minimize the discrepancies with relevant feedback is to act. You can't adjust the level that your blood sugar should be at or the level that your body temperature should be at. The only way of minimizing the discrepancy is through action. So as Clark puts it, bringing about action requires attenuating, that is, assigning low precision to the sensory information currently indexing the actual disposition of the body so as to enable precise proprioceptive predictions to prevail. Intentional action thus depends upon a delicate balance that combines precise proprioceptive predictions with attenuated information concerning current bodily states. An interesting consequence is that action thus depends on a kind of systematic misrepresentation of how our body is currently arrayed in space. I emphasize that because it's very similar to the idea of ideology. Ideology is a systematic misrepresentation of the way of the social world, but it leads to a kind of alteration of the social world to more approximate it. So one of the interesting consequences of this picture is that we can replace this classic pattern finding and pattern making disjunction that we saw in Searle and Anscombe. We could replace it with a more nuanced continuum. So here, rather than two categories into which we could place thoughts or judgments or sentences, we have a continuum and anything you think or say can be placed on different places in this continuum depending on how sticky it is. That is, how likely we are to hold on to the belief no matter what, and the prediction error that you get. So diet doesn't impact health. Presumably we're willing to revise that and if the prediction error is high, as it is in this case. But something like life has meaning, even if there's a lot of prediction error, we can't help but hold on to it because it's very sticky. But it can vary for individual to individual or occasion to occasion, and it's a continuous variation, not a discrete one, like in the classical understanding of these things falling into one of two categories. A final area that I'm really interested in applying this to is another ancient tradition, an alternative to the European philosophical tradition, the Buddhist tradition. This is Amber Carpenter channeling Christopher Gowans, talking about the belief in the self. So she writes, the false belief in a substance self, that there is a stable entity distinct from phenomena with which to identify, leads to the sort of mental activity of grasping and aversion that creates, generates, and constitutes the continuum that is what we in fact are, process cells. So falsely taking myself to be substantial generates the kind of thoughts that keep my process self, my continuous self going. And more broadly, I'm not going to read this citation out of interest of time, but the very Buddhist idea that desires help construct our reality is, I think, very compatible with the active inference framework. The idea is that we divide the reality up into the chunks that we see based on what we want, based on our preferences. And if we didn't have those desires, we might divide reality up in a different way. And I think that fits very nicely with the active inference framework. So anyhow, that's the direction I'm taking it these days, and I hope you found this interesting.
Yes, thanks a lot, Thaddeus. So now, yes, let us move on to Matt. And then we'll move to Remy.
Thank you. So I think the talk I'm about to give is somewhat congruous in the sense that you both discussed what it is that active inference allows us to do and how it allows us to frame how we carve reality. But I think I'm about to talk about the mechanism at play when we talk about the ways in which our perception overlays with group dynamics and then shapes that reality itself. And I'm going to go relatively quickly to give Andrew and Remy a chance to talk as well. The core idea here is that every adaptive system, biological or social, operates by minimizing uncertainty. And so active inference starts with the individual. So the self model maintains coherence between internal states of the world, internal states and the world. But because no one can model the entire world alone, cognition extends beyond just the individual. And so to reduce uncertainty, we extend our cognitive boundaries by coupling our inferences with those of others. And this shared modeling of reality depends on shared priors, so overlapping assumptions about what it is likely meaningful or true. And so trust here arises when we assume that others self-evidence as we do, that they also act to maintain coherence between their predictions and the world. And so through this mutual self-evidencing, individuals become part of each other's generative models. They enable social cognition, the ability to think together, to coordinate, and to construct shared worlds. And so these distributed inference loops become the foundation of social identity and group belonging. And so self-esteem here functions as a precision regulator, a dynamic estimate of how well our internal model aligns with social feedback. So when prediction errors are low and feedback is affirming, confidence increases, and when errors rise and feedback turns negative, self-esteem decreases, prompting potentially self-correction. Overconfidence and shame emerge when the system miscalibrates precision. So overconfidence inflates certainty, discounting error signals and preventing learning, and shame amplifies precision on negative feedback, overweighing error and suppressing action. So in this sense, self-esteem is a sociometric gauge of prediction error, keeping our self-models coherent with the social world. And so through this continuous calibration, individuals align with collective expectations and they form more stable social groups. And so social groups can form around shared expectations or beliefs that collectively minimize uncertainty. And so over time, confirmation bias reinforces these shared priors. Individuals selectively attend to evidence that supports their existing models and ignore what contradicts them. It links to what Thaddeus was saying about motivated reasoning. And so this feedback stabilizes social identity, but also traps the group in local minima of belief space, the states that feel coherent internally but are resistant to change. So within these echo chambers, prediction errors are reduced not by updating beliefs, but by filtering experience itself. And such stability preserves belonging at the cost of flexibility. So the system maintains low surprise through mutual reinforcement rather than genuine adaptation. And so once we have these shared beliefs, once they are stabilized, power and influence can determine whose priors guide the collective models. Power here emerges when one agent or an ideology or ultimately a group can modulate the priors that guide collective sense-making. Rather than controlling actions directly, influence operates through the precision weighing of beliefs by determining what counts as credible, relevant, or true. Leaders, narratives, institutions steer collective attention. They shape how groups interpret evidence and update their models of the world. Under this view, power is the capacity to steer collective belief updating. It is to define the boundaries of what can be imagined or questioned. And so the group's generative model thus becomes a shared cognitive architecture governed by those who set its priors. And this hierarchical modulation scales from individuals and small groups to entire societies. But finally, we can express cultural, political, and interpersonal processes in terms of shared inference, and we can formalize how meaning, trust, and coordination emerge without reducing their complexity or richness. The goal here is not to necessarily mechanize society, but to make its hidden computations visible, to describe how collective sense-making evolves, adapts, and sometimes fails. And so we can use this to design systems that learn and align together. We can apply it to artificial intelligence, but we can also apply it to policy making writ large. And that's the direction I hope to take here.
Thank you, Mahault. It was fascinating. Remy, are you ready to share?
Yes, I'm going to share my screen or attempt to do it. Okay. Can everybody see the presentation? Yes.
Yep.
Okay. So, yeah, I'm just gonna make it full screen. Okay. So, yeah, I'm gonna talk about things that are really similar to what Tad presented a bit earlier. So, yeah, I'm just, oh, it seems that it froze. Sorry. Okay, I'm just gonna, okay. So can everybody see the presentation?
Yeah.
Yeah, okay. So what has drawn me to active inference is really something that's similar to what Tad was talking about, which is this kind of questioning of traditional distinctions, which have really ancient origins in Occidental philosophy and have been represented also in more contemporary philosophy of mind. So this distinction that Tad discussed between what is sometimes called epistemic attitudes, which have the function to accurately represent the world, so things like beliefs and perceptions, and on one hand, and on the other hand, pro-attitudes, which like intentions and desires, which have the function to change or transform the world. And as Tad explained, there's no such distinction in active inference. There's only predictions, which can be more or less like beliefs, more or less like desires, depending on precision modulation, as Tad explained. And so I think this has a potential to explain, to eliminate a wide variety of social phenomena. As Tad explained, I think ideology is one of them. But what I want to focus on here is the phenomenon of social norms. So what are social norms? Social norms are simply behavioral regularities that are socially maintained in a group. So simply these are patterns of behavior which are socially maintained, which means that members of a group will behave so as to incentivize and reward a behavior that follows the norm, and disincentivize or punish a behavior that infringe upon the norm. And so social norms are just like patterns of behavior which are enforced through patterns of social sanctions. And how do these social sanctions come about? How do they emerge? I think that the active inference framework has a lot of things to say about that. The idea, as I said earlier, is that in the active inference framework, there's no strict distinction between beliefs and desires. So when an agent predicts something about its world, it can either alter the prediction so that it fits how the world is, or it can also alter the world itself so that it fits what its model is predicting. And so in a social group, there will be various kinds of social regularities, ways that people tend to behave in this group. And so we can expect the members of this group to learn these social regularities. So these the models of these agents will tend to integrate these social regularities. They will tend to form social predictions that predict these regularities. And when these predictions are fixed in the model, you can expect something like social sanctions to appear, because as we said earlier, when these social predictions are well confirmed, well placed in the model, the agents will not simply update their social predictions concerning the environment. They will also try to minimize social prediction error by intervening in their environment so as to confirm these social predictions. And so we can expect members of a group that have learned social regularities of their group to enforce these social regularities. That is, we can expect them to start behaving so as to produce in their social group the behavior that follows the norm, and to produce behavior that punishes behavior that violates the norm. And so I think that this erasing of the distinction between belief and desire to have just one notion of prediction can help us explain how social norms appear in social groups and how they stabilize in social groups, because members of such groups will attempt to minimize social prediction error, and not only by revising their own model of the world, but also by actively enforcing these social predictions on their social environment. I think so that we have now better tools to understand how social regularities in social groups can become social norms. So that's what I had for today. Thank you for listening to me. And yeah, I think it's close to what Dad was saying about ideology, but it's kind of a spin on the notion of a social norm.
Okay, thank you, Remy. I will do the next one, if I can share my screen. Okay, so this is, I think it was originally a 45-minute presentation. I will go through it very quickly. So the thing I want to talk about is my contention that we can actually make things up and it matters, which I will explain very shortly. So first, the way that we engage with the world displays very clear signs of what we call open-ended evolution. We can make new things up that do not seem to follow very clearly from pre-established law or principle. For example, we can build a city, and then there is an entire new level of organization that follows its own rules that are constrained by, but not strictly entailed by, prior law of physics. We can make signs that mean things, and because we treat them as meaning things, they do indeed seem to mean things. At least they work to signify stuff, and they work to constrain our cognition. And so there is I would say, very, 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 very strong case, and a quite trivial one at that we can build uses of the world that causally matter. And there is an entire subfield of physics that, yes.
Well, I'm sorry. I think your presentation is
Frozen. Thank you.
It's back.
And so I will not go into detail, but it's hard to represent and explain physically, because in physics we tend to have specific list of states that define a system, and we can't just tell to the math to invent new math in the middle of doing math. That does not work. So most of it is what I showed you about active inference. What I want to get at is the following: contextuality in life and cognition. There is a very basic concept in quantum physics that is, I think it's simple, but it's the reason why everyone is so confused about it, and it sounds very weird. That's called contextuality. So at a very basic level, I don't really want you to read that, but I want you to know that the math exists. The kind of system we study in quantum physics, they are vectors And there are vectors that are kind of like probability distributions up to squaring, but whatever. And when we do an observation, what we observe is not the vector, but eigenvalue, multiplicatively stable value of the vector given the operator. So if I look at energy, I can find any of the level of energy that are defined by the operator with which I look at energy. And what this means is that the physical act of observation, in Untether again, gladly, I don't have much longer to talk. So the physical act of observation in a contextual theory cannot be understood to reveal pre-existing states, even reveal up to noise. It brings them about. And there is a quite simple way to show it from a thermodynamic perspective that you would know about if I could make this slideshow work. Which is that if you want to observe an object, you're reducing the entropy, and the entropy has to go somewhere because we live in a bounded universe. And so every time you observe some information, you destroy some information somewhere else. And this is something you cannot escape if the universe is bound by thermodynamics, which I will very much assure you it is. And my contention here is that, human perception is in fact contextual, maybe not quantum. I do not have the contention that our brain is a quantum system, but at the scale of function activity, which is relevant to explain and understand our behavior, it is contextual. And the duck rabbit is a case in point. You can observe it as a rabbit or as a duck. You cannot do whichever would be a neutral process of observation that would neutrally constrain action down the line. You either perceive it as a rabbit or you don't. And in the same, in the same way, when we observe material landscape here, pathway in the forest, we can observe it as a pathway. We are actively projecting contexts that are defined by the priors with which we look at situation. And the priors in the rabbit duck case is that there is such a thing as a duck and such a thing as a rabbit, and they are different things. And the prior here is the fact that we are physical bodies which walk upright on feet and can walk in a pathway, but not through a bush. Mice would likely not see the picture as we do. If you could get the mice to look at the picture, which is an entire other story. And this is nerve-wracking. And this becomes very important when we consider the constructive nature of cognition and of, the communication system that we build. We can just decide that something is a letter, and then we can use it to communicate. We can just decide that something is a word, and then we can use it to communicate. I can just decide that this gesture means okay, and this gesture also means okay, and another one I will not show means I don't like you. We can decide this, and then we think in those terms, and then it becomes actual determinants of social organization. And the entailment of this, if I am correct in the broader scheme of things, is that there is a process by which we can observe reality, observe social reality and material reality in a way that basically tells us what the constraints over what you can perceive are, what are the letters, what are the kind of path you can go down, and the kind of path that, no, you cannot. I assure you, you cannot do that. And because this process is not, purely Platonic transmission of pre-existing ideals, because it is something that requires trial and error and misunderstanding, it enables the possibility for open-ended evolution. And this is this, tension between what we want the world to be and what the world is that enables that. And moreover, I would claim that if this thing is related, we can understand sociality, at least the kind of norms that Remy was talking about, but more broadly, the constraints that the material and the social context bears into our cognition, they can be formally described as constraints, and they can be formally defined as a closed system of constraints, where every constraint brings about other and is brought about by the other. And that's what at least some corners of the inactive literature called biological autonomy. So if this is correct, then there are structural life forms, and there are several layers of autonomy that are embedded in human society, from the level of, well, basically down to the level of ourselves and up to the level of judges, parliaments, discussion about whether social organization. And this is, I would say, the core idea I'm campaigning for. So, thanks for your attention. I hope it was a short talk. It's your turn, Andrew.
Okay. Okay. Can you guys see and hear everything okay?
Mm-hmm.
Great. Yeah, thanks. So, wasn't quite sure what to expect from the roundtable, so I did not give any kind of like redux of active inference. I've done that a lot over the past couple of years. I'm also going to set a 5-minute timer for myself. So this is effectively just like kind of a snapshot montage of some of the things that I've personally been working on. And it starts with, hopefully this maybe fills in some gaps regarding something like affordance sharing for anyone who watches this. So there's 3 slides total. I always overpack them. This first one is essentially a summation of sort of what I did last year at University of Pennsylvania, which was give a 3-hour tutorial, somewhat Ryan Smith style for anyone familiar with his work, on creating agent-based models using the active inference framework, but now in more of a social science focused multi-agent setting. I think from my perspective of the field, there's a lot more work to be done on multi-agent, agent-based modeling, especially with applying active inference specifically, or even just any kind of sort of cognitive or autonomous agent model in general. During that 3-hour tutorial, I kind of make this narrative, this argument that seems to be happening in computational social science, where those who do engage in agent-based modeling are repeatedly coming back to ideas of what is cognition and what does it mean for an individual to have beliefs. And so whenever it comes to doing agent-based modeling, where traditionally, due to low computational resources and power, we've largely relied upon very simple conditional rules that agents follow whenever we actually simulate their behavior, which, you know, there's sort of the justification for that is, well, one, we don't have the computational power to create an agent who's necessarily able to emulate sort of real world behaviors that we find in other areas of science. But then also, well, if the model is sort of real enough, if it exhibits enough sort of verisimilitude, then that's enough of a justification. And then whenever you start to imagine trying to simulate, say, hundreds of agents simultaneously, you're definitely reaching the limit whenever it comes to concerns about computational power. So I'll attempt to speed through the rest of this, but this is simply anyone who's interested in that tutorial I gave. There's roughly 70 to 80 slides of material, as well as all the code for this particular simulation, which I taught everyone sort of how to recreate. This is a classic computational social science simulation by Laser and Friedman at Northeastern and Harvard, respectively. And this is a way of looking at agents in a way that they're composed in networks. And so suddenly network science becomes relevant, looking at agents who maybe interact with particular agents, but not others. We often think of, you know, societies or collectives at varying levels. And so basically this almost provides a kind of sandbox to allow for testing agents in different kinds of networks with one another, with different network configurations, and have them do what we could phrase as parallel problem solving. And so this kind of boils down to, how do agents collectively solve problems, which is something that I'm personally very interested in. I think that culture in some ways could be read that way. I think that sociology in some ways could be read that way. I think that if we're able to have different kinds of proxies for, I don't know, say we need to have food to live. And so whenever we organize different kinds of agricultural and distributional systems around food, and those become sort of a, you know, a basis for being able to have a society, otherwise it dissipates, you know, having those kinds of perspectives of these are agents who are collectively, you know, trying to maintain their homeostasis, or however we want to phrase that. But that's sort of what, those are some of the kinds of dynamics that this simulation gets to. And then by being able to use active inference agents, you can see how the simulation is reconfirmed using the old agent-based model as well. But here we have agents who learn, who adapt to the particular network configuration that they're within, the kinds of ideas that are being shared. We do find semblances of a lot of the kind of phenomena that that I think Mao was referencing earlier. Here, there are agents who they share ideas with one another, trying to find the better solution. But whenever agents are too heavily connected with one another, sort of like our modern world a little bit, and thinking about interactivity on the internet, attention is so broadly distributed that what happens is that agents tend towards actually converging towards whoever seems to have the best idea. And then whenever that happens, the diversity of ideas and solutions to a problem starts to dissipate, and everyone's kind of limited by the leader at the top. And so if that leader at the top sort of doesn't quite have the right idea, or it's not very well reflective of reality, then what you find are a lot of agents kind of converging towards you know, ideas that might be very much maladaptive, or be more focused on the social dynamics between the agents rather than actually solving the problem. So that's a bit abstract, but it's just what I find very interesting in the framework is the of active inference is relating it to neurobiological plausibility of getting down to sort of first principles. I've done a variety of different kinds of projects, and so tomorrow, which has kind of been my main focus this week in preparing for a presentation, was this model that we're actually making in more of a computational psychiatry setting. And so I'm actually working with a clinical therapist who's done a clinical study with 7 individuals who have PTSD. And this is sort of that, how do we bridge the qualitative to quantitative gap in the kinds of data and information we can collect and then kind of compose and analyze or interpret in the formation of a study to yield some kind of insight. And so we're effectively making a model that somewhat kind of replicates a lot of the behaviors synthetically produced from these 7 different accounts of individuals with PTSD, as well as, of course, a lot of other sort of empirically inclined literature. There needs to be, in active inference, there needs to be a lot more kind of work on validation of different kinds of models. There's been a lot of great work already done with like Asumura Takuya, who's done a lot on validating this sort of at the cell culture or neuronal level. And so I'm very excited to see where the social sciences can kind of take this next in recreating like broadly social behavior. So with this particular example, this is an agent who, analogously exhibits the symptomatology of PTSD, but they're in a social task. And so we're looking at something like epistemic trust. We're looking at what does it mean to pursue your own individual goals while simultaneously needing to potentially rely upon others. How do you establish that kind of trust? What happens when trust is lost? What happens actually in the body? So there are aspects of like modeling the autonomic nervous system here and relations between affect and emotion. Yet another kind of reference back to some of the things that I think Mal brought up earlier with sort of having a sort of emotional sensor, or looking at precision modulation, changes in confidence. All those dynamics are here. There will be more on that tomorrow. And then finally, this is a little much, but this is just sort of a quick overview of some different kinds of things I'm looking at right now with agent models. I'm deeply involved with the Active Inference Institute, where I teach the textbook with Daniel Friedman. I'm involved in a variety of projects. I look frequently at different computational resources that are being developed that people could use, figuring out how I can use them, and then how I can teach others to use them in potentially new or creative ways. And so, I'm just interested to see what we can do, not just with optimizing agents and systems for accomplishing real world tasks in the way we want them to do, but actually looking at how do agents on their own, so to speak, kind of interact amongst one another. So the upper left, this is just, I'm interested in mixed models. You know, a lot of people are using POMDP models to emulate decision making, but I'm more interested as someone who my main career is as a data analyst. I'm looking at different kinds of data all the time, and so I'm interested in like how do we include continuous data. Of course, there are many ways to do that in active inference, but it's just what are the ways that sort of neurobiologically plausibly align with what we can make, what we can emulate, and then what can actually scale, right, such that we can reach those kind of dreamed 100,000 million agent level agent-based model simulations, and what can be fit to real empirical data otherwise. So I'll stop there. I went much over on time, but thank you for your attention on all that.
Thank you, Andrew. So we went a little bit of time. We spent 70 minutes on the presentations instead of 45. This is okay. So to my knowledge, we do not have any hard time limits. Now, is there a limit on the Google call? No, thank you. So we don't have any time limits. I don't have any time limits. So like for me, it is very much okay. So what I would like to happen for the rest of the session, however lengthy it gets, is for us to discuss what active inference brings to a table for social science. It is, I would like it to be a very open-ended conversation. We can talk about anything that we like collectively and individually. Just has to be somewhat scholarly. Also, I'd like us to talk roughly equivalent amount of times, each of us. I don't think we have a timer, but I guess we can be mindful of that. And I would also...
excuse me, do you mind if I take a quick break before we start? Because
okay,
I'll be right back. Sorry.
Yeah. And last thing, we can, like if we want to show things, we can show things. We don't have to just talk. There is an interesting graphic we think of. We can share it. So just to break the ice, I'd like to ask one question. I would say we are beating upon the contention that there is indeed some value that active inference has for this social science. I would say there is a pretty strong case to believe there is not. Social science have existed for a long while. They have existed with very limited information about cognition, and they functioned this way. You don't need to have a very specific model of the hypothalamus to know what symbolic threat is. And yeah, so what I would like to discuss is, in your opinion, what it is that active inference brings to the table for this social science, how valuable it is, what are the terms in which it works, do we reduce social science to cognitive science, or is this something more integrative? And if we are convinced that there is indeed value to active inference, how do we tell this to social science people that maybe are not very interested in learning a lot of mathematics for pretty questionable value from their perspective? Oh, I'm hardballing. Yeah, we don't have. Please go ahead now.
Yeah. Well, I mean, that's what most of my thesis motivation section was about, basically saying, why would we want to apply active inference to social science and what's in it for them? And my answer was predictive power. That's one of the things that social science really doesn't have very much. We have a lot of descriptions. We think we understand things. We can discuss about phenomena and critique it. But when it comes to actually predicting things, we're very bad. And that's partly because social systems are extremely complex and they span over multiple scales, and a big chunk of it is subjective, i.e. not accessible through real objective metrics. So it's really hard for us to get a real insight, and that's part of what active inference also gives us. It gives us what we could consider to be a mechanistic map of the processes that we can then leverage to make predictions based on measurements we've taken for years and years and years. Sociology, psychology, anthropology have made a lot of measurements, if not a lot of very good predictions. And now what we can do is, okay, well, now we've got this mechanism, we can potentially fit to all those measurements we've taken. What does it allow us to say about, the future at X time scale?
Yeah, so we don't have to raise the hands every time. I guess if it gets a bit competitive, we can do that. But just for context, Thaddeus, what I asked the main question, which was a bit of a hardball, which was, why do we believe that active inference has anything to bring to social science?
Oh, okay. Should I go now, or? I just wanted to riff off of what Mahault said, which is, but just the only thing I'd add is that a nice thing about the active inference framework is it doesn't just give theorists a predictive purchase on this complex domain, but it explains how humans non-theoretically can adapt to this complex domain without having an understanding of it, right? That's what I find very interesting, is that because we through the mechanisms that I was describing regarding ideology, but also Rémi about norms, it shows that you could have a sort of relatively cognitively cheap ways of creating social consensus and enabling coordination, making people more predictable to each other without them having to understand how it's done, how this very complex domain functions. So I think that's a really nice kind of corollary, maybe, of the active inference framework.
Yeah, just quick comment that I think because I'm regularly interfacing with people who are very interested in active inference and trying to figure out how to apply it in their respective field, it's something I notice people frequently kind of flock to is the notion of the Markov blanket, whether they're very familiar with the notion of what it means to have like a conditional independence or not. The idea of being able to separate out what is a thing, which becomes very relevant in social science whenever we say, like, what is a society, what delimits that society, what is inside of it and what is outside of it. And I think that I've enjoyed talking about the notion of the Markov blanket with others whenever they try to conceptually model out, like, map, like what is a society, what are these different institutions, and then if you could reach some point where you could delimit what are sort of the inputs and the outputs, or the sensory and the blanket state, active states in relation to those entities, then you become much closer able to actually specifying a system where you're not getting so confused whenever you change different scales, right? Because social science is like, we'll break things out into a micro scale and a meso scale and a macro scale, or others will look at things at different time scales, like the Annales school with history and Fernand Braudel, that sort of thing. And I just think it's great, but I think that active inference supplies a very strong framework for looking at many phenomena, as opposed to kind of, siding with your own like little sub-discipline silo in how you look at things, and then kind of either casting out or getting in a debate with others, but not making much progress beyond that without making too much assumptions about how others operate.
Yeah, I mean, another thing that beyond the interdisciplinarity, which I agree is because it acts as a lingua franca due to its precision, and due to the fact that Carl and most of the people who have developed it come from, to some extent, a degree of the social sciences, at the very least cognitive science. So the language that they use has been nicely couched in this sort of veneer of accessibility for social scientists, cognitive scientists. But I find that another benefit, which perhaps not everybody will thinks is a benefit, but coming from queer studies, gender studies, is its amenability to postmodernism. you mentioned it, Thaddeus, with the constructionism, but I feel like it gives you a concrete foundation to make those claims beyond just the observation that it really does seem like the concepts have different meaning for different people, and they seem to lead to different kinds of conclusions for different people as well. But under active inference, you can literally couch that under, yeah, your mapping is different because you've carved reality at its joints differently. And therefore, now that you've carved reality at its joints differently, you're going to sample reality and shape it through your sampling also differently because of this joint distribution, and therefore the ways in which your boundary coexists with the world and forces it into a certain way. And that's profoundly postmodern. And I think it also eschews some of the issues we found with postmodernism, which is, okay, but now what? If you accept that things are relative and hard to measure, that measurement itself is a bit not fallacious, but begging the question to some extent, what do we do? What do we measure? What's the future? I think active inference sort of answers that question. It's like, okay, yeah, sure. We can map all these different ways of couching reality, and it is amenable to a dynamism of perception itself and to cultural influences, but also we can map things to each other. Like we can understand how perhaps through this anchoring with common observations, you have seen something slightly different given your vector. And we're now coming to the point where we can apply things like perhaps category theory, cohomology, and all kinds of mathematical tools to understand how these different things map to each other without having to resort to, well, nothing's real, nothing's true, we can't do anything.
Yeah, so I strongly agree with what Mahault just said. Up to postmodernism, I'd say I'm not a fan of postmodern theory for much reasons. I can't stand some Foucault, but that's pretty much it. What I would say is there is a very strong record of social science that try to work with laws, positivistic social sciences, that try to measure behavior in isolation and then use it for prediction. And this record is absolutely terrible. There is no reproducibility for anything. Most of the time, there isn't even a coherent theory behind predictions. And at some point, I will share a thing because such is my power. At some point, there is a very strong contention that agency matters. And agency is if the active inference picture is concrete, more constrained by how we happen to perceive a given situation than by pre-existing mechanism or social structure in a very strong Marxist-ish sense. And then what we are left with is what Goffman calls frame analysis. It is semiotics. It is specific fields of visual science that have studied how we signify stuff and how we understand stuff. And to me, it's a very strong result that if active inference is correct, then those fields are in their basic ontology correct. The object they posit exists, they're valid construct, and we can work with them. Because such is not true for, say, social psychology. We cannot just, well, we can just measure effects and then expect them to replicate outside of context, but it did not work. It did not work very well. And so active inference seems to be correct from an empirical perspective because, again, this is my basic contention. We do not have another theory of how we can circumvent the inverse problem. And maybe its formulation is not wide enough. It's too restrictive. I do believe that the formulation of the energy principle is restrictive. It's one of my horse battle. But the basic structure of it seems to work. There is no competitor to that, and it seems to flow from very basic physical principles. So I think it's a very strong indication for some tradition of study, which do include queer studies, which include symbolic interactionism, which include the most constructivist interpretation of structuralism. And to me, it's a very strong result because we can not only say that, again, those fields have theoretical constructs that work, but also now we have a way to model it that is not based in speculation, that is based in very specific computational hypothesis that translates the basic physical principle of cognition. This is I cannot say that this will make and break sociology. This is ridiculous. This is another field with its own theory. But this is, I would believe, a force that is very important to validate and verify specific theories within specific fields of the social science. And this is where Mao was talking of lingua franca. I think this does that. I think active inference is a lingua franca. It's a way to talk and represent sociological phenomena. And so on a bit more negative note, I think also we must be aware to not think it is a self-standing theory of sociology that will replace this or that approach to sociology. This is a cognitive science thing, and it works, and it can be made useful for sociology, but there is also a distinction in methodology and in ontology and in what we are trying to do at the most basic level between the two disciplines. So Remy, you did not say anything yet. Do you want to weigh in on this issue?
Yeah, no, I do not have that much to add, but thank you very much for giving me the opportunity to intervene. I wanted to come back. Like I'm a mere philosopher, so I don't know much about empirical applications of active inference. But I was wondering. So Mao, you said earlier that there's a potential for better predictions in social sciences with active inference.
Yep.
Oh, yeah. Okay. Sorry. Okay. So yeah. So do you know if there's like work that are is it just like we're thinking that there might be better prediction, or do you know if there's current work in social sciences that use active inference and that yield better predictability? Do you have any? So I would be very curious to see if we have this additional benefit of active inference in the social sciences.
Yeah, anything that relates to social systems, I know, but it's generally used in industry, right? So, for example, the company Versus, which I'm part of, uses it to do market predictions. I know that CogNarr had done a lot of simulations for social groups. One of our simulations was about predicting opinion dynamics within social media. We're being approached by multiple companies to do, say, marketing trends, etc. So it's just that I think what's missing a little bit is heavy work on empirical validation. Part of the benefit of active inference is it can be leveraged by one person. So you can get into your computer, make a little simulation, and it has some degree of validity because you can reproduce an existing phenomenon. But gathering a lot of data is really expensive. So we're still missing large-scale studies of the kind, but Ryan Smith is doing such studies right now. And he is getting predictability. So it's not that it's not happening, it's that these are the kinds of coalitions that take a lot of funding, a lot of coordinated efforts, and ultimately the things which social sciences are good at, which is taking measurements of given social groups.
Thank you very much.
Might just briefly add to that too, that I agree with a lot of Mao's points. There does need to be a lot more empirical data collection. And so what I like, just coming from the kind of computational social science side, I see the strong division between those who would use something like agent-based modeling and recreating dynamics, which are some of the things we've kind of talked about here today. And then on the other hand, there are those who are only looking at very large, like kind of big data level volumes of data, textual corpus, looking at a lot of downloaded X or tweet data or otherwise. And so you get this weird division between like natural language processing over here versus like kind of recreating essentially dynamics that come out of physics numerically. And so I would love to see more of an integration between those two kinds of perspectives. I can't say precisely how that should happen, but I only say all of this because I think that there are a lot of social scientific theories that maybe haven't been able to see their day per se because someone hasn't been able to simulate something or test it on data or otherwise. So I think that active inference here at least gives us the framework to start doing that. again, we need to really build out the toolkit, so to speak, and get more people involved and feeling capable that they can sit down at their computer, give something a shot, and publish their results so we can keep this going.
Yeah, so I would want to get back on what you just said about agent-based modeling versus big data analysis. I would say that active inference gives us a very strong ground to believe that. Sorry, Remy, could you cut the audio? I can hear people behind you, I think. Thank you. So I would say it gives us very strong ground that cognition is contextual in a practical sense, that it depends on context. And therefore, I would place much more faith into detailed agent-based analysis of specific phenomena, try to reconstruct, I don't know, dynamics of influence ritual, dynamics of power in distributed social network, etc., than we could have in a very large statistical analysis, because your stats will be based on a very great variety of contexts, none of which understands, and for which you have no a priori reason whatsoever to believe that it generalizes. So it's a problem with experimental methodology. We never test for ergodicity. We never test that the effect that we measure is invariant between populations. And I would contend that most of the time it is in fact not. And so I think we need to move toward much more detailed qualitative analysis of how people think things. And I think we need to move to models, approaches to computational methodology that reflect that. And that's more in the agent-based modeling brand than it is in the data analysis, strictly speaking. Thaddeus?
You're still muted.
Yeah.
Can't hear you.
This is a different topic. I'm going off a bit, but in a number of the presentations, people talked about how active inference can explain why non-adaptive or maladaptive belief systems are maintained, I think especially in Mao's talk. But I'm wondering what the definition of adaptive and maladaptive is in that context, because of course, for the individual, it's adaptive because you need to respect the norms of your community or the prevalent ideologies in order to succeed in that community. So, are you in? You know, is the idea that the group becomes the unit of analysis here, so that it's a maladaptive group because in the long run, say, the ideology gets the group to deplete natural resources at a rate that threatens its sustainability or something like that? Or is there some kind of normative background that's being presumed in claims that these beliefs are maladaptive, where you're just saying they're just wrong? It's wrong to treat women differently from men or something like that. So yeah, I'm just wondering what your thoughts are on those sorts of questions.
Yeah, so I've given this actually quite a bit of thought. I don't have a formal answer, but I have a thread of research that aims in that direction. And I think you have to think of it in terms of paths and scale of paths. And something we're developing with David Hyland and Dalton Sakthivadivel and Alex Kiefer and other people from the empowerment literature is, and Ben Goertzel as well. There are paths on a given time scale which are irreversible. So for example, if you jump off a cliff, even if you're in the middle of jumping off the cliff and you're not dead yet, effectively, you can't come back from that. That's an irreversible path. And so whilst not everything is as obvious as that, you can sort of couch your paths a little bit like the Feynman paths, where you can see there's a probability distribution over certain paths. And then the probability distribution means that somewhat they're most likely connected, right? There's a probability of going from one path to the other the closer they are, and the closer they are, the more likely they are to be under the same distribution. And so before knowing what a good path is, apply some normative aspect to it. There still are some paths cannot be returned from, and some paths have a high ability to be flexible. So you can go from one to the other. So assume you don't know what a good path is. You still know that if you go in that direction, you're most likely to be able to switch if you were wrong than if you go in that direction where you will not be able to switch. And if you're wrong, you're a bit fucked. And so that's the difference between like a rigid path and a flexible path. So we can sort of take this as a sort of metric that doesn't have any valence to it. Now, considering scales of interest, let's consider that on my life alone, I can make a judgment of suffering, say based on suffering. Well, okay, well, my life will probably suffer less if I max out on one thing. But if I look at a larger scale, say my children or my children's children or whatever, and that's usually the kind of thought process that long-termists take. Yes, I could max out my benefit through like convenience reality that we take right now, but I'm depleting all the resources for everybody else. And so again, this notion of path, yes, my path is still somewhat flexible, but on a larger scale, that path also entails that their paths are now extremely rigid. They have no other possibilities afterwards because their resources are depleted. So you have to consider scale of concern as well. And then the last thing is functionality. Like, it is true that some beliefs can be maintained without losing a degree of functionality if you are not actively acting on those beliefs. So there are scales of beliefs that are differently related to your day-to-day life. And I'm going to use an example that it's potentially, controversial, but if you believe angels exist and that if you jump off a bridge, an angel will catch you, you will die. No angel will catch you. We can test this. Like it's testable. But if you hold that belief with high precision and you take some actions based on it, you will die. But there are people in the world today that hold a belief that is somewhat related to that, if not that. The thing is, they sort of shelter themselves from areas where they actually have to act on those beliefs. So if you believe the earth, if you believe the earth is flat, you probably shouldn't be an aerospace engineer. And it turns out that most of them aren't aerospace engineers. So they can maintain such beliefs in a sort of normative way without them being dysfunctional. But that means they are limited to that sphere of reality. So all of these three things together, I think, lead us to beliefs which can be more or less maladaptive, regardless of the cultural context, which would qualify certain beliefs as adaptive. And then you can talk about just existing within a social context. Relative to a social context, walking around naked is maladaptive. Now, it holds no value other than you will probably incur social consequences along the lines of what Remy was saying. And if you live in Canada, you'll probably, like me, have issues if you walk outside naked. But if you live in, I don't know, somewhere really warm and nice, then the only issue is social. So perhaps you're only maladaptive relative to the current context of the group.
But could I just quickly respond to that before people go? Yeah. So I really love that, and I especially like the first idea that it's without committing to any particular normative preferences, it's better to have open paths than committed paths. This kind of fallibilism. It's a very minimal sort of and plausible constraint on what is adaptive, certainly. But my worry is that there might be situations where just false beliefs basically are extremely adaptive because our most important decision making is social. Mm-hmm. And so it's not just a matter of, you might get some sanctioning in the way, or Remy suggests, but literally like life and death decisions affecting our biological fitness, who to trust and who not to trust, being able to find mating partners. All of these things rely essentially on having beliefs which are complementary to those of members in your society, and that could be anything, right? I mean, if in order to get a partner, a life partner, you have to believe that men's and women's roles, men and women are sort of naturally suited for specific kinds of roles, and that is, it doesn't really matter if that belief is false or anything like that. All that matters is that it matches the beliefs, that it complements the beliefs of the available pool, right, of people you have to interact with. And that seems to be a case where you can have very false beliefs equivalent to a flat earth, but they're not quarantined from action. They're actually involved in action, because all that matters is that other people have equally absurd beliefs for those sorts of social actions. And I guess that's the case that I'm most interested in. All right.
Andrew?
You all just covered a lot of ground, so I'll try to keep it short. But this is a very interesting piece on the maladaptive versus adaptive, and I do think that both of them seem to entail the dimension of time, and so we're talking about something changing, and it can become very abstract, where like, okay, well, anything that changes based upon like some kind of mutual interaction and relationship with things around it, influences, must be adapting, whatever that means. And so yeah, I do think that to say something is adaptive expressly as opposed to being maladaptive is to apply some kind of criteria for how you can judge like how well something adapted or something. Part of what brought me to active inference, aside from a few dozen other reasons, was an interest in mental health and clinical care. That's the computational psychiatry project there that I showed earlier. And one take on the idea of adaptive versus maladaptive is, if an individual themselves expresses a personal disturbance with how their life has been, and they notice it's coming from certain kinds of things that don't appear to be immediately external to them, that is, they are advocating for themselves, I'm having a problem, then it suddenly becomes a little bit more potentially like ethical or reasonable to apply the word maladaptive. Oh, there's something maladaptive, that their life is being led in a direction, or I guess we could say a path, that they themselves don't like, that is harmful to them in some way, shape, or form, right? So that's one take on that kind of divide, and it's so difficult as social scientists whenever we want to make these kinds of divisions, right? Because we're immediately hit with like, well, aren't you just agreeing with one particular set of norms whenever something is adaptive rather than maladaptive, right? And why are your norms better than my norms, or the norms I think should exist, right? So it's just we're scientists within the phenomena that we are trying to study, and it's so tricky. So I don't know if I gave a lot of useful material there, but I hope it is helpful in some way. Yeah.
So we'll need to close this out, sadly, for logistical reasons. I just want to say one thing. I think when we talk about adaptive and maladaptive, what we tend to imagine is some kind of utility theory, rational choice theory of decision, because this is what, I don't know about the rest, but at least the Western canon has theorized for thousands of years. And we think that we infer belief somewhat rationally, and then from this belief we infer desired actions somewhat rationally. And this is not how people work. So Thaddeus described, in my opinion, very relevantly, the social meaning of beliefs. There is a social value to being believed to being perceived as a flat earth person, and so maybe there is interest to talk about flat earth. And this is something that has been studied by the social sciences for decades, actually. I think the most revealing thing I've come across, well, I'm doing hyperbole now, but something very interesting is the study of authoritarian personality by Theodor Adorno, Frankfurt School, which is by all right someone I should be sworn to kill because I'm not into Frankfurt thing, but whichever. So the point I'm getting at is that you have authoritarian personalities are, by these studies, people from very authoritarian families. And there is always the double discourse of, oh yeah, my father was great, he was the best of fathers. Well, sometimes the eggs spoiled, he told me it was my fault, and then he beat me in the belt, and then he locked me in a room that was dark, and then I starved. But you know, he's a father, he's the best. there is a way in which violence is not only naturalized but presented as a sign of goodness. And this is because within a society, well, a small society, a family that is this violence, you'd rather agree with that. And so you integrate it as the normal way of doing things. And as mostly already pointed out, norms are not, there is no clear distinction between what is normative and what is descriptive. So the norms that you integrate, what you believe the world is what you believe the world must be. At least this is what modes of behavior your attention will be tuned towards. And I want to very quickly point out one political philosopher, my favorite contemporary political philosopher, which is, yes, I want to do that, which is Olufemi Washington guy. And he pointed out, in my opinion, very, very, very accurately that in authoritarian systems that I'm interested in, as anyone that has open news since 2016 understands why. In this context, the role of propaganda is not to affect beliefs, because you cannot just yell at people to believe the earth is flat. They will maybe stop answering you, but they will not change beliefs. What the goal of propaganda is to change what public discourse is accepted, what you think you can say without getting bad things happen to you. And for reasons that are very much related to active inference, what you kind of behavior you expect yourself to perform publicly will couple very closely to what you believe to be the case. And I think that's that little tiny threads that comes from the solution of identity under active inference. It is something that is very strong. It's something that's very robust. It is something that is basically what we can bring to social science as a cognitivists that have a strong interest in active inference and that understand how this kind of thing works. Because not only we have some kind of conceptual thread that has a very high level of validity, but also we have a way to model it and to translate it into specific computational hypotheses and specific frameworks to interpret evidence. So this is, yes. I did not want to articulate closing thoughts, but we are closing at the time I articulate my thoughts. So I guess this will work as a closing thoughts. I'd like to thank you all for the opportunity to talk today. I'd like to thank in particular Mahault for helping me with recording, well, for recording the session and hereby helping me organizing it. It was a pleasure talking to you, and I hope we have some opportunity to get things, get a little deeper at some point in the near future. We will stay in touch. So thank you, and thanks to our audience for bearing with our rants about mathematics and cognitive science.
Thank you.
I think.
Thank you.